Perhaps, as you've looked up at a star-filled night sky, you've asked yourself a simple yet profoundly meaningful question. Are those immense galaxies merely drifting through the endless darkness, or is there a hidden connection between them that the human eye has never been able to see? Remarkably, modern science offers an answer even stranger than imagination itself. The universe is not a chaotic place where galaxies wander aimlessly through space. Instead, they are linked together by a colossal network, stretching across billions of light years. A vast structure that astronomers call the cosmic web. But tonight, we won't be focusing solely on staggering numbers, distant galaxies, or scientific discoveries. Instead, we'll embark on a slower, more contemplative journey, where every luminous filament stretching through space seems to tell a story of connection, of order hidden beneath apparent chaos, and of humanity's remarkably small yet deeply meaningful place within the immense tapestry of the cosmos. The psychologist Carl Gustav Jung believed that beneath everything we perceive lies a deeper architecture, hidden patterns, and invisible relationships that the conscious mind often fails to recognize. Although he never studied astronomy, this idea evokes a striking parallel with the cosmic web. Just as the human mind is connected through the profound layers of the unconscious, the hundreds of billions of galaxies scattered across the universe also appear to be woven together by an immense cosmic network that light has only recently begun to reveal. In this video, we'll explore how the cosmic web emerged from tiny fluctuations in the moments following the Big Bang, why dark matter became the invisible framework supporting the entire universe, what the enormous cosmic voids once thought to be completely empty are truly telling us, and how scientists have managed to observe a structure that the human eye can never see directly. Each chapter will take you one step deeper into the vastness of space, while gently inviting you to reflect on connection, time, and the very nature of our own existence. If you enjoy stories that blend science, the history of discovery, and thoughtful insights into the human mind, consider subscribing to the channel and joining us on future journeys through the mysteries of the cosmos. And now, settle into a comfortable position. Take a slow, deep breath. Let go of the thoughts accumulated throughout your day, and allow yourself to drift gently into the greatest network the universe has ever created. A place where every star, every galaxy, and perhaps even each of us is a single thread woven into an extraordinary story that has unfolded since the dawn of time. What is the cosmic web? Perhaps ever since human beings first learned to lift their eyes toward the night sky, we have carried within us a very special feeling. It is a feeling of being both small and endlessly curious, touched by a quiet sense of wonder as countless shimmering points of light stretch across the deep black heavens. From Earth's surface, the stars appear to be arranged at random. Galaxies resemble distant clouds of silver drifting through the darkness. Everything looks like a vast painting created with light, beautiful, yet difficult to understand. For thousands of years, people have wondered whether some hidden order lies behind that beauty, or whether the universe is simply an endless expanse where galaxies drift silently, forever unconnected to one another. If you are listening to these words on a peaceful night, try to imagine that we are slowly leaving Earth behind. We rise gently, passing through the soft blue atmosphere, gliding beyond the moon, and continuing past our solar system. Behind us, the sun becomes nothing more than a tiny star among billions of others. We travel even farther, crossing the Milky Way, which stretches for more than 100,000 light-years. Then something remarkable begins to appear. The galaxies are not scattered like grains of sand without purpose. From a great enough distance, they resemble tiny drops of dew, resting upon immense strands that stretch across space itself. The farther we move away, the clearer the picture becomes, until the entire universe reveals itself as a vast, delicate network, so graceful and intricate that many people cannot help but compare it to an enormous spider's web suspended in the darkness. Today, astronomers call this structure the cosmic web. It is not an image born from imagination, but the result of decades of observation, simulation, and scientific research. The cosmic web is considered the largest structure ever discovered within the observable universe. It stretches across billions of light years, linking hundreds of billions of galaxies into a system so immense that every unit of measurement familiar to our everyday lives suddenly feels impossibly small. What makes this story even more fascinating is that when the earliest telescopes were built, many scientists believed galaxies were distributed more or less randomly. Each galaxy seemed like a lonely island floating in the endless ocean of space. But as technology advanced, and as humanity began creating three-dimensional maps of millions of galaxies, an entirely different reality slowly emerged. Galaxies do not exist in isolation. They gather into groups and clusters, connected by vast streams of matter that extend across unimaginable distances. Seen from far enough away, the universe resembles a colossal living organism, where galaxies are like cells, and the great strands of matter form a silent circulatory system, connecting everything together. Perhaps this image brings to mind one of Carl Gustav Jung's most beautiful reflections. Although he was not an astronomer, Jung believed that what we perceive is only the surface of reality. Beneath individual consciousness lies a deeper layer that he called the collective unconscious, a realm where all human beings are connected through shared symbols and ancient memories. Looking at the cosmic web, it is difficult not to sense a symbolic resemblance. Galaxies separated by millions of light years are still woven into the same immense network. In much the same way, each human being may appear to be a separate individual, yet deep within our souls, we share many of the same fears, hopes, and longings. Of course, this is a philosophical reflection rather than a scientific conclusion, yet sometimes it is precisely these symbolic images that allow us to experience the beauty of the universe in a more intimate way. Science can explain the structure of the cosmic web through equations and data, but the sense of awe it inspires belongs to a very different realm, the realm of imagination and quiet contemplation. To better understand the cosmic web, we must first become familiar with the elements that compose it. Imagine an enormous spider's web glistening after an early morning rain. Fine strands connect with one another, forming countless intersections. The cosmic web contains similar structures. Astronomers call these long streams of matter filaments. They are like the great highways of the universe, along which matter continuously flows and gathers. Where many filaments intersect, they form clusters, or galaxy clusters. These are regions of extraordinarily high matter density, containing hundreds, sometimes even thousands, of galaxies held tightly together by gravity. If filaments are like mighty rivers, then clusters are the great oceans where every current ultimately converges. Beyond filaments and clusters, there are even larger structures known as walls, often called cosmic walls. These immense sheets of galaxies stretch across hundreds of millions of light years, forming gigantic plains within space. When astronomers first discovered these cosmic walls, they were astonished. Few had imagined that nature could create structures of such extraordinary size while maintaining their stability over billions of years. Yet perhaps what makes the cosmic web truly extraordinary is not the regions filled with galaxies, but the places where there is almost nothing at all. Between the filaments and the walls lie enormous empty regions, known as voids. Some voids span hundreds of millions of light years while containing only a handful of galaxies. If filaments are bustling highways, then voids are like silent oceans, where darkness and emptiness seem to extend without end. This invites a deeply thought-provoking reflection. In our daily lives, we often focus on what is present, while overlooking the importance of empty space. Yet the universe appears to follow a different principle. These vast empty regions play a vital role in shaping the entire structure of the cosmic web. Without voids, the filaments would not stand out so clearly. Without empty space, the network itself would have no recognizable form. Perhaps this is true of our inner lives as well. Sometimes it is within moments of stillness that we come to recognize the meaning of what truly exists. And then an even greater question begins to emerge. What created this immense cosmic network? What force could connect hundreds of billions of galaxies across distances that far exceed the limits of human imagination? Is gravity alone responsible? Or does the cosmic web owe its existence to mysterious components that science is still slowly uncovering? That is where our journey will continue in the next chapter, where the mysteries of dark matter, gravity, and the first tiny fluctuations that followed the Big Bang will gradually reveal themselves as though the universe itself were quietly telling the story of how it gave birth to the greatest network it has ever created. If the cosmic web were made only of the galaxies we are able to see, perhaps the story would be much simpler. But the remarkable truth is that galaxies account for only a very small part of the picture, like tiny drops of dew reflecting the morning sunlight upon a spider's web. Like drops of dew glistening in the early morning light, they reveal only the shape of the web, not the web itself. The force that truly supports this immense cosmic structure is something invisible, something that emits no light and has never been observed directly by human eyes. Scientists call it dark matter. The name dark matter sometimes leads people to imagine a mysterious black substance drifting through space. In reality, that is not what it is. The word dark simply means that it neither emits nor reflects light. And it interacts with light so weakly that it remains essentially invisible to us. We cannot see it through optical telescopes. We cannot touch it or collect it in a laboratory. Yet we know it exists because its gravity quietly shapes the entire universe. Imagine standing on a hillside on a warm summer evening. Before you, a swarm of fireflies dances through the darkness. You cannot see the air itself, yet you know the wind is there because suddenly the entire swarm changes direction together. Dark matter is much like that unseen wind. We cannot observe it directly, but we can observe how galaxies move under the influence of the gravity it creates. It is through those movements that astronomers realized the universe must contain an enormous amount of matter that human eyes have never seen. What is especially remarkable is that if we consider only ordinary matter, the stars, planets, nebulae, and galaxies we can actually observe, gravity would not be strong enough to create the vast cosmic web we see today. Computer simulations consistently arrive at the same conclusion. Without dark matter, galaxies would be distributed far more sparsely, and this immense network would be almost impossible to form. In many ways, dark matter is like the hidden framework of a great building. We admire its walls, its windows, and its roof. Yet it is the unseen structure beneath them that quietly holds the entire building together. In a symbolic sense, this brings to mind one of Carl Gustav Jung's profound reflections. Jung believed that much of what shapes human life does not lie within the thoughts we consciously experience each day, but within the deeper layers of the mind, where memories, archetypes, and unconscious patterns continue to influence the way we think and act. We cannot see them directly, yet we feel their presence in the choices we make throughout our lives. Of course, dark matter belongs to astrophysics, while the collective unconscious belongs to psychology. They exist within entirely different disciplines. Even so, both invite us to contemplate a beautiful idea. Sometimes the most important realities are the ones our eyes can never perceive. Dark matter is not the only ancient secret carried within the cosmic web. This vast structure also preserves the memory of an age far older than any story humanity has ever recorded. If we could travel back nearly 14 billion years, returning to the first moments after the Big Bang, we would find no galaxies and no brilliant stars. The universe was then an immense ocean of blazing hot plasma, where matter and light were blended together in an almost perfectly uniform state. But almost does not mean completely. On the tiniest scales imaginable, the density of matter still varied ever so slightly. In some places, there was just a little more. In others, just a little less. Those differences were so incredibly small that if the entire universe at that time were reduced to the size of a single ball, the variations would be smaller than the tiny imperfections on the surface of a marble. And yet it was from those unimaginably subtle fluctuations that the entire large-scale structure of the universe would eventually emerge. Gravity, faithfully carrying out its quiet work, began pulling matter toward regions where the density was ever so slightly greater. At first, the changes happened almost imperceptibly, but as more matter gathered, gravity grew stronger, and the process became much like a snowball rolling down a hillside, growing larger with every turn. Hundreds of millions of years passed, then billions more. From those faint ripples of the newborn universe, the first filaments slowly took shape. Galaxy clusters began to form. The great voids gradually expanded. The cosmic web was not born in a single moment, but through the almost infinite patience of time itself. Perhaps this is one of the ideas that fills us with both humility and hope. Everything truly great can begin with the smallest of differences. A change so subtle it would have seemed insignificant at the dawn of the universe eventually gave rise to the largest structure we have ever discovered. Life often unfolds in much the same way. Small choices, quiet thoughts, and tiny acts of kindness sometimes require a great deal of time before their deepest meaning is finally revealed. Part of the memory of that primordial age still remains with us today in the form of ancient light. As the universe cooled enough for light to travel freely, the first photons began a journey lasting billions of years before eventually reaching our modern telescopes. Scientists call this ancient glow, the cosmic microwave background, a faint light that still carries the imprint of the infant universe. If the cosmic web were compared to a magnificent ancient tree, this primordial light would be like the growth rings hidden within its trunk, silently recording every stage of its long life. Each time astronomers observe this cosmic background radiation, they are not simply looking at a sky filled with microwave signals. They are looking into the memory of the universe when it was only a few 100,000 years old. The regions that appear ever so slightly warmer or cooler within those maps are the very seeds that, over billions of years, would grow into galaxy clusters, cosmic filaments, and the vast, empty voids that together form what we now call the cosmic web. It is remarkable to realize that every night, when we lift our eyes toward a sky filled with stars, we are witnessing the outcome of a story that began nearly 14 billion years ago. The light reaching us has traveled not only across unimaginable distances in space, but also across the immense depth of time itself. Every distant galaxy is like a letter sent from the ancient past, patiently crossing the universe to tell us the story of our own origins. Perhaps the greatest beauty of the cosmic web does not lie in its extraordinary size, but in its interconnectedness. No galaxy truly exists alone. Every galaxy belongs to a cluster. Every cluster rests upon a filament. Every filament contributes to the immense network that spans the observable universe. And within one tiny corner of that network, our own Milky Way continues its quiet journey, alongside billions of other galaxies. In the next chapter, we will move closer to our own cosmic home and discover something both humbling and wondrous. The Milky Way, our solar system, and even Earth itself do not stand apart from the cosmic web. On the contrary, we are one very small thread within this vast structure, moving together with the entire cosmic network through the boundless ocean of space and time, the immense architecture of the universe. As we concluded the previous chapter, we were left with an image that may linger in our minds for a long time. Seen from billions of light years away, the universe does not appear as a chaotic emptiness. Instead, it resembles a vast web woven from countless invisible strands of matter, where every galaxy is only a tiny point of light within an immeasurably larger tapestry. Yet the longer we contemplate that image, the more gently another question begins to emerge. Does the universe truly possess an architecture? Or is what we observe simply the accidental arrangement of hundreds of billions of galaxies scattered throughout space? For most of human history, people imagined the universe as an endless expanse where stars and galaxies were scattered randomly, much like grains of sand across a shoreline. It was, after all, a perfectly reasonable assumption. Throw millions of particles of dust into the air, and each one settles in a different place. Watch the clouds drift across the sky, and their shapes are forever changing in unpredictable ways. It is no surprise, then, that many astronomers of the last century believed galaxies were distributed in much the same fashion. But science sometimes offers surprises even more beautiful than imagination itself. As telescopes became increasingly powerful, and as ambitious sky mapping projects began recording the positions of millions of galaxies, billions of light years away, the familiar picture slowly began to change. Viewed through only a small window of the sky, everything still appeared random. But when astronomers expanded their perspective to a truly cosmic scale, an extraordinary pattern gradually revealed itself. Galaxies are not spread evenly throughout the universe. Instead, they tend to gather along immense rivers of matter, intersecting at enormous junctions, while leaving between them vast regions of almost unimaginable emptiness. It was at that moment that many scientists realized something profound. The universe does not merely possess structure, it possesses an astonishingly sophisticated architecture. The word architecture here does not imply that some cosmic architect deliberately designed the galaxies. Rather, it describes the remarkable order in which matter arranges itself across the largest scales imaginable, much like a forest that is never planned by anyone, yet naturally develops into a balanced ecosystem, or a river that finds its graceful curves simply by following gravity and the shape of the land. The cosmic web arises from the fundamental laws of nature, yet the result possesses the quiet beauty of something exquisitely composed. This idea echoes a familiar theme within the psychology of Carl Gustav Jung. Jung believed that beneath the seemingly chaotic flow of human thoughts lie deeper patterns that he called archetypes. These archetypes do not determine every individual thought, but they quietly provide an underlying order to our inner lives. In a symbolic sense, the cosmic web is much the same. Galaxies may move, collide, be born, and eventually disappear. Yet all of these events unfold within a far greater framework that gravity has patiently woven over nearly 14 billion years. Perhaps what astonishes astronomers most is not the sheer number of galaxies, but the way they are connected. Imagine looking down upon Earth from far above on a clear night. Cities appear as islands of light, while highways connect them into an intricate network. If you were to observe only a single light bulb, nothing remarkable would stand out. But when you step back and see the entire system, you begin to recognize that everything is joined together by countless roads. Galaxies throughout the universe are remarkably similar. Each galaxy is like a city of light. The filaments are the immense highways that link those cities together. Filaments are colossal streams of matter stretching across hundreds of millions of light years. They are not delicate threads like those of an actual spider's web. Instead, they are regions where matter is more densely concentrated, carrying thousands of galaxies, vast clouds of hot gas, dark matter, and plasma, all slowly flowing under the influence of gravity. If we could behold the entire cosmic web at a single moment, its filaments would resemble luminous rivers flowing through the darkness of the universe. Their scale is almost beyond imagination. Our own Milky Way spans roughly 100,000 light-years, That distance alone is so immense that even light, the fastest thing in nature, requires 100,000 years to travel from one side of our galaxy to the other. Yet many cosmic filaments are thousands of times longer still. If the Milky Way were a small island, then a filament would be an entire continent, stretching across many oceans. For that reason, when we speak of the cosmic web, what truly matters is not any individual galaxy, but the immense network to which every galaxy belongs. Astronomers sometimes compare galaxies to light bulbs suspended along an enormous electrical grid. Looking at a city from afar at night, our attention is naturally drawn to the glowing lights. Yet it is the hidden network of wires that quietly connects everything together. The universe is much the same. Galaxies are simply the brightest, most visible parts. They are like tiny lamps marking the locations of a far greater network of matter concealed within the darkness. And it is here that we begin to touch one of the greatest mysteries of modern astronomy. What truly holds these filaments together? What provides the invisible framework that allows hundreds of billions of galaxies to arrange themselves into an architecture capable of enduring for billions of years? The answer lies within something we briefly encountered in the previous chapter: dark matter. If the universe contained only the stars, planets, clouds of gas, and galaxies that our telescopes can observe, this immense structure simply could not remain stable. The gravitational pull produced by ordinary matter is not sufficient. For this reason, scientists believe that most of the cosmic web's hidden framework is composed of dark matter, an invisible form of matter that accounts for the majority of the universe's total mass. There is something quietly beautiful about this realization. The most important element is the one we cannot see. And perhaps that truth extends beyond the universe itself. Sometimes it is true of our own lives as well. The things that shape us most deeply are rarely the ones visible to others. Not fame, not success, not the achievements displayed before the world. Instead, it is our quiet values, our hidden memories, and the silent experiences that have patiently formed who we are throughout the years. Perhaps that is why every time we gaze into a sky filled with stars, we experience a peace that is difficult to describe. Deep within us, human beings are naturally drawn toward whatever is both vast and mysterious. The cosmic web, with its immense architecture and invisible framework, seems to remind us that behind every visible beauty lies a deeper reality. A place where unseen connections quietly support a world far greater than our imagination can fully comprehend. In the next chapter, we will journey deeper into that invisible framework itself, exploring how dark matter has woven the great highways of the universe, while also discovering why immense empty regions exist between the brilliant filament spaces that may appear almost completely vacant, yet play an essential role in the magnificent architecture of the cosmos. If galaxies are like luminous islands scattered across the ocean of space, then dark matter is like the unseen bedrock hidden beneath the water, silently supporting every one of those islands beyond the reach of human sight. At first, this may sound almost paradoxical. From childhood, we are taught to believe that whatever shines is what matters most. Yet the universe appears to operate according to an entirely different principle. Most of what determines its shape is almost completely invisible. Today, modern computer simulations consistently reveal the same remarkable picture. Remove dark matter from the equations, and the universe can no longer develop into the vast network we observe today. Galaxies become far more loosely distributed. Many galaxy clusters never form. The enormous filaments simply do not exist. For this reason, astronomers believe that the cosmic web was first built upon a framework of dark matter. Only afterward were hydrogen, helium, and all ordinary matter gradually drawn by gravity toward those invisible pathways, eventually gathering to form galaxies. If we could somehow see through every star, every nebula, and every galaxy, we might discover an immense skeleton embracing the entire universe. The galaxies themselves would appear as nothing more than tiny lanterns suspended upon that hidden framework. That is why astronomers often say that what we observe is merely the light of the network, not the network itself. There is a quiet reflection hidden within that image. In life, we naturally pay attention to whatever shines most brightly. We notice success. We celebrate achievements. We remember extraordinary moments. Yet we rarely notice the unseen foundations that support them all. A great tree cannot stand without roots buried deep beneath the earth. A symphony cannot exist without its moments of silence. Neither can a human life mature without the quiet experiences that no one else will ever witness. Carl Gustav Jung expressed a closely related idea when he wrote, "Until you make the unconscious conscious, it will direct your life and you will call it fate." Although this quotation is frequently cited in discussions of Jung, what matters most is not the wording itself, but the spirit behind it. There are forces that shape our lives long before we become aware of them. They quietly influence our thoughts, our emotions, and the choices we make. The cosmic web invites us to sense something very similar: invisible gravity, invisible dark matter, unseen forces that nevertheless shape the largest structure in the entire universe. Yet the cosmic web cannot truly be understood if we focus only on its luminous filaments. Part of its extraordinary beauty also lies within the immense empty regions stretching between them. Astronomers call these regions cosmic voids. At first glance, many people imagine a void to be a place of absolute emptiness. In reality, that is not the case. Cosmic voids still contain tiny amounts of gas, dark matter, and occasionally even a few solitary galaxies. Yet compared with the filaments, the density of matter is so extraordinarily low that these regions become the most sparsely populated places in the entire universe. The immense architecture of the universe continued. Some cosmic voids stretch for more than 300 million light-years. To appreciate the scale of such a distance, imagine a beam of light beginning its journey from one edge of one of these immense empty regions today. It would continue traveling for another 300 million years before finally reaching the opposite side. That span of time is far greater than the age of the earliest dinosaurs that first walked upon Earth. Why, then, do such enormous empty regions exist? The answer once again leads us back to gravity. During the earliest epochs of the universe, regions that contained slightly more matter gradually attracted even more. Meanwhile, the areas that were already less dense continued to lose matter to their surrounding neighbors. This quiet process unfolded over billions of years. The filaments grew denser and stronger, while the voids became larger and more expansive. Just as rainwater naturally flows down a mountainside into the valleys below, matter throughout the universe continuously drifts toward the places where gravity is strongest. This gives the cosmic web a very special kind of beauty. It was not built in a single day. It is more like an ancient forest that has grown patiently over billions of years, where every branch, every leaf, and every opening in the canopy has been shaped by time itself. Perhaps, when many people first look at those immense empty regions, they imagine them to be meaningless. Yet nature rarely creates anything that truly has no purpose. Without those vast empty spaces, the filaments would never stand out so clearly. If matter were distributed equally everywhere, the cosmic web simply would not exist. It is precisely the contrast between crowded regions and sparse ones that gives the universe its magnificent form. There is something deeply reflective about that image. In our own lives, we often fear emptiness. We try to fill every schedule, every quiet moment, every corner of the mind with endless sounds and endless information. Yet the universe seems to teach a very different lesson. Empty space is not something to be erased. It is an essential part of the structure itself. A piece of music becomes more beautiful because of its pauses. A painting gains depth through its open spaces. A forest feels more peaceful because not every patch of ground is covered with trees. And perhaps the human mind also needs moments of quiet like these. Carl Gustav Jung devoted much of his life to encouraging people to face their own inner worlds. Although he never spoke of cosmic voids, his philosophy consistently emphasized the value of stillness. It is within moments of silence that we are finally able to hear the quiet truths that the noise of everyday life so often conceals. Perhaps this is also why gazing into the night sky brings such an unmistakable sense of peace. Not simply because we see the stars, but because beyond those stars lie immeasurable expanses of darkness, where silence itself seems to stretch without end. It is the darkness that gives meaning to the light. It is the empty spaces that allow the universe's great network to reveal its shape. By now, we begin to realize that the cosmic web is more than a physical structure. It is also a story of connection. No galaxy truly exists alone. Each one is linked to others through immense filaments. Those filaments themselves are defined by the vast voids surrounding them, and all of them rest upon the invisible framework of dark matter. It is an architecture that is at once simple and magnificent. It was not built from stone, or steel, or concrete. It was built by gravity, woven by time, supported by realities invisible to the human eye, illuminated by hundreds of billions of galaxies, each quietly telling the story of nearly 14 billion years of cosmic evolution. In the next chapter, we will bring our attention closer to our own celestial home, within this immense network that seems to stretch forever. Where exactly is the Milky Way? What place does our solar system occupy within the vast architecture of the cosmic web? And is our tiny Earth truly alone within the universe? Or is it quietly journeying alongside an unimaginably greater cosmic network? Together, we will continue that journey, the Milky Way within the cosmic web. As we closed the previous chapter, we stood before the magnificent panorama of the cosmic web, where colossal filaments connect clusters of galaxies like luminous rivers flowing across endless darkness. From distances measured in billions of light years, every galaxy becomes nothing more than a tiny point of light within a structure so vast that it stretches beyond imagination. And perhaps it is precisely here that another very natural question begins to arise. If the entire universe is woven together by the cosmic web, where does our own Milky Way fit within that grand design? Is our solar system drifting alone through an infinite emptiness? Or are we too part of the magnificent network the universe has been patiently weaving since the dawn of time? To discover the answer, let us once again imagine that we are gently drawing closer. Instead of standing at the edge of the observable universe, we slowly approach a familiar spiral galaxy. Its graceful spiral arms emerge like ribbons of silver curving through the darkness. Hundreds of billions of shimmering stars form a vast whirlpool slowly turning through space. This is the Milky Way, our galactic home. For most of human history, the Milky Way was believed to be the entire universe. Our ancestors looked upon the pale ribbon stretching across the night sky and imagined that it marked the ultimate boundary of everything that existed. Only during the 20th century, when telescopes became powerful enough to reveal distant galaxies, did humanity discover a far more humbling truth. The Milky Way is not the center of the universe, nor is it the only galaxy. It is simply one among hundreds of billions of galaxies that inhabit the observable cosmos. At first, that realization may make us feel smaller. Yet, strangely enough, the more we understand our place within the universe, the more many people discover a quiet sense of peace. For we are no longer an isolated island floating through endless space. We belong to something far greater. The Milky Way is not alone. It belongs to a small community of more than 50 galaxies that astronomers call the local group. If the Milky Way were a city, then the local group might be imagined as a broad metropolitan region where many cities coexist and interact with one another. Its two largest members are the Milky Way and the Andromeda Galaxy. Alongside them are the Triangulum Galaxy and dozens of smaller dwarf galaxies, all quietly moving under the shared influence of gravity. What is especially fascinating is that the galaxies within the local group are not standing still. They are constantly in motion. The Andromeda Galaxy is gradually approaching the Milky Way at a speed of more than 100 kilometers per second. In roughly 4 to 5 billion years, the two galaxies are expected to collide and merge into a single, much larger galaxy. That may sound like a dramatic event, yet on the scale of the universe, it is simply another ordinary chapter in the life cycle of galaxies. Perhaps, when we contemplate spans of time such as these, the small worries of everyday life become just a little lighter. A single day, a single year, even an entire human lifetime. These are only fleeting moments upon the immense clock of the universe. That realization does not make life meaningless. Quite the opposite. It makes each present moment infinitely more precious. From the perspective of Carl Gustav Jung, human beings feel most complete when they recognize that they belong to something greater than themselves. Jung spent many years studying the shared symbols that appear throughout mythology, religion, and dreams across many different cultures. This led him to believe that beneath every individual lies a deeper layer of connection. If we see the cosmic web as a symbol, we encounter a remarkably similar idea. No galaxy exists entirely by itself. Every galaxy belongs to a group. Every group belongs to an even greater structure. Beyond the local group, another level of connection begins to appear. The local group itself is only a tiny part of a much larger structure known as a supercluster. For many years, astronomers referred to the supercluster containing the Milky Way as the Virgo supercluster. But more detailed maps eventually revealed that this structure is far larger than previously imagined. Today it is commonly known as Laniakea, a Hawaiian word meaning immense heaven, or immeasurable paradise. The name seems wonderfully appropriate. Laniakea stretches across more than 500 million light-years and contains approximately 100,000 galaxies. If the local group is a small neighborhood, then Laniakea is an entire continent. And the wonder does not end there. Even Laniakea is not the final destination. It is itself only one thread within the cosmic web. The farther we expand our perspective, the more the universe resembles a series of nested boxes. The solar system lies within the Milky Way. The Milky Way lies within the local group. The local group belongs to Laniakea. Laniakea rests upon one of the immense filaments of the cosmic web. Each level is vastly larger than the one before it. Yet every level remains intimately connected through gravity and time. The image brings to mind the famous Russian Matryoshka dolls, each one containing another within. Only here, perhaps this is one of the most beautiful gifts that modern astronomy offers us. It teaches us that the question, "Where are we?" is never as simple as it first appears. When we say, "We are on Earth," that is true. When we say, "We are in the solar system," that is equally true. When we say, "We are in the Milky Way," that too is true. And when we say, "We exist within the cosmic web," that statement is no less true. We simultaneously belong to many different layers of the universe, just as every person simultaneously belongs to a family, a community, a nation, and to humanity itself. These larger connections do not diminish our individual identity. Instead, they remind us that existence itself is always part of something greater. And once we begin to recognize those connections, we find ourselves looking at the night sky differently, no longer as countless unfamiliar points of light, but as unimaginably distant neighbors, traveling alongside us through a journey that has continued for nearly 14 billion years. In the next chapter, we will continue that journey to discover an even more astonishing truth. Not only the Milky Way, but Earth itself, our solar system, and every one of us is moving together with the immense network of the universe, even though, in our everyday lives, we almost never notice it. If you were to gently lift your eyes toward the night sky right now, everything might seem perfectly still. The stars appear fixed in their places, The moon drifts slowly across the heavens. The earth beneath our feet feels completely motionless. That impression is so natural that, for much of human history, people believed they stood at the center of a quiet and unmoving universe. Modern science tells us a different story, a story that is both magnificent and humbling. In truth, nothing around us is truly standing still. Even as you sit comfortably listening to these words, the Earth continues rotating upon its axis at thousands of kilometers per hour. At the same time, the Earth and the entire solar system orbit the center of the Milky Way at approximately 220 kilometers per second. And while all of that is happening, the Milky Way itself is moving together with the local group, the Laniakea supercluster, and the immense filament to which it belongs. In other words, we do not simply live on a moving planet. We are moving together with multiple layers of the universe at the very same time. It is an extraordinary thought. We feel as though we are sitting quietly in a familiar room, yet in reality, we are traveling through space at speeds far beyond anything humanity has ever built. Even more remarkable, we never feel it. There is no rushing wind, no trembling, no sound. We simply drift gently together with the universe. Perhaps this is one of astronomy's most beautiful lessons. Not every movement must be experienced through our senses. Some motions are so vast that they become the very foundation of what we perceive as stillness. It is much like sitting aboard a ship gliding smoothly across calm water. Unless you look out the window, you may believe you are perfectly motionless. The universe is much the same. All of us are passengers on a journey that began nearly 14 billion years ago. That realization makes the image of the cosmic web feel wonderfully alive. It is not a static picture hanging in some cosmic museum. It is a living structure, growing, changing, forever in motion. The filaments continue guiding matter toward galaxy clusters. The clusters continue becoming larger. The cosmic voids continue expanding. And within that immense current, our own Milky Way quietly continues its journey. If we look back across Earth's history, another remarkable realization appears. When the first dinosaurs walked upon our planet, the solar system occupied a different location within the Milky Way. When the earliest mammals began to evolve, we were somewhere else entirely. When human beings first learned to make fire, built their earliest civilizations, and looked toward the heavens with wonder, the Milky Way never ceased carrying us onward along its orbit. Every moment in human history has unfolded while our planet has been silently traveling through the cosmic web. There is something deeply moving about that thought. It reminds us that no moment of our lives has ever existed apart from the universe. Every laugh, every tear, every civilization, every book, every piece of music, all have come into being upon a planet journeying together with the cosmos. In the spirit of Carl Gustav Jung, human beings naturally tend to place themselves at the center of their own stories. That is perfectly understandable, because we experience the world through ourselves. Yet, as we mature, we gradually recognize that every life is woven into larger relationships, family, community, history, and nature. Astronomy expands that perspective once more. It shows us that even our planet does not exist in isolation. Earth belongs to the solar system. The solar system belongs to the Milky Way. The Milky Way belongs to the local group. The local group belongs to Laniakea, and all of them belong to the cosmic web. This interconnectedness does not make humanity feel insignificant in a negative sense. Instead, it reminds us that we have always belonged to something immeasurably greater. Perhaps that is why so many astronauts, after seeing Earth from space, describe an extraordinary feeling. From that distance, they no longer see national borders. They no longer see the divisions created by human beings. They see only a small blue world quietly drifting through an infinite darkness. When our perspective changes, the meaning of many things changes as well. Conflicts that once seemed enormous become surprisingly small. differences that once felt overwhelming become easier to carry. Perhaps the cosmic web quietly invites us to view life from that same broader perspective, not to deny human emotions, but to place them within a larger context where all life shares the same universe. There is one final truth that science rarely expresses in the language of poetry, yet somehow allows us to feel naturally. Every atom within our bodies was once forged in the hearts of ancient stars. The carbon atoms within your hands, the oxygen atoms carried in every breath you take, the iron atoms transporting oxygen through your bloodstream. Every one of them was forged inside generations of stars that lived and died long before our solar system was ever born. Which means that there has never truly been an absolute boundary between ourselves and the universe. We do not simply live within the universe. We are made from the very substance of the universe. And as that thought gently settles into the mind, the cosmic web begins to feel like more than a concept in astrophysics. It becomes a quiet symbol of connection. Invisible strands of matter linking galaxies together. Gravity binding clusters of galaxies into a vast network. Time connecting the past to the present. Light joining distant stars with the eyes that silently gaze upward into the night. Perhaps, in a deeply meaningful way, human beings have always searched for those same invisible threads within their own lives. A connection to memory, a connection to those we love, a connection to nature, and, ultimately, a connection to the quiet feeling that we belong to something greater than ourselves. As we come to understand the Milky Way's place within the cosmic web, we also begin to understand our own. We are neither the center of the universe, nor lonely creatures adrift through an endless void. We are a very small, yet genuine, part of a story that has been unfolding for nearly 14 billion years. In the next chapter, we will journey even farther back through time to explore one of the most fundamental questions in modern cosmology. How did the cosmic web first come into existence? How did tiny fluctuations in the moments following the Big Bang eventually grow into the largest structure humanity has ever discovered? It is a story that begins in the very first moments of time itself, where seeds smaller than atoms quietly gave rise to the entire cosmic tapestry that we continue to admire today. How the cosmic web was formed. As we closed the previous chapter, we discovered that the Milky Way is not alone. Our solar system, our Earth, and every one of us are traveling together within an immense network, stretching across the universe. Yet the more we admire the beauty of the cosmic web, the more another question gently arises. If this network is the largest structure humanity has ever discovered, then how did it come to be? How could an early universe that was almost perfectly uniform eventually give rise to filaments, stretching across hundreds of millions of light years? Enormous galaxy clusters, and vast empty regions so immense that light itself requires hundreds of millions of years to cross them? To discover the answer, tonight, we will journey backward through time, not thousands of years, not millions, but nearly 14 billion years, returning to the first moments after the event scientists call the Big Bang. The name itself sometimes leads us to imagine an enormous explosion occurring somewhere in empty space. But that is not quite what happened. The Big Bang was not a bomb exploding inside space. Space itself and time itself began expanding from that event. It was the moment when everything contained within today's observable universe existed in an incredibly hot, incredibly dense, and unimaginably tiny state. If we could somehow stand within those first moments, we would see no stars, no galaxies, no planets, not even fully formed atoms. The entire universe would resemble a radiant ocean of energy, where matter and radiation were blended together under temperatures so extreme that none of the familiar structures we know today could yet exist. At first glance, this newborn universe appears almost perfectly uniform. Like the surface of a perfectly calm lake on a windless morning, everything seems identical in every direction. Yet modern observations reveal something even more remarkable. That uniformity was never absolute. From the very beginning, tiny fluctuations already existed within that blazing ocean of energy. Some regions contained ever so slightly more matter. Others contained ever so slightly less. The differences were almost unimaginably small. If the entire early universe were compressed to the size of Earth itself, those variations would be far smaller than the tiny roughness of a single grain of dust resting upon the ground. It is astonishing to realize that from those fragile fluctuations, the entire grand architecture of the universe would eventually emerge. Many people find themselves reminded of the way an ancient forest begins from a single tiny seed. Standing before a tree that has lived for hundreds of years, it is easy to forget that it once existed only as a small sprout hidden quietly beneath the soil. The cosmic web is much the same. Before it became an immense network stretching across billions of light years, it existed only as extraordinarily subtle differences in the density of the newborn universe. From the perspective of Carl Gustav Jung, profound transformations within the human psyche rarely begin with dramatic events. Many of our deepest changes begin instead with a single image, a dream, or a quiet thought so small that we scarcely notice it at first. Although this is a symbolic reflection rather than a scientific comparison, it evokes a beautiful feeling. Nature, too, seems to possess its own gentle way of growing. The greatest things often begin with the smallest beginnings. Yet tiny fluctuations alone were not enough. Without a force capable of amplifying them, those differences would quickly have been smoothed away, leaving the universe forever as a perfectly uniform sea of matter. That force is gravity. In everyday life, we usually think of gravity as the reason an apple falls to the ground, or why we remain firmly upon Earth's surface. But on the scale of the cosmos, gravity plays an infinitely greater role. It is like a patient artist, spending billions of years shaping the very architecture of space itself. Where matter was only slightly denser, gravity became only slightly stronger. That tiny difference drew even more matter toward those regions. As more matter gathered, gravity grew stronger still, attracting even more. It became a self-reinforcing process, like a snowball rolling down a mountainside. At first, it is no larger than your hand. With every turn, another layer of snow clings to its surface. By the time it reaches the valley below, it may have grown thousands of times larger than when it began. Gravity works in much the same way. It never acts suddenly. It never transforms the universe overnight. It simply remains patient. And it is that patience which has shaped everything we see today. There is something profoundly beautiful about the way nature uses time. Human beings live by days, months, and years. We naturally hope to see results immediately, but the universe unfolds across spans of time so vast that the human mind struggles to comprehend them. For the cosmic web, hundreds of millions of years may be little more than a few quiet moments. That makes every filament, every galaxy cluster, and every cosmic void feel like a work of art created not within an instant, but through nearly 14 billion years of patient creation. Even so, ordinary matter alone still cannot fully explain what astronomers observe today. Once again, the familiar mysterious character quietly returns. Dark matter. Modern cosmological models indicate that dark matter interacts very little with light, yet it responds fully to gravity. This allowed it to gather into massive structures long before ordinary matter was able to do the same. One way to imagine it is as a network of invisible rivers that formed first. Only afterward did hydrogen and helium, the simple elements that would eventually give birth to stars, begin slowly flowing along those hidden channels. In other words, dark matter became the first framework of the cosmic web. It created immense gravitational valleys. Ordinary matter simply flowed into them. Without dark matter, stars would struggle to gather into galaxies. Galaxies would struggle to assemble into clusters. And the cosmic web, as we know it today, might never have existed at all. There is something wonderfully mysterious in realizing that the first structure ever built within the greatest architecture of the universe is one that we still cannot observe directly. Perhaps that also reminds us of a gentle truth. In both nature and in life, the strongest foundations are rarely the most visible. A house stands because of the foundation hidden beneath the ground. A forest survives because of roots buried deep beneath the soil. And the cosmic web is supported by an invisible framework that only gravity can reveal. As the hidden framework of dark matter gradually took shape, the universe still looked nothing like the one we know today. There were no graceful spiral arms of galaxies, no enormous galaxy clusters, no immense void stretching across hundreds of millions of light years. Everything resembled only the first sketch of a masterpiece. The basic outlines had appeared. The painting itself was still waiting for time to complete it. Then, little by little, ordinary matter entered the story. Hydrogen and helium, the two simplest elements born in the early universe, were no longer spread evenly throughout space. Slowly they drifted toward the gravitational valleys that dark matter had already prepared. At first, the movement was almost impossible to notice, but time was one thing the universe possessed in endless abundance. Tens of millions of years passed, then hundreds of millions, eventually billions. The clouds of gas became increasingly dense. Under their own gravity they grew hotter, they collapsed inward, and finally, the first stars ignited within the primordial darkness. It was the moment when light began illuminating the invisible framework that had patiently been prepared long before. The entire process may be imagined as a winter sunrise. Before the sun rises, mountains, rivers, and fields already exist, yet they remain hidden beneath soft grey mist. Only when the light arrives do their shapes gradually become visible. Galaxies are much the same. They did not create the cosmic web. They merely revealed the network that dark matter had shaped long before they themselves were born. That is why astronomers often compare galaxies to lamps illuminating an immense system of highways. When night falls upon a city, we notice the lights first. Yet what truly connects them are the roads stretching silently between them. The cosmic web possesses that same quiet beauty. Galaxies are simply luminous markers, indicating where matter has gathered densely enough for stars to form. Behind those lights lies a network far greater still. As time continued, galaxies did not remain isolated. They gathered into even larger structures. Along the rivers of matter flowing through the cosmic web, hundreds, then thousands, of galaxies became bound together by gravity, forming clusters. These are the great cities of the universe, where galaxies remain separated by enormous distances according to human standards, yet close enough to interact, collide, and evolve together across billions of years. On even greater scales, many filaments run alongside one another or intersect, forming immense walls, vast sheets of galaxies stretching across hundreds of millions of light years. When scientists first produced three-dimensional maps containing millions of galaxies, they were astonished. The universe was nothing like a beach where grains of sand lie scattered randomly. Instead, it resembled a magnificent city, connected by countless avenues and great plazas, except that every avenue was measured not in kilometers, but in millions of light years. Yet even with filaments, walls, and clusters, the cosmic web would still be incomplete. Part of its beauty lies within the immense empty spaces between them. These are the cosmic voids. At first glance, many imagine voids to be places where absolutely nothing exists. The truth is far more subtle. They still contain small amounts of gas, a little dark matter, occasionally even a few solitary galaxies. Yet compared with the filaments, their density is so extraordinarily low that they become the universe's great regions of silence. It is fascinating to realize that the more matter flows into the filaments, the larger the voids become. These two processes unfold together, like opposite sides of the same coin. Where one region grows denser, another grows emptier. It is precisely that contrast which allows the entire cosmic web to reveal its magnificent form. This reminds us of a familiar principle in art. A painting is created not only by the brushstrokes, but also by the untouched white spaces between them. A melody is shaped not only by its notes, but by the silence separating each phrase. If every note were played at once, there would be no music. If every empty space were painted over, the eye would have nowhere to rest. The universe appears to create according to the very same principle. The filaments are the brushstrokes. The clusters are the focal points. The voids are the essential spaces that allow the entire masterpiece to exist in harmony. Perhaps this is one of the gentlest lessons offered by the cosmic web. In life, we often fear emptiness. We try to fill every moment with work, every silence with sound, every thought with endless information. Yet nature quietly shows us something different. Emptiness is not always a sign of absence. Sometimes it is precisely what allows everything else to have meaning. Carl Gustav Jung devoted much of his life to encouraging people to encounter their own inner worlds. In the spirit of his work, only when we are willing to enter the unexplored regions within ourselves do we truly begin to understand who we are. The cosmic voids, in a symbolic sense, invite a similar reflection. They are not places where nothing exists. They are places of quiet, where presence is experienced in a different way. When we view the entire formation of the cosmic web through the lens of time, another remarkable truth appears. There was never a single moment when the network suddenly came into existence fully formed. It grew gradually, like a forest. First came a few tiny seedlings, then the first young trees, then branches intertwined. Eventually, an entire ecosystem emerged, every part connected to every other. The cosmic web matured in exactly that way, from fluctuations smaller than atoms, to the first concentrations of dark matter, to clouds of gas, to stars, to galaxies, to galaxy clusters, to filaments, to enormous walls, and finally, to the immense cosmic network that we continue to explore today. What makes this story so extraordinary is not only its scale, but the universe's almost limitless patience. Human beings measure life in decades. Civilizations are measured in thousands of years. The cosmic web has been under construction for nearly 14 billion years. Every galaxy is the result of countless processes unfolding so slowly that no civilization could ever witness them from beginning to end. Perhaps that is why learning about the universe brings such a profound sense of peace. It reminds us that nature is never in a hurry. The greatest creations always require time to grow. And perhaps we, too, do not need to hurry so much. An idea planted today may become understanding many years from now. A tiny seed may become a forest. A single act of kindness may quietly transform an entire life. Just as the smallest fluctuations after the Big Bang eventually became the greatest structure we have ever known. When you look up at the night sky after everything we have explored together, perhaps you will no longer see only the stars. Instead, you may begin to imagine the immense rivers of matter that lie beyond them, the great filaments quietly linking hundreds of billions of galaxies, the vast cosmic voids shaping the beauty of the entire universe. And a story that has unfolded for nearly 14 billion years, a story that is still far from finished. For the cosmic web has never been a completed structure. It continues to grow. It continues to evolve. And in the next chapter, we will explore another of its remarkable mysteries, where much of the universe's ordinary matter seemed to disappear, why astronomers spent decades searching for it, and how the cosmic web ultimately became the place where one of modern cosmology's greatest puzzles found its answer. The missing matter of the universe. As we concluded the previous chapter, we witnessed how the tiny fluctuations born after the Big Bang, guided patiently by gravity and the invisible framework of dark matter, gradually wove together the cosmic web, the largest structure humanity has ever discovered. The filaments, the galaxy clusters, the immense cosmic voids, none of them appeared by chance. They are the result of nearly 14 billion years of continuous evolution. And yet, just as astronomers began to believe they were finally understanding this extraordinary picture, another mystery quietly emerged. A mystery both subtle and deeply challenging. It began with what seemed to be a very simple question. Where has the universe's ordinary matter gone? At first, the question sounds almost strange. After all, we can clearly see countless stars, galaxies, enormous clouds of gas, and planets. So how could matter simply go missing? To understand this mystery, we must first distinguish between two concepts that are often confused. Throughout the previous chapters, we have spoken many times about dark matter, the invisible substance that provides the structural framework of the cosmic web. But what we are about to discuss now is something entirely different. It is not dark matter. It is baryonic matter, ordinary matter, the familiar material from which everything in our everyday lives is made. Protons and neutrons, the fundamental particles known as baryons, form atoms. Atoms combine into molecules. Molecules become water, stone, forests, animals, human beings, planets, and stars. Simply put, everything we can see, touch, or experience with our senses is composed of baryonic matter. What makes the story so fascinating is that the Big Bang model, together with observations of the cosmic microwave background, allows scientists to calculate with remarkable precision how much baryonic matter should exist in today's universe. Yet when astronomers add together all the matter they can actually observe in stars, galaxies, nebulae, and clouds of gas, they consistently arrive at a surprisingly smaller number. A very large fraction appears to be missing. For decades, astronomers referred to this puzzle as the missing baryonic matter problem. At first glance, it sounds more like a detective story than a scientific question. No one doubted that this matter had once existed. The equations predicted it. Observations of the early universe confirmed it. And yet, when scientists looked into today's universe, nearly half of its ordinary matter seemed to be absent from all the places where it ought to have been. The mystery is rather like walking into an immense library. The catalogue insists there should be 10,000 books. Every shelf is carefully numbered. Yet when you begin counting, you find only about half that number. The missing books have not been erased from the records. They have not vanished from history. They simply appear to be somewhere no one has yet discovered. And so, astronomers began a search that would last for decades. They pointed telescopes toward every corner of the sky. They studied galaxies, galaxy clusters, nebulae, even regions of space that appeared completely empty. Yet the answer refused to change. The amount of observable matter remained far too small. Perhaps this is one of the reasons science is so captivating. Just when humanity believes the puzzle is nearly complete, another missing piece quietly reveals itself. And that very absence becomes the beginning of an entirely new journey of discovery. In a beautiful symbolic sense, this mystery also recalls the way Carl Gustav Jung viewed the human mind. Jung believed that what we consciously experience represents only a small portion of the psyche. Beneath the surface lie deeper layers filled with memories, emotions, and symbols that continue to exist even though we rarely perceive them directly. Of course, this is merely a symbolic parallel. Astronomy and psychology speak about entirely different realities, yet both gently remind us of the same truth. What cannot yet be seen is not necessarily absent. Eventually, this long search led astronomers toward a bold new idea. Perhaps the missing baryonic matter had never disappeared at all. Perhaps it had simply been spread throughout regions that our instruments had not yet been capable of observing. Those regions lie between the galaxies themselves. Many people imagine the space between galaxies as a perfect vacuum. The reality is far more subtle. The space surrounding the filaments of the cosmic web is not completely empty. Instead, it contains extraordinarily diffuse clouds of gas, composed primarily of hydrogen and helium, stretching across millions of light years. Their density is so incredibly low that within a volume of space as large as an ordinary room, there may exist only a handful of atoms. At first, a few atoms hardly seem worth mentioning. But remember the unimaginable scale of the cosmic web. When all of those faint clouds are added together across the entire universe, their combined mass becomes enormous. It is like countless tiny drops of dew covering an immense forest. Viewed individually, each droplet is almost invisible. Yet when morning arrives, the entire forest sparkles because of them. Scientists call this elusive component the warm-hot intergalactic medium, usually abbreviated as WIM. It consists of gas between galaxies with temperatures ranging from hundreds of thousands to tens of millions of Kelvin. Hearing those temperatures, many people naturally imagine brilliant glowing clouds. But because the gas is so extraordinarily diffuse, the light it emits is astonishingly faint, almost completely overwhelmed by the darkness of space. That is why, for decades, it remained virtually invisible to our telescopes. There is something wonderfully ironic about this realization. The missing matter was not hidden because it was too small. It was hidden because it was too thinly spread. Imagine a delicate mist covering an entire valley. Standing within it, you might barely notice its presence. Yet when the first rays of sunlight shine through, the whole landscape suddenly reveals a beauty your eyes had overlooked before. The cosmic web is much the same. Its filaments are not merely the highways connecting galaxies. They are also immense rivers carrying vast streams of hot, diffuse gas throughout the universe. In other words, most of the universe's missing ordinary matter never disappeared at all. It has simply been quietly drifting between galaxies, spread throughout the filaments of the cosmic web like invisible morning mist that humanity has only recently begun to recognize. And naturally, if this gas is almost invisible, if it emits so little light, if it is dispersed across such extraordinary distances, how could astronomers ever prove that it truly exists? How can humanity observe something that is almost impossible to see? If those immense clouds of hot, diffuse gas between galaxies do not shine brightly enough for ordinary telescopes to detect, how can we be certain they are really there? This is precisely what made the missing baryonic matter problem one of the most patient and elegant investigations in modern astronomy. It was not like discovering a new planet, nor was it like photographing a distant galaxy. Instead, it resembled the work of an archaeologist following barely visible footprints across ancient sand, or a detective reconstructing an entire story from only a handful of seemingly unrelated clues. Rather than searching directly for the gas itself, scientists chose to study what happens when light passes through it. The idea sounds remarkably simple, yet it is profoundly insightful. You cannot see the wind, yet you know it exists when leaves begin to sway. You cannot see the air itself, yet you recognize its presence when the first rays of morning sunlight pass through a thin veil of mist. Sometimes, the best way to discover something invisible is not to observe it directly, but to examine the traces it leaves upon something else. The universe tells its story in much the same way. One of the most useful natural beacons in the cosmos is the quasar. A quasar is an extraordinarily luminous region surrounding a supermassive black hole at the center of a very distant galaxy. As matter falls toward the black hole, it becomes so intensely heated that it emits more light than hundreds of billions of stars combined. Because of this incredible brilliance, quasars can be observed across billions of light years. Imagine standing upon a hillside on a dark night. Far away, a lighthouse sweeps its beam across a mist-covered coastline. You cannot see each droplet of mist individually. Yet when the beam passes through it, you immediately know something is present within the air. The light from a quasar serves much the same purpose. During its journey of billions of years toward Earth, that light passes through countless filaments of the cosmic web. Each time, it encounters a cloud of hot, diffuse gas. A tiny fraction of the light is absorbed by atoms within the cloud at very specific wavelengths. When astronomers analyze the quasar's spectrum, they discover extraordinarily subtle absorption lines. These tiny fingerprints reveal that previously unseen clouds of gas truly exist between the galaxies. It is a wonderfully beautiful discovery. Not because it is dramatic, but because it reminds us that even light itself can become the storyteller of the universe. Quasars, however, are not the only tools available. Scientists also use X-rays to search for gas heated to millions of degrees. At such extreme temperatures, elements such as oxygen and neon emit or absorb X-rays in distinctive ways. Although these signals are extraordinarily faint, space-based X-ray telescopes can detect them after extremely long observations. Such work demands astonishing patience. Some datasets are collected over many months. Others require years, all to confirm a signal so faint that it can easily disappear within the background noise. Perhaps science resembles tending a garden. Not every seed sprouts the next morning. Not every answer arrives after a single experiment. Some discoveries emerge only after years of quiet observation. In that sense, science follows the same rhythm as nature itself. Never hurried, never loud, yet endlessly persistent. And in recent years, another remarkable messenger has joined this cosmic investigation, carrying precious new clues about the cosmic web. These are known as fast radio bursts, or FRBs. These signals last for only a few thousandths of a second, yet they carry an extraordinary amount of energy. They originate in galaxies unimaginably far away, then travel across billions of light years, before finally reaching radio telescopes here on Earth. Along their journey, those radio waves must pass through the diffuse matter that fills the space between galaxies. Each free electron within the hot intergalactic gas slows the signal ever so slightly. By measuring the tiny delay between different radio frequencies with remarkable precision, scientists can estimate the total amount of matter the signal has encountered along its path. There is something truly wonderful about realizing that a signal existing for only a fleeting instant can tell a story spanning billions of light years. It is like a single raindrop revealing the direction of the wind across an entire sky, or a falling leaf quietly announcing that autumn has arrived. In astronomy, the smallest clues often reveal the greatest truths. No single observational technique, by itself, was enough to solve the mystery of the missing baryonic matter. But when astronomers combined observations from quasars, X-ray telescopes, fast radio bursts, and many other spectroscopic methods, the picture gradually became clearer. Most of the missing baryonic matter had never disappeared. It had been there all along, quietly dispersed throughout the filaments of the cosmic web, between galaxies, between galaxy clusters, across the immense regions that humanity had once imagined were nothing more than empty space. This is one of the most beautiful moments in science, not because humanity has somehow conquered the universe, but because we have learned how to listen to the faint whispers the universe has been sending us for billions of years. In a symbolic sense, this also echoes a reflection very much in the spirit of Carl Gustav Jung. Within our own lives, the things that matter most are not always those that stand plainly before our eyes. There are emotions buried deep within us, ancient memories, quiet beliefs. All of them continue shaping the way we live, often long before we become consciously aware of them. They have not disappeared. They simply await a more attentive way of seeing. Perhaps this is another lesson the cosmic web quietly offers us. To see is not always to observe with our eyes. To understand does not always begin with what is obvious. Sometimes, discovering a great mystery requires the patience to listen to the smallest signs. After decades of searching, the mystery of the missing baryonic matter has gradually approached its solution. Not every detail has yet been fully resolved, but the larger picture has become remarkably clear. The cosmic web is not merely the framework connecting galaxies. It is also the vast reservoir that contains most of the universe's ordinary matter in the form of long streams of hot, diffuse gas stretching throughout intergalactic space. That realization changes the way we see the cosmic network. Its filaments are no longer simply highways linking galaxies. They resemble the immense circulatory system of the universe, quietly transporting gas, quietly nourishing the birth of new galaxies, quietly preserving the missing pieces of the cosmic puzzle. Much like the bloodstream within the human body, its most essential work is carried out silently. Perhaps that is one of nature's greatest beauties. The things that endure the longest rarely seek attention. The things that matter most often work in silence. Now, as the night grows deeper and our journey carries us farther into the heart of the cosmos, perhaps you will begin to sense that the vast spaces between galaxies are no longer empty voids. They are places quietly preserving matter, energy, and the memory of nearly 14 billion years of cosmic evolution. In the next chapter, we will continue following these traces as we explore the remarkable observations that have allowed humanity to see the cosmic web more clearly than ever before. From the cosmic microwave background, to ancient starlight, to the phenomenon of gravitational lensing, each observation becomes another piece of the puzzle, gradually completing the grandest picture humanity has ever assembled of the universe through which we are all quietly traveling. Observational evidence for the cosmic web. As we concluded the previous chapter, we followed the trail of the ordinary matter that was once believed to be missing from the universe. The remarkable truth was that it had never truly disappeared. Instead, it quietly stretches between galaxies as vast streams of hot, diffuse gas, hidden along the filaments of the cosmic web. Yet another gentle question naturally arises. If the cosmic web is truly so immense, if much of its structure is supported by invisible dark matter, how do we know it actually exists? How have we managed to see it? Or perhaps a better question is this: how can we observe something that our eyes can never perceive directly? Perhaps this is one of the most beautiful stories in modern astronomy. For discovering the cosmic web required far more than building larger telescopes. Humanity also learned how to listen to the memories that light itself has quietly carried for nearly 14 billion years. If there is one witness that has remained present from almost the very dawn of the universe until today, it is light itself. Light possesses a remarkable gift. It not only allows us to see the present, it also allows us to look into the past. When we gaze at the moon, we see it as it appeared a little more than 1 second ago. When we observe the sun, we see it as it was roughly 8 minutes earlier. When we point our telescopes toward galaxies billions of light years away, we are quite literally observing the universe as it existed billions of years in the past. That means astronomy has never been only the science of space. It is also the science of time. Every beam of light is like a letter sent from the past. Every star tells a story that began long before humanity itself appeared. And among all the messages the universe has ever sent us, one is older than all the others. Scientists call it the cosmic microwave background, usually abbreviated as the CMB. At first, the name sounds rather technical. Yet once we understand what it truly represents, we discover that it may be one of humanity's most extraordinary scientific discoveries. Imagine standing beside a quiet lake on a winter morning. Its surface is perfectly still. You gently drop a small pebble into the water. Circular ripples spread outward, growing wider and wider. Long after the pebble has disappeared beneath the surface, the ripples continue carrying the memory of that very first moment of contact. The cosmic microwave background is much like those ripples. It is the ancient light left behind when the universe was only about 380,000 years old. Compared with the universe's present age of nearly 14 billion years, that was almost its very first moment. Before then, the universe remained so incredibly hot that electrons and protons could not combine to form atoms. Light continually collided with electrically charged particles and was unable to travel freely. The entire cosmos resembled an immense, glowing fog through which no beam of light could pass. Then, little by little, the universe cooled. Electrons began combining with protons to create the first hydrogen atoms. Space became transparent, and for the very first time, light was finally free to begin its journey. Those ancient photons have continued traveling for nearly 14 billion years before eventually reaching our modern telescopes here on Earth. What moves so many people is not merely the age of the cosmic microwave background. It is the realization that we are truly observing light emitted while the universe itself was still in its infancy. Every time scientists study a map of the CMB, they are not simply measuring a faint microwave signal. They are gazing upon the newborn portrait of the universe itself. To the naked eye, a CMB map appears almost featureless. Its temperature is astonishingly uniform, approximately 2.7 Kelvin, colder than nearly any environment human beings have ever experienced. Yet, when satellites such as COBE, WMAP, and Planck measured it with extraordinary precision, they discovered tiny temperature differences. Some regions were warmer by only a few millionths of a degree. Others were cooler by similarly minute amounts. At first glance, such tiny variations seem almost insignificant, yet they changed the entire history of the universe. They are the surviving fingerprints of the density fluctuations we discussed in the previous chapter. From those regions that were only slightly denser than their surroundings, gravity slowly gathered matter together, eventually giving birth to galaxies, galaxy clusters, and finally the cosmic web itself. In many ways, the CMB resembles the very first photograph of a newborn child. Within that photograph, you cannot yet see the face the child will have as an adult. Yet every essential feature is already present. The cosmic web is much the same. The filaments had not yet appeared. The galaxy clusters had not yet formed. Yet the seeds of everything were already hidden within the tiny fluctuations preserved across the surface of the cosmic microwave background. In a sense, the CMB map resembles the fingerprint of the universe's dawn. No two human beings possess exactly the same fingerprint. Likewise, no two universes would share precisely the same history. Every slightly warmer region, every slightly cooler one, each preserves a fragment of the story describing how matter first began gathering under the influence of gravity. That is why astronomers often describe the CMB as preserving the fingerprint of the cosmic web. Not because the network itself had already formed, but because every ingredient required to create it had already been written into that ancient light. There is a beautiful reflection hidden within this idea. In life, we often notice only the finished result: a towering tree, a winding river, a great city, a fully grown human being. But few of us ever pause to think about the tiny traces that quietly shaped everything from the very beginning. Carl Gustav Jung devoted his life to exploring the deepest layers of the human mind. In the spirit of his work, the earliest experiences of our lives, even those that seem long forgotten, can continue to leave patterns that influence how we feel and act many years later. This is not a scientific comparison with the cosmic microwave background, but rather a symbolic image. Just as the human psyche preserves the impressions of its earliest days, the universe, too, preserves the memory of its own dawn within its ancient light. Perhaps the most extraordinary thing is that this memory has never disappeared. It is still all around us. Every direction toward which a telescope is pointed contains photons that began their journey nearly 14 billion years ago. Those rays of light have traveled past countless galaxies. They have crossed immense filaments. They have drifted through vast cosmic voids, only to arrive here at last, quietly telling us the story of the earliest moments of existence itself. And then another gentle question begins to emerge. If light can preserve the memory of the infant universe, might it also carry other traces gathered during its journey through the cosmic web? Could the great cosmic network itself leave its imprint upon the light that passes through it? When the first photons of the cosmic microwave background began their journey, they carried with them more than the memory of the newborn universe. Throughout nearly 14 billion years of travel, they passed countless galaxies, galaxy clusters, the immense rivers of matter that form the cosmic web, and regions of dark matter that no human eye has ever directly observed. What is remarkable is that light cannot travel through all of those places without leaving behind subtle traces of the journey. In everyday life, we are already familiar with light being bent. A spoon placed in a glass of water appears broken at the surface. Sunlight, passing through a single drop of dew, can make an entire garden sparkle. That happens because light changes direction when it moves through different materials. But beyond the familiar phenomenon of refraction, the universe possesses another, even more astonishing way of bending light. Not through water, not through glass, but through gravity itself. According to Einstein's general theory of relativity, matter does not simply exist within space. Its mass bends space-time itself. When light passes near an object with tremendous mass, its path curves as it follows that distortion. This phenomenon is known as gravitational lensing. At first, the idea can feel rather abstract. Imagine a large sheet of fabric stretched tightly across a frame. Place a heavy ball in its center, and the fabric sags beneath the weight. Now roll a small marble across the surface. Instead of moving in a perfectly straight line, the marble curves as it passes near the depression. Space-time behaves in much the same way. Galaxy clusters and regions rich in dark matter create gentle depressions in the fabric of space itself. Light passing nearby is subtly deflected. Sometimes this bending produces distorted images, sometimes glowing arcs, sometimes multiple images of the very same galaxy. Yet what fascinates astronomers most is not simply the beauty of these phenomena, it is the information they reveal. If light bends more strongly than can be explained by the visible stars and gas alone, then additional invisible mass must also be present. Through gravitational lensing, scientists have gradually constructed maps showing the distribution of dark matter across enormous regions of the universe. The remarkable thing is that they have never seen dark matter directly. Instead, they have observed the way dark matter changes the journey of light. Once again, the universe tells its story through the smallest of clues. There is a gentle reflection hidden within that realization. Some things in life cannot be understood simply by looking directly at them. They reveal themselves through the influence they leave behind. A single kind word can change the course of someone's entire day. An old memory can quietly shape a decision made years later. A genuine love may be recognized not through words, but through the life it quietly transforms. Nature behaves in much the same way. Dark matter emits no light, yet it leaves its signature upon light. Gravity has no color, yet it leaves its signature upon the shapes of galaxies. The cosmic web is not plainly visible before our eyes, yet it leaves its signature upon every beam of light that travels through it. In the spirit of Carl Gustav Jung's work, we often perceive only the surface of psychological life, while its deeper layers reveal themselves through symbols, dreams, and patterns of behavior. Although this is a philosophical reflection rather than a scientific comparison, astronomy and psychology gently point toward the same lesson. Sometimes, if we wish to understand the true nature of something, we must first learn to read the traces it leaves behind. Beyond gravitational lensing, astronomers also use millions of distant galaxies as reference points scattered across the sky. When the light from all of those galaxies is distorted in the same subtle direction, the phenomenon is known as weak gravitational lensing. A single galaxy might appear distorted for many different reasons, but when millions of galaxies display the same delicate pattern, a much larger picture begins to emerge. It is like watching a single leaf. By itself, it tells us little about the wind, but when an entire forest sways together, the direction of the breeze becomes unmistakable. Using this method, astronomers have created increasingly detailed maps of the cosmic web. Regions rich in dark matter emerge like invisible rivers linking galaxy clusters together. Remarkably, these maps agree extraordinarily well with computer simulations built from the known laws of physics. It is one of science's most beautiful moments, when many independent paths all lead toward the same answer. The cosmic microwave background reveals the earliest seeds. Gravitational lensing reveals the invisible framework. The light of quasars uncovers the gas between galaxies. Galaxy surveys trace the immense filaments. Each piece, viewed alone, may seem incomplete, but together they form one coherent picture. Perhaps this is also how we come to understand ourselves. Rarely through a single memory, a single experience, or a single story. Instead, we gradually discover who we are by bringing together countless memories, emotions, and experiences. The universe is being understood in exactly the same way. No single observation can tell the entire story, yet every ray of light, every map, every radio signal adds another brushstroke to the greatest portrait humanity has ever painted. By now, perhaps we understand why astronomers often say that the cosmic microwave background preserves the fingerprint of the cosmic web, not because the filaments themselves are already visible within the CMB, but because those tiny fluctuations embedded within that ancient light contain the very first blueprint from which the entire network would later emerge. Like a seed already containing the form of an ancient tree, like a tiny spring already carrying within it the future shape of a mighty river, that ancient light preserved the memory of everything yet to come. There is something profoundly peaceful about that thought. Each night, as we lift our eyes toward the heavens, the photons reaching them have traveled for longer than the entire history of Earth itself. They have crossed galaxy clusters, traversed immense cosmic voids, followed the great filaments of the cosmic web, and all the while, they have quietly carried the story of the universe's formation. Perhaps the greatest wonder is not that humanity has finally seen the cosmic web. It is that the universe has never stopped telling us about itself. It speaks through light, through gravity, through the tiny fluctuations left behind from the dawn of time. And only when we learn to listen patiently do we begin to realize that the space surrounding us has never been silent. It has always been filled with memories waiting to be understood. In the next chapter, our journey leads us toward what appears to be the opposite of the dense regions of the cosmic web. Together we will enter the cosmic voids, the immense empty spaces lying between the filaments. They may seem almost completely empty, yet they play an essential role in shaping the architecture of the entire universe. And perhaps those vast regions of stillness will also help us understand why, in both the cosmos and the human soul, emptiness can sometimes hold a quiet and beautiful meaning. Cosmic voids, the immense spaces between. As we close the previous chapter, we listen to the stories carried by light across nearly 14 billion years. From the cosmic microwave background to the subtle effects of gravitational lensing, every beam of light became a patient messenger, quietly preserving the history of the cosmic web. Because of those messages, humanity gradually discovered that the universe is not a chaotic emptiness. It is an immense network woven from filaments, galaxy clusters, and invisible rivers of matter. Yet if you spend enough time contemplating a map of the cosmic web, you may begin to notice something even more surprising. The most striking feature is not where galaxies are abundant. It is the regions where almost nothing seems to exist. At first, that sounds almost contradictory. Why should the largest structure in the universe consist mostly of empty space, if the filaments resemble colossal highways linking galaxies together? Then between those highways lie dark regions so vast that they challenge the limits of human imagination. Astronomers call them cosmic voids. The name alone invites images of complete emptiness, a cold, silent place where absolutely nothing exists. Yet, as with so many things in nature, reality is more subtle than appearances suggest. A void is not completely empty. That is the very first lesson modern astronomy teaches us. If an imaginary spacecraft could travel into the heart of one of these cosmic voids, it would not enter absolute nothingness. Scattered throughout that enormous space would still be isolated hydrogen atoms, extremely diffuse streams of hot gas stretching across millions of light years, small amounts of dark matter, and occasionally, a few lonely galaxies drifting quietly through an almost endless silence. It is simply that everything exists there in far smaller quantities than elsewhere within the cosmic web. To picture this more easily, imagine standing atop a mountain at dawn, looking down across an immense valley. Some regions are covered by dense forests, others are crossed by winding rivers. Yet there are also wide open meadows, where only a handful of shrubs grow. You would never say the meadow contains nothing. It remains part of the landscape. Life is simply less concentrated there. Cosmic voids resemble those vast meadows of the universe. They are not regions of absolute emptiness. They are simply the places where matter exists at its lowest density. Remarkably, these immense voids occupy most of the volume of the observable universe. If the cosmic web could somehow be compressed into a gigantic map, the filaments and galaxy clusters would appear as delicate threads. Most of the picture would consist of quiet, open spaces. That realization surprises many people. In everyday life, we naturally pay attention to what is present. Mountains, cities, people. Rarely do we consider that the empty spaces between them may also play an essential role. Nature, however, seems always to seek balance. A forest is created not only by its trees, but also by the open spaces between their branches. A piece of music consists not only of sound, but also of silence. A night sky is beautiful not only because of its stars, but because of the deep darkness behind them. Perhaps the cosmic voids are quietly offering the same gentle lesson. In the spirit of Carl Gustav Jung's work, human beings often feel uneasy in the presence of emptiness. We fear silence. We fear the quiet spaces within our lives. We try to fill them with work, with noise, with endless thought. Yet Jung also believed that it is precisely within those moments of inner stillness that we encounter ourselves most deeply. This is not a comparison between psychology and astrophysics. Rather, it is a symbolic resonance. Cosmic voids resemble the quiet places within the universe. They are not meaningless. They allow the entire surrounding network to reveal itself more clearly. If we looked only at the filaments, we would never fully understand the shape of the cosmic web. The voids themselves give the network its structure. For this reason, many astronomers compare the cosmic web to an enormous sponge. The matter forms the framework. The voids become the open spaces within it. Without those empty regions, the structure would lose its distinctive form. One of the most famous cosmic voids ever discovered measures more than 300 million light-years across. To appreciate that distance, remember that light, the fastest thing known in nature, travels nearly 300,000 kilometers every second, yet still requires more than 300 million years to cross from one side of that void to the other. If all of human history were no more than a single breath, light would need thousands of times longer than the entire span of civilization simply to traverse one cosmic void. That realization teaches us the true scale of the universe, not merely through numbers, but through humility. Yet cosmic voids are not fixed forever. They continue to change. They continue to evolve. And remarkably, gravity itself is the reason they continue growing larger. At first, that seems counterintuitive. We naturally think of gravity as pulling everything together. That is certainly true. But because matter is continually drawn toward the filaments and galaxy clusters, the regions that were already sparse become increasingly empty. Imagine a broad field after a gentle rain. The water does not remain evenly spread across the ground. It slowly flows toward the lower places. As more water gathers there, the higher ground becomes drier still. Cosmic voids behave in much the same way. Matter does not disappear. It simply leaves the sparse regions and flows toward areas where gravity is stronger. Across billions of years, the filaments become increasingly distinct. Galaxy clusters grow ever more massive, and the voids become larger still. It is an extraordinarily slow process. So slow that no civilization could ever observe it directly from beginning to end. Yet through decades of astronomical observations and sophisticated computer simulations, humanity has begun to perceive its rhythm. It is the rhythm of a universe quietly reorganizing itself. If we could somehow accelerate cosmic time, as though fast-forwarding a film spanning billions of years, we would witness a spectacle both majestic and profoundly peaceful. Galaxy clusters would slowly expand like islands growing within an immense ocean. The filaments would gradually become thicker, brighter, and more interconnected. Meanwhile, the cosmic voids, the seemingly unchanging empty regions, would quietly evolve in a remarkable way. They would not shrink. Instead, they would continue to expand. At first, this seems contrary to intuition. If gravity always draws matter together, why should empty spaces grow larger? The answer lies within the uneven distribution of matter itself. Imagine a large sheet of fabric spread across a table. Now gently pull the fabric inward at several different points. Not only do the places beneath your fingers become thicker, the spaces between them stretch farther apart. The cosmic web evolves in much the same way. Its filaments act like immense rivers of gravity. They continuously draw gas, dark matter, and even small galaxies toward themselves. Galaxy clusters, located where many filaments intersect, attract still more matter from those same cosmic rivers. Every current flows toward regions of greater density. What remains are the voids. They are not pushed outward. They simply become regions that retain less and less matter. Across billions of years, more matter leaves these sparse regions than enters them. As a result, the voids grow steadily larger, while their boundaries, the galaxy walls and filaments, become ever more sharply defined. There is something wonderfully unusual about this process. It is not creation through addition. It is creation through subtraction. A sculptor does not create a statue merely by adding stone. The sculpture emerges through the patient removal of everything that does not belong. Nature appears to shape the cosmic web in much the same way. As matter gradually leaves the voids, the architecture of the universe becomes ever more clearly revealed. It is an idea well worth quietly contemplating. As requested, I will assume the role of a professional Vietnamese English translator and literary adaptation specialist, specializing in scientifically accurate translations for long-form narration. My task is to translate your text faithfully, without omitting, adding, or altering any information, while preserving a gentle, meditative narrative style, inspired by the spirit of Carl Gustav Jung, suitable for a bedtime audience. Filaments that nourish galaxy clusters. In life, we often assume that growth means accumulating more knowledge, more experiences, more achievements. Yet sometimes, true maturity comes not from holding on, but from learning to let go. Letting go of what is no longer necessary, letting go of old fears, letting go of the thoughts that weigh heavily upon the mind. This is not a conclusion drawn from astronomy. Rather, it is a philosophical reflection inspired by the quiet way the universe unfolds. Carl Gustav Jung believed that the journey toward maturity is not merely the accumulation of knowledge, it is also the courage to face oneself, to recognize what truly belongs to us, and what is merely an outer shell waiting to be released. In a symbolic sense, cosmic voids tell a remarkably similar story. It is precisely when matter moves away that the larger structure gradually reveals itself. What is especially fascinating is that life, on the scale of galaxies, still exists within these cosmic voids. A number of small galaxies have been discovered drifting through these immense expanses. They tend to be more isolated. They experience fewer collisions. They are influenced far less by enormous neighboring galaxies. In many cases, galaxies that reside within a void follow evolutionary paths quite different from those found at the crowded centers of galaxy clusters. Because their surroundings are calm and relatively free from powerful gravitational interactions, they may continue forming new stars for much longer periods of time. This reminds us that even in the regions that appear the emptiest, the universe is never completely silent. The lives of stars continue. Light continues to be born. Planets may still take shape, and perhaps, Somewhere within one of those solitary galaxies, another civilization is gazing into its own night sky, wondering whether it is truly alone in the endless darkness. There is something deeply moving about that thought, because it reminds us that solitude and connection can exist at the very same time. A galaxy within a void may seem unimaginably distant from every other galaxy, yet it still belongs to the cosmic web. A person may pass through long seasons of stillness in life, but that does not mean they have become disconnected from the world. Perhaps every form of existence is joined together by threads too subtle for the eye to see. This is also what makes a map of the cosmic web so breathtaking when viewed from a truly vast perspective. If we focus on only a single galaxy cluster, we see thousands of galaxies in motion. If we step farther back, we begin to see the filaments connecting those clusters together. But only when we move far enough away to include the vast cosmic voids does the entire network finally emerge. It is much like reading a novel. One chapter alone is never enough to understand the whole story. One character alone cannot reveal the meaning of the work. Only by seeing the book in its entirety do all of the details begin to connect. The universe tells its story in much the same way. Galaxies are its characters. Filaments are its narrative threads. Galaxy clusters are its moments of emphasis. And the voids are the quiet pauses that give rhythm to the entire story. Perhaps that is why astronomers today no longer think of cosmic voids as regions where nothing exists. Instead, they recognize them as an essential component of the architecture of the universe. Without them, we could never understand why filaments formed the way they did. Without them, any measurement of the universe's matter distribution would be missing half of the picture. Without them, the cosmic web would no longer be a complete network. There is a quiet beauty in that realization. Sometimes what gives a structure its meaning is not only what is present, it is also the space that surrounds it. A beautiful garden needs pathways. A beautiful painting needs breathing room. A beautiful piece of music needs moments of silence. And the universe is beautiful because, between its hundreds of billions of galaxies, there remain tranquil oceans of darkness, stretching across hundreds of millions of light years. As the night deepens beyond your window, it becomes easy to imagine that we ourselves are quietly drifting through one of these immense cosmic voids. There is no sound in space. No wind, only the light of distant galaxies, silently crossing billions of years of darkness before finally reaching human eyes. That emptiness is not as cold as we once imagined. It is part of balance, part of beauty, an indispensable part of the universe's story. And perhaps, in our own lives, moments of stillness are not signs of loss at all. They may simply be the space required for what truly matters to come gently into view, just as the cosmic voids have allowed the magnificent architecture of the cosmic web to reveal itself over nearly 14 billion years of cosmic evolution. In the next chapter, we will leave these quiet expanses behind and return to the vibrant currents of the cosmic web, where the filaments serve as the universe's great highways, silently transporting gas, dark matter, and even entire galaxies, nourishing the continued growth of colossal galaxy clusters that are still evolving to this very day. Filaments that nourish galaxy clusters. As we leave behind the tranquil cosmic voids of the previous chapter, perhaps the image that lingers in our minds is one of immense emptiness regions, where matter is so sparse that even light requires hundreds of millions of years to cross them. But if the voids are the quiet pauses within the universe's grand symphony, we now return to its melodies that never cease to flow. For woven between those vast empty spaces are immense ribbons of matter, delicate in appearance, yet astonishingly powerful, connecting hundreds of billions of galaxies throughout the cosmos. These are the filaments of the cosmic web, or perhaps, more fittingly, they are the invisible rivers that nourish the universe itself. The first time many people see a three-dimensional map of the cosmic web, they often feel as though they are looking at the neural network of an enormous brain. Long strands curve gracefully, branch outward, and intersect one another, creating a structure that is both intricate and remarkably ordered. Where several strands meet, colossal galaxy clusters are born. Between those junctions, the filaments stretch endlessly through the darkness like infinite cosmic roads. At first glance, they may appear to be little more than simple connections. In reality, however, they are among the most essential components of the universe's entire architecture. Astronomers often compare filaments to the highways of the cosmos. This is more than a beautiful metaphor. It is also a remarkably accurate description of their role. Imagine a vast nation. Its thriving cities do not exist in isolation. They are connected by highways, railways, and transportation networks. Those roads carry people, food, resources, and energy, allowing every city to continue growing. If the entire transportation system was severed, those cities would gradually weaken. Filaments perform a remarkably similar function within the universe. They are immense rivers of gravity. Along them, matter is constantly in motion, not at a pace humans can perceive, but according to a rhythm measured across billions of years. What flows along these cosmic highways is not automobiles or trains. It is hydrogen gas, helium, dark matter, and even entire galaxies, quietly drifting along the currents of gravity. As requested, here is a faithful, complete English translation that preserves the original meaning, maintains a gentle bedtime narration, and reflects the contemplative spirit associated with Carl Gustav Jung, without adding or omitting any details. There is something truly wonderful about that thought. We often imagine galaxies as motionless islands floating in the vast ocean of space, but in reality, they are also travelers, journeying along the invisible pathways of the cosmic web. Not every galaxy remains where it was born. Many smaller galaxies are gradually drawn along the filaments. Slowly, they drift toward larger galaxy clusters. The process unfolds so gradually that a civilization like ours could never witness it directly. Yet through computer simulations and decades of astronomical surveys, scientists have discovered that these cosmic currents truly exist. What is especially fascinating is that filaments do more than transport galaxies. They also carry immense streams of gas. These rivers of gas provide the essential raw material from which stars are born. Every star requires gas to come into existence. Without hydrogen, without helium, there would be no enormous nuclear furnaces that we call stars. And without stars, there would be no heavy elements, no carbon, no oxygen, no iron, no planets, and there would be no life as we know it today. In other words, as filaments carry gas throughout the cosmic web, they are doing far more than moving matter. They are carrying the seeds of future generations of stars. There is a quiet beauty in that thought. A stream of gas drifting silently between galaxies today may, billions of years from now, become a new star, a new planet, and perhaps, somewhere, the birthplace of life itself. In a way, filaments resemble the rivers of Earth. A river does not keep its water for itself. It carries water from the mountains to the plains. It nourishes forests. It nourishes people. It nourishes entire civilizations. Filaments do much the same. They do not keep matter. They guide matter to where it is needed. Perhaps that is why many astronomers describe them as the circulatory system of the universe. From a symbolic perspective, this also echoes Carl Gustav Jung's understanding of the interconnected layers of human life. He believed that no individual exists as a completely isolated being. We are continually shaped by our families, our communities, our cultures, and by deeper psychological patterns that extend beyond our immediate awareness. Although this is not a scientific comparison, the image of the filaments offers a beautiful reflection. Just as invisible streams of matter connect galaxies across the cosmos, human life is woven together by countless unseen relationships that we often fail to recognize. Another remarkable feature of filaments is that they are more than cosmic highways. There are also supply lines. Where many filaments converge, more and more matter accumulates. Those are the places where clusters, vast collections of galaxies, begin to form. If filaments are like rivers, then galaxy clusters are like enormous lakes into which every river eventually flows. It is not difficult to imagine what happens next. The more streams of matter arrive, the larger the galaxy cluster becomes. The more gas it contains, the more galaxies it gathers. The more interactions and collisions occur, and the entire structure continues to evolve over billions of years. This explains why the largest galaxy clusters are always found at the great intersections of the cosmic web. It is not a coincidence. It is the result of billions of years of accumulating matter. Just as the great cities of Earth often emerge where rivers meet places blessed with transportation, resources, and opportunity, the universe seems to follow a remarkably similar principle. The most highly connected places become the places that flourish the most. Yet this naturally leads to another fascinating question. What happens to a galaxy after it completes its long journey along a filament and finally enters a massive galaxy cluster? Does it remain the same as it was before? Or does its new environment begin to reshape its destiny? If, in the previous section, we followed the movement of matter along these immense cosmic filaments, now let us imagine accompanying a small galaxy on its own journey across billions of years. At first, the galaxy drifts quietly within a vast filament. Around it lie diffuse clouds of hot gas, invisible dark matter, and a handful of neighboring galaxies, all slowly moving in the same direction. There is no sound, no urgency, only gravity, quietly carrying out its work, patiently guiding everything forward. After hundreds of millions of years, the galaxy gradually approaches a region where many filaments converge. From a great distance, the galaxy cluster appears as little more than a faint patch of light. But as it draws closer, the scene becomes increasingly magnificent. Hundreds, then thousands of galaxies, all revolving around an immense gravitational center. Between them drifts gas heated to tens of millions of degrees. Hidden beneath it all lies an amount of dark matter greater than all of the visible matter combined. This is a galaxy cluster. One might imagine it as a vast ocean, while each individual galaxy is like a ship entering waters governed by entirely different currents. What is remarkable is that once a galaxy enters this environment, it no longer remains unchanged. Its surroundings begin to transform it. One of the first things that happens is that the galaxy must travel through the extremely hot gas that fills the cluster. Although this gas is extraordinarily diffuse, the galaxy moves through it at speeds ranging from hundreds to thousands of kilometers per second. Over time, the accumulated pressure becomes strong enough to gradually strip away the colder gas contained within the galaxy itself. Astronomers call this process ram pressure stripping. The image is much like a car speeding through heavy rain. The rushing air continually pushes the raindrops backward. In the universe, however, what is swept away is not rainwater but the cold gas that serves as the essential fuel for forming new stars. As that reservoir of gas gradually disappears, the galaxy begins to change. Regions where new stars are born become fewer. Young blue stars appear less and less frequently. The galaxy's light slowly shifts toward shades of yellow and then red as most of the remaining stars have grown old. Over time, a galaxy that was once vibrant and active may become far quieter. This is not an ending. It is simply another stage in the life cycle of a galaxy. Beyond losing their gas, galaxies within a cluster are also continually influenced by the gravitational pull of their neighboring galaxies. The distances between galaxies remain enormous. Yet over billions of years, countless small interactions accumulate into profound transformations. Some galaxies are stretched, some become distorted, some collide and merge with one another. After each merger, a larger galaxy is born. Spiral arms may disappear. Shapes are transformed. The orbits of billions of stars are rearranged. All of this unfolds so slowly that, within the span of a human lifetime, we would notice no movement at all. But according to the universe's clock, it is an uninterrupted flow. Interestingly, not every galaxy follows the same path. Galaxies that spend long periods within clusters tend to become older in character. By contrast, galaxies that remain along filaments or within cosmic voids often continue receiving fresh supplies of gas, allowing them to form stars for much longer. This tells us that environment plays an essential role in the evolution of a galaxy. A galaxy's future is shaped not only by its own nature, but also by the place in which it lives. This is one of the most compelling discoveries of modern astronomy. It reminds us that even on the grandest scales of the universe, existence is always woven through relationships. No galaxy is ever completely isolated. No galaxy cluster forms without receiving matter from the filaments. No filament exists independently of the cosmic web itself. Every structure influences every other structure. In the spirit of Carl Gustav Jung's work, human beings also do not grow in complete isolation. We are shaped by our relationships, by our families, our cultures, our communities, and by the experiences that accumulate throughout our lives. This is not a conclusion drawn from astronomy, but rather a symbolic reflection that helps us appreciate the beauty of connection. Just as galaxies are transformed when they enter a galaxy cluster, people, too, often mature through the environments they encounter along the journey of life. Perhaps that is why, when we look upon the cosmic web, we see far more than a network of matter. We see an immense circulatory system. The filaments carry gas. The gas gives birth to stars. The stars forge the heavy elements. Those elements become planets. Upon some of those planets, life may one day emerge. And somewhere, beings capable of wonder may look up into the night sky, seeking to understand the very network that made their own existence possible. There is something beautifully complete about that cycle. The carbon atoms within our own bodies were once forged deep inside the hearts of stars. As requested, here is a faithful, complete English translation in a gentle American English narration style, preserving every idea and maintaining the calm, reflective tone inspired by the spirit of Carl Gustav Jung, without adding or omitting any information. Those stars were born from vast clouds of gas. Those clouds of gas were guided by the filaments. The filaments grew within the cosmic web, and the cosmic web itself arose from unimaginably tiny fluctuations in the moments following the Big Bang. If we trace that chain of connections all the way back, we begin to realize that the distance between humanity and the dawn of the universe is not nearly as great as we once imagined. Every breath, every heartbeat, every atom within our bodies is the result of a story that has unfolded over nearly 14 billion years. Perhaps that is what makes the study of the universe so extraordinary. It does not simply answer questions about distant galaxies quietly. It also answers questions about ourselves, where we came from, what we belong to, and how life could emerge at all within a universe so unimaginably vast. As the night settles into stillness, imagine the entire cosmic web as an ancient forest breathing quietly in the darkness. Its filaments are like living vessels, nourishing each galaxy cluster. The galaxy clusters, in turn, resemble great hearts, patiently gathering matter across billions of years. No sound echoes through that immense expanse. Only gravity, endlessly patient, carries out its work, weaving the beauty that humanity has only just begun to understand. And just as a healthy body depends upon its circulatory system to sustain life, the universe depends upon its filaments to nourish its galaxy clusters. Without these flowing currents, galaxy clusters could never continue to grow. Galaxies would receive no fresh supplies of gas, and the story of cosmic evolution would have unfolded in an entirely different way. In the next chapter, we will meet two mysterious forces that together determine the future of the entire cosmic web: dark matter, the quiet force that builds the network, and dark energy, the mysterious component causing space itself to expand ever more rapidly. One draws things together, the other stretches them apart. It is through the silent dialogue between these two invisible forces, unfolding across billions of years, that the ultimate destiny of the universe we are exploring tonight will be decided. Dark matter and dark energy. As we concluded the previous chapter, we followed the immense filaments of the cosmic web, where streams of gas, dark matter, and entire galaxies drift quietly like endless rivers flowing through the cosmos. We watched galaxy clusters grow as fresh supplies of matter continually arrived along these invisible cosmic highways. Yet when we step back and observe the entire picture from an even greater distance, another gentle question begins to emerge. What is truly guiding all of this? Who is the architect of the cosmic web? And what will ultimately determine the fate of this immense network over the billions of years yet to come? To answer those questions, we must become acquainted with the two most mysterious characters in modern cosmology. Interestingly, both are almost entirely invisible. We cannot see them with our eyes. We cannot touch them. Even today, scientists continue striving to understand their true nature. They are dark matter and dark energy. Their names sound remarkably similar, yet they are not the same. They are fundamentally different. They play entirely different roles, and together they appear to drive two opposing tendencies in the evolution of the universe. If we wish to imagine them in the simplest possible way, perhaps we could think of dark matter as a pair of gentle hands patiently gathering scattered pieces together. Meanwhile, dark energy is like an invisible breath, slowly stretching the fabric of space itself. One brings things together, the other pulls them apart. The delicate balance between these two processes has shaped the universe we see today. Let us begin with dark matter. Throughout our journey so far, we have encountered this invisible companion many times. It formed the original framework of the cosmic web. It allowed gravity to gather matter into filaments and galaxy clusters. It keeps many galaxies rotating without flying apart. What is truly remarkable is that although dark matter neither emits light, reflects light, nor interacts significantly with ordinary matter except through gravity, it still accounts for most of the matter in the universe. Perhaps we can picture it as the roots of an ancient tree. When we admire a great tree, our attention naturally goes to its trunk, its branches, and its leaves. Yet the part that truly keeps the tree standing lies hidden beneath the ground. The roots never display their beauty openly, but without them, there would be no trunk, no branches, no seasons filled with blossoms. Dark matter is much the same. It is not the first thing we notice, yet it is the foundation that allows the cosmic web to exist. Across billions of years, the gravity of dark matter quietly draws hydrogen, helium, and small galaxies toward the filaments. That flow continues without interruption. No sound, no haste. Only gravity patiently carrying out its work. The image reminds many people of a great forest. The underground streams beneath the soil are rarely seen, yet they quietly nourish every tree. The cosmic web possesses similar underground rivers. They are what we call dark matter. If dark matter were the only actor in this story, the evolution of the universe would probably be rather straightforward. Galaxies would continue drawing one another closer. Galaxy clusters would steadily grow larger. The cosmic web would gradually become denser over time. But toward the end of the 20th century, astronomers made a completely unexpected discovery. Instead of slowing under the influence of gravity, the expansion of the universe was actually accelerating. The discovery astonished nearly the entire astronomical community. Because our intuition tells us that gravity always pulls things together. If you throw a ball into the air, it slows before falling back down. If galaxies continually attract one another, then the expansion that began with the Big Bang should gradually slow as well. Yet observations of distant exploding stars supernovae told a different story. Space was not merely continuing to expand. its expansion was speeding up. It was as though a car climbing a hill did not slow down at all, but instead accelerated more and more. To explain this astonishing phenomenon, scientists introduced the concept of dark energy. This is not a form of energy in the familiar sense, like heat or electricity. Rather, it is the name given to whatever causes space itself to expand at an ever-increasing rate. If dark matter resembles hands gently drawing galaxies together, then dark energy is like the very fabric of the universe slowly being stretched. One important point deserves careful attention. Dark energy does not push galaxies apart the way wind pushes a falling leaf. Galaxies still move primarily under the influence of gravity. What is changing is the distance between them, because the space separating them continues to expand. Imagine tiny ink dots drawn upon the surface of a rubber balloon. As the balloon inflates, the dots need not move on their own. The distance between them naturally increases, not because the dots are traveling, but because the surface carrying them is expanding. Space itself behaves in much the same way. It is a remarkable thought. We often imagine space as nothing more than the place where everything exists. Yet space itself has a history. It has evolved, and it continues changing every second. From a symbolic perspective, this gently echoes one of Carl Gustav Jung's recurring themes. He often described the human psyche not as something fixed and motionless, but as a living process of continual transformation. Human beings are constantly influenced by different forces. On one side, the longing for belonging, stability, and roots. On the other, the desire to grow, to explore, and to step into the unknown regions within ourselves. This is, of course, a philosophical reflection, rather than a scientific comparison with dark matter or dark energy. Even so, it helps us appreciate that within the human soul, opposing tendencies may work together in shaping genuine growth. Perhaps this is why the story of dark matter and dark energy is not only a story about physics, it is also a story about balance, between connection and expansion, between holding on and letting go, between quiet forces that together shape something far greater than themselves. If dark matter is the quiet force gathering the universe's pieces together, while dark energy continually expands space itself, perhaps the most beautiful question we can ask is this: what happens when these two tendencies coexist for billions of years? At first glance, they resemble two melodies being played at the same time. One invites everything to draw closer together. The other gently carries everything farther apart. There is no collision, no battle in the way human beings usually imagine conflict. Only two natural processes unfolding together on the grandest scale we have ever known. It is the balance between them that has given the universe its present form. On relatively small scales within a galaxy, or even within a galaxy cluster, dark matter and ordinary gravity still dominate. That is why stars continue orbiting the centers of galaxies, why the galaxies of the local group remain gravitationally bound to one another, why the Milky Way and the Andromeda Galaxy continue moving toward their eventual encounter despite the overall expansion of the universe. This is an important point. Dark energy does not tear apart structures already held together by gravity. Its influence becomes significant only across the immense distances separating galaxy clusters. Perhaps we can imagine islands scattered across a great ocean. Each island retains its own shape, yet the sea between them slowly widens. The islands do not fall apart. They simply become farther apart. The universe is undergoing a remarkably similar process. Galaxy clusters remain intact, yet the vast expanses between them continue to grow. That is why astronomers often say that dark matter builds the cosmic web, while dark energy determines its long-term future. What is especially remarkable is that both of these components remain invisible. Humanity has never directly observed dark matter, nor have we directly observed dark energy as a tangible substance. We know of them only through the influence they leave upon the universe. Perhaps this is one of the most humbling lessons modern science has to offer. The forces that govern most of the universe are also the ones we understand the least. For centuries, humanity believed that the stars made up most of the universe. Then we discovered galaxies, then dark matter, then dark energy. Each new discovery made the picture both larger and more mysterious. That does not represent a failure of science, quite the opposite. It is the very beauty of science itself. Every genuine answer opens the door to new questions. If we imagine the cosmic web as a vast living organism, then dark matter is like the skeleton and circulatory system quietly supporting the entire body. Dark energy, meanwhile, is like the slow, steady breath of space itself. One holds, the other expands. One creates distance. Yet perhaps it would not be entirely accurate to think of them as two opposing rivals. In reality, they coexist within a single, unified system. Without dark matter, galaxies would have struggled to form. Without dark energy, the long-term evolution of the universe would have unfolded in an entirely different way. Nature does not seem to choose one side over the other. Instead, it allows many processes to exist together. It is precisely that balance that creates the beauty of the whole picture. The image brings to mind an ancient forest. Some trees are reaching upward with vigorous new growth. Some leaves are gently falling to the ground. Some seeds are only just beginning to sprout. Some old trunks are slowly returning to the soil. If we focus on only one of those processes, we might conclude that the forest is either growing or disappearing. But when we step back and see the whole, we realize that the forest is simply continuing to live. The universe is much the same. It is not only about formation. It is not only about expansion. It is not only about connection. All of these processes coexist within a rhythm that has continued for nearly 14 billion years. In the spirit of Carl Gustav Jung's work, human growth often comes from learning to reconcile the seemingly opposite aspects within ourselves. He viewed maturity as a journey toward wholeness, where different tendencies do not necessarily cancel one another out, but instead coexist within a more balanced and integrated structure. This is not a scientific comparison with dark matter and dark energy, but rather a philosophical reflection. It gently suggests that even on the largest scales of the universe, development does not arise from a single force acting alone. Today, cosmologists continue searching for the answer to one profound question. What will happen in the unimaginably distant future? If dark energy continues to dominate as it appears to today, the distances between galaxy clusters will continue to grow. After tens or even hundreds of billions of years, galaxies that are now visible to one another may drift permanently beyond each other's observable horizons. Each galaxy cluster could become an isolated island within an ever-expanding cosmic ocean. Yet inside those clusters, gravity will continue its quiet work. Galaxies may still merge. New stars may continue to form, so long as enough gas remains. Planets will continue orbiting their stars. In other words, the expansion of the universe does not mean that every structure will dissolve. It simply changes how those structures relate to one another across the greatest cosmic distances. There is something deeply peaceful about that thought. The universe is not a machine racing toward a sudden ending. It is more like a piece of music whose tempo slowly changes. Old melodies gradually fade into the distance. The pauses between them grow longer, yet the music continues. When we look up at the night sky, it is difficult to sense that all of space around us is expanding every single moment. Galaxies continue their journeys. The cosmic web continues to evolve. And the universe's two most mysterious components quietly continue shaping the future of everything. Perhaps the greatest gift of this chapter is not its numbers or its physical models. Perhaps it is simply a way of seeing, a perspective that reminds us that existence is always the result of many forces acting together. Some forces draw us back toward our origins, others open new horizons before us. And perhaps maturity is not about choosing one while rejecting the other, but about discovering the balance between them. The cosmic web itself exists through that balance. Dark matter quietly continues connecting. Dark energy gently continues expanding. Neither completely triumphs. Neither completely disappears. Together, they continue writing the universe's story. A story that has already unfolded across nearly 14 billion years. And as the night grows quieter still, perhaps it becomes easy to imagine that we ourselves are drifting within that same story. A tiny planet orbiting an ordinary star, belonging to an ordinary galaxy, resting upon one filament of the cosmic web, within a universe that continues to expand in silence. That thought does not make humanity seem insignificant. Instead, it reminds us that we have always been part of something far greater than ourselves. A story that is still being written by light, gravity, and time. In the next chapter, we will explore how humanity has learned to see dark matter through some of the most advanced technologies ever created. From massive galaxy surveys and gravitational lensing to space missions that are gradually constructing the most detailed three-dimensional map of the cosmic web ever achieved. How do we see dark matter? As we closed the previous chapter, we became acquainted with the universe's two most mysterious components. Dark matter, the quiet force that binds and builds the cosmic web, and dark energy, the phenomenon causing space itself to expand ever more rapidly. One gathers matter together. The other gradually carries cosmic structures farther apart. Between these two processes, the entire history of the universe continues to unfold. Yet perhaps one very natural question still remains. If dark matter is completely invisible, if it neither emits light, reflects light, nor significantly interacts with ordinary matter except through gravity, then how can humanity know that it truly exists? How can we create maps of something no eye has ever seen? Perhaps this is one of the most beautiful stories in modern science. Instead of trying to observe the invisible directly, humanity learned to observe the effects it leaves behind. In everyday life, we experience this principle all the time. You cannot see the wind, yet you see branches swaying. You cannot see gravity, yet you watch a leaf fall toward the ground. You cannot see a magnetic field, yet you watch a compass needle slowly turn toward the north. Dark matter was discovered in much the same way. We do not see it directly. We see how it changes the world around it. One of the most important tools that allows astronomers to do this is gravitational lensing. In the previous chapter, we learned that gravity can bend the path of light. When light from a distant galaxy passes through a region containing a large amount of mass, its path becomes curved. If that region contained only the visible stars and gas we can observe, the amount of bending would have a predictable value. But reality tells a different story. Again and again, the light bends more than expected. That can only mean that additional invisible mass is present. That invisible mass is dark matter. The remarkable part is this: scientists do not need to see dark matter directly to determine where it is. They simply observe millions of beams of light passing through it. It is much like standing beside a lake. You cannot see the current beneath the surface, yet you can infer its presence from the ripples spreading across the water. Light becomes the storyteller, space becomes the map, and dark matter leaves its signature upon the journeys of countless photons. Using millions of measurements like these, astronomers gradually assembled the first maps showing how dark matter is distributed throughout the universe. At first glance, those maps resemble faint, misty clouds. But once they are combined on enormous scales, a familiar picture begins to emerge. The cosmic web, its filaments, its galaxy clusters, its immense voids. They appear not because of the light emitted by stars, but because of the gravitational fingerprints left behind by dark matter. There is something especially beautiful about this way of making discoveries. Sometimes, what matters most is not seeing. It is learning how to read subtle signs. In the spirit of Carl Gustav Jung's work, Many of the deepest dimensions of the human mind cannot be observed directly either. They reveal themselves through dreams, symbols, emotions, and behavior. This is only a philosophical reflection rather than a scientific comparison. Yet both astronomy and psychology remind us of the same gentle truth. What is invisible can still leave unmistakable traces for those who know how to observe carefully. Yet gravitational lensing tells only part of the story. To understand the entire cosmic web, astronomers also needed to determine the locations of millions of galaxies throughout space. That is why galaxy surveys were created. If we imagine the universe as an unexplored continent, then galaxy surveys resemble patient expeditions carefully measuring every mountain, every river, and every valley to produce a complete map. Each galaxy is catalogued, its distance is measured, its position in three-dimensional space is determined. At first, the task may sound fairly straightforward, but consider its true scale. Not hundreds of galaxies, not thousands, but millions, and eventually tens of millions, each one lying millions or even billions of light-years away, each requiring its distance to be measured through multiple independent techniques. Each tiny data point is then combined with countless others to create one immense picture. It is rather like placing individual dots of ink onto a blank sheet of paper. At first, they seem completely unrelated, but once enough dots have been added, the image gradually emerges. That is how the cosmic web has been revealed, not through a single photograph, but through millions of careful measurements collected over many decades. Perhaps there is another quiet lesson here. We often imagine that great discoveries arrive in dramatic moments of sudden inspiration. Yet in reality, most scientific progress is built from countless small steps. One measurement, one observation, one piece of data, one sleepless night beside a telescope, then another, and another. It is that patience that has gradually allowed humanity to perceive what once seemed entirely invisible. Today, when galaxy surveys are combined with gravitational lensing data, they do far more than simply tell us where galaxies are located. They reveal where dark matter resides, where filaments stretch across space, where galaxy clusters will continue growing, and where the great cosmic voids continue expanding over time. The picture is still incomplete, yet every year it becomes a little clearer, like an oil painting patiently enriched with one layer of color after another, or an ancient map slowly filled in after each new voyage across unknown seas. Then, with the rapid development of space technology during the 21st century, humanity began building instruments even more powerful than before, not merely to observe individual galaxies, but to create an extraordinarily precise three-dimensional map of the entire cosmic web. In the previous section, we explored how light and galaxy surveys first allowed humanity to glimpse the hidden presence of dark matter. Now, that journey continues with tools more powerful than ever before. For centuries, human beings could only gaze at the heavens with the naked eye. Then came the first telescopes. Later, enormous observatories built atop remote mountain peaks. But to map the cosmic web across tens of billions of light-years, humanity required entirely new eyes machines capable of observing billions of galaxies simultaneously with unprecedented precision. One of the most ambitious of these projects is the Euclid mission. If the cosmic web were an endless forest, Euclid would be like an artist patiently sketching every tree, every stream, and every open meadow, until the complete landscape finally emerges. Remarkably, Euclid does not attempt to observe dark matter directly. Instead, it continues, using the very method nature itself has suggested. It studies light. It measures the incredibly tiny distortions in the shapes of billions of distant galaxies. From those nearly imperceptible distortions, scientists can infer where dark matter is most heavily concentrated. Imagine looking across the surface of a lake on a day when only the gentlest breeze is blowing. A single ripple reveals very little, but if you observe the entire lake, Millions of tiny ripples together tell a complete story about the wind. The light from billions of galaxies behaves in much the same way. Each galaxy carries only a tiny signal, but when all those signals are combined, an enormous map begins to appear. It is no longer merely a map of stars. It is a map of gravity itself. Perhaps what moves so many people most deeply is this: humanity has never traveled beyond the Milky Way. We have only set foot upon the moon. Yet through mathematics, light, and extraordinary patience, we have begun mapping a structure that stretches across billions of light years. That is not only a triumph of technology, it is also a triumph of curiosity. Alongside Euclid, another remarkable project is opening an entirely new era of astronomy. They serve as celestial landmarks that help astronomers trace the immense architecture of the cosmic web. One of the most remarkable aspects of modern astronomy is that no single observation tells the entire story. Each survey reveals a different layer of reality. Galaxy surveys map where galaxies are located. Gravitational lensing uncovers the invisible distribution of dark matter. Quasars illuminate the vast distances between galaxies. The cosmic microwave background preserves the memory of the infant universe. Like pieces of an enormous mosaic, each dataset contributes a small part of a much larger picture. When they are combined, the hidden structure of the universe gradually emerges. There is something profoundly beautiful about that process. Imagine trying to understand an ancient forest. One person studies the trees, another observes the rivers, another records the changing seasons, another examines the soil beneath the roots. Each sees only part of the whole. But together, they begin to understand the forest as a living system. The cosmic web has been revealed in much the same way, not through one telescope, not through one discovery, not through one generation of scientists, but through countless observations patiently gathered over decades. From a symbolic perspective, this also echoes one of Carl Gustav Jung's recurring themes. He often suggested that genuine understanding rarely arrives all at once. Instead, it grows gradually, as seemingly separate experiences, memories, and symbols slowly form a more coherent whole. This is not a scientific comparison with astronomy, but it offers a gentle philosophical image. Just as an individual slowly comes to understand the deeper patterns within a lifetime, humanity is slowly learning to recognize the hidden patterns woven throughout the universe. Perhaps that is why the cosmic web inspires such quiet wonder. It reminds us that reality is often far more interconnected than it first appears. Individual galaxies are not isolated islands. Clusters are not independent cities. Even the greatest cosmic structures belong to something larger. Everything participates in a network extending across billions of light years. When we step back far enough, relationships become more important than individual objects. That realization changes the way we see the universe. Perhaps it can also change the way we see ourselves. Throughout history, humanity has often imagined itself standing at the center of existence. Modern astronomy gently offers another perspective. We are not at the center, yet we are not separate either. Our planet belongs to the solar system. The solar system belongs to the Milky Way. The Milky Way belongs to the local group. The local group is part of Laniakea. Laniakea stretches along one filament of the cosmic web, and the cosmic web itself is only one chapter in the continuing story of an expanding universe. Seen this way, belonging becomes more meaningful than centrality. Perhaps every level of existence is defined not by isolation, but by connection. As the night grows quieter, imagine looking far beyond the stars visible to the naked eye, beyond the familiar constellations, beyond the Milky Way, beyond the countless galaxies scattered across the darkness. There, immense filaments continue to stretch across hundreds of millions of light years. Great galaxy walls quietly span the cosmos. Vast voids slowly expand between them. Invisible dark matter continues shaping the structure, and light, traveling for billions of years, continues carrying ancient stories toward us. All of it unfolds in silence. No sound crosses those enormous distances. Only gravity, only light, only time. Perhaps that silence is not empty at all. Perhaps it is simply the quiet language in which the universe has always spoken. And perhaps one of humanity's greatest achievements is that we have learned, little by little, to understand that language. In the next chapter, our journey will move even farther into one of the deepest questions in modern cosmology. Does the cosmic web have an edge? Can the largest structures in the observable universe continue forever? Or is there a fundamental limit to how large cosmic structures can become? Together, we will explore the cosmological principle, the largest scales ever observed, and what they reveal about whether the universe remains uniform beyond everything we have mapped so far. What draws so many people to astronomy is not merely the enormous numbers. It is the feeling that, little by little, the pieces begin to fit together. Galaxy surveys, gravitational lensing, the cosmic microwave background, quasar surveys, computer simulations. Each method tells the same story, not in exactly the same way, but each complements the others. It is like several people standing at different vantage points, each describing the same mountain. Every observer sees only one side. Yet when all of those perspectives are brought together, the complete landscape finally emerges. That is how the cosmic web has gradually been confirmed. Not through a single experiment, not through a single telescope, but through the remarkable agreement of many independent methods of observation. From a symbolic perspective, this recalls an idea closely associated with Carl Gustav Jung. He suggested that we rarely come to understand ourselves through one experience or one dream alone. Genuine insight gradually emerges as many symbols, memories, and perspectives come together to form a meaningful whole. This is a philosophical reflection rather than a scientific comparison between psychology and astronomy, but both remind us that the largest pictures are often assembled from countless small pieces. Perhaps that is also the beauty of the cosmic web. No single galaxy can tell the story of the universe. No single galaxy cluster can explain its entire architecture. No single observation can complete the map. But when millions of galaxies are placed upon the same sky, when light that has traveled for billions of years reaches the lenses of modern telescopes, when mathematics, physics, and human patience come together, a picture unlike anything in human history begins to emerge. For the first time, we are able to glimpse the largest home we have ever known. Not Earth, not the solar system, not even the Milky Way, but the immense network that connects them all. As the night outside your window grows quieter, it is easy to imagine that we, too, are living on one of those countless small galaxies. Every night, light from unimaginably distant galaxies silently crosses the filaments of the cosmic web, journeys through immense cosmic voids, and finally reaches Earth. Through the patience of generations of scientists, those ancient rays of light have revealed that the universe has never been a random scattering of stars. It is a structured network, shaped by history and still evolving today. In the next chapter, our journey becomes even more extraordinary. Rather than simply observing the universe, humanity will begin recreating it inside some of the world's most powerful supercomputers. Through simulations such as the Millennium Simulation and Illustris TNG, we will discover how a handful of simple physical laws can, over billions of years, weave the very cosmic web that modern telescopes are only now beginning to reveal, simulating the universe. As we close the previous chapter, we followed the patient efforts of astronomers as they mapped the universe. From the Sloan Digital Sky Survey to immense structures such as the Sloan Great Wall and vast groups of quasars, countless small pieces of data gradually assembled into a breathtaking picture, demonstrating that the cosmic web is not merely a beautiful mathematical concept but a real structure stretching across the night sky. Yet another quiet question now arises. If we can observe the cosmic web as it exists today. Could humanity somehow travel backward through time and witness its entire formation? Of course, we cannot. No civilization could survive long enough to watch nearly 14 billion years of cosmic evolution unfold. But that does not mean we are powerless. Instead of traveling backward through time, scientists imagined something even more ambitious. If we cannot observe the entire history of the universe, why not try to recreate it? That idea gave birth to one of the most fascinating fields in modern astrophysics: cosmological simulations. At first glance, the word simulation may sound like something from a video game or a computer-generated movie, but in science, it carries a far deeper meaning. It is a way of allowing the laws of physics to tell their own story. Scientists do not draw the cosmic web from imagination. Instead, they begin with a young universe based on observations of the cosmic microwave background. They then include equations describing gravity, the expansion of space, dark matter, ordinary matter, and many other physical processes. Finally, they allow those laws to evolve inside some of the most powerful supercomputers ever built. What happens next almost feels miraculous, not because the computer invents something new, but because nature begins recreating itself. Imagine planting a tiny seed in the soil. You do not need to pull each leaf into existence. You do not have to shape every branch by hand. You simply provide the right conditions. Nature does the rest. Cosmological simulations work in much the same way. Scientists do not design individual galaxies. They do not arrange every filament. They do not place galaxy clusters wherever they wish. They establish the fundamental laws. Then they allow time and physics to do the work. Across billions of simulated years, tiny primordial fluctuations gradually grow into filaments, galaxy clusters, and enormous cosmic voids. Remarkably, the final result closely resembles what telescopes actually observe across the real universe. One of the most famous examples is the Millennium Simulation. When it was first unveiled, it astonished astronomers around the world. Within the simulation, tens of billions of dark matter particles interacted solely through gravity across an immense virtual universe. As time passed, they naturally assembled into increasingly complex structures. At first, there were only slightly denser regions. Then small concentrations appeared. Then filaments. Then intersections. Eventually, an enormous cosmic web stretched across the simulated universe. Without prior knowledge, many people would struggle to distinguish the simulation from real observational maps of galaxies. It was an extraordinary moment. For the first time, mathematical equations and astronomical observations met each other. No longer were they two separate stories. They had become two different ways of telling the same cosmic history. That achievement gave cosmologists tremendous confidence. If the laws of physics we understand today can naturally reproduce a universe that closely resembles the real one, then we are likely moving in the right direction toward understanding how the cosmic web formed. Of course, that does not mean every mystery has been solved. Quite the opposite. Every successful simulation opens the door to even deeper questions. Some details still refuse to match perfectly. Some phenomena require new ingredients. Some physical processes remain active areas of research. But that is precisely what makes science so beautiful. Every honest answer leads to more profound questions. From a symbolic perspective, this also echoes one of Carl Gustav Jung's enduring ideas. We cannot literally return to the past and relive every moment of our lives. Yet through memory, symbolism, and careful reflection, we can gradually reconstruct the story that shaped who we have become. This is a philosophical reflection, rather than a scientific comparison between psychology and cosmology. But both invite us to appreciate a similar truth. Understanding the present is often a way of rediscovering our origins. Perhaps that is why cosmological simulations are so captivating. They do not simply predict the future, they retell the past, not with words, but through the same physical laws that have quietly governed the universe since the dawn of time. Watching these simulations unfold feels almost like witnessing a seed sprouting in slow motion. Tiny fluctuations gradually grow, filaments begin to emerge, galaxy clusters slowly become larger, cosmic voids steadily expand. The entire cosmic web seems to mature like a living organism. Perhaps the most remarkable aspect is that no one directs each individual detail. No invisible hand arranges the position of every galaxy. Only a handful of simple laws repeat themselves over unimaginably long periods of time. Perhaps that is one of nature's deepest forms of beauty. Extraordinary complexity can arise from remarkably simple principles. If the Millennium simulation allowed humanity to watch the gravitational framework of the cosmic web emerge from tiny fluctuations after the Big Bang, scientists soon began asking an even more ambitious question. Could we simulate not only the skeleton of the universe, but the rich story unfolding within it? Could the diffuse gas between galaxies, the birth of stars, the evolution of galaxies, and the influence of supermassive black holes all emerge together within a single unified model? That ambition gave rise to a new generation of cosmological simulations, Illustris TNG. The letters TNG stand for the next generation. The name reflects more than improved computing power. It represents a major step forward in humanity's attempt to recreate the history of the universe. Whereas the Millennium simulation focused primarily on the evolution of dark matter and the gravitational framework of the cosmos, Illustris TNG expanded the picture by incorporating many additional physical processes. Not only dark matter, but also hydrogen and helium gas, the birth of stars, supernova explosions, and even cosmic magnetic fields, the evolution of galaxies, and even the supermassive black holes that lie at the centers of many galaxies. With these additions, the simulation no longer resembled a simple sketch. It began to look like a far more complete portrait. Imagine an artist. In the first painting, they sketch only the basic outlines of a forest. There are mountains, a river, the trunks of ancient trees. In the second painting, they begin adding the soft light of dawn, drifting mist, birdsong, the colors of the leaves, and streams reflecting the sky. The forest itself has not changed, yet it suddenly feels alive. Illustris TNG creates much the same impression. Within its simulations, enormous rivers of gas flow along the filaments of the cosmic web, like invisible streams quietly nourishing galaxies across the universe. As enough gas accumulates, new stars begin to ignite, and the light of entire galaxies gradually brightens the surrounding darkness. Elsewhere, supermassive black holes release extraordinary amounts of energy, heating the gas around them and influencing the rate at which new stars form within their host galaxies. What is truly astonishing is that all of these very different processes can coexist within a single, unified model. It demonstrates that nature's laws do not operate in isolation. They constantly interact with one another. Gravity shapes the motion of gas. Gas governs the birth of stars. Stars forge the heavy elements. Those elements become planets. And supermassive black holes, in turn, reshape the environment between galaxies. The entire universe resembles a grand symphony. No instrument performs alone. What excites astronomers most is not simply the beauty of these simulations. It is what happens when they place them alongside real observations. The simulated filaments closely resemble the ones seen in the sky. Galaxy clusters appear in the expected locations. Cosmic voids have remarkably similar sizes and distributions. Even many of the statistical properties of simulated galaxies closely match what telescopes actually observe. Of course, that does not mean the simulations are perfect. Differences remain. Questions remain unanswered. But the remarkable level of agreement has convinced astronomers that the fundamental laws of physics currently used in these models successfully capture much of how the universe has evolved. Perhaps this is one of science's most beautiful moments. When an idea is first written in mathematics, then tested through observation, and finally recreated through simulation. 3 different paths, leading to the same picture. From a symbolic perspective, this also recalls Carl Gustav Jung's view of human understanding. He believed that we cannot truly understand ourselves through reason alone, nor through emotion or memory in isolation. Only when many perspectives illuminate the same reality does a fuller picture gradually emerge. This is a philosophical reflection, rather than a comparison between astrophysical simulations and psychology. But it conveys a beautiful principle. Truth often reveals itself when many pieces come together. Perhaps that is why modern simulations are not meant to replace the real universe. They are better understood as a conversation with nature. Scientists propose a hypothesis. The computer allows the laws of physics to unfold. The results are then compared with what the real sky reveals. If they agree, confidence in the model grows. If they differ, the models are refined, and the process begins again, without end, without haste, like someone learning to listen rather than trying to impose an answer. There is something profoundly humble about the way science works. Its purpose is not to prove itself right, but to move ever closer to reality. As the night grows deeper, imagine that somewhere inside a supercomputer, nearly 14 billion years of cosmic history are unfolding in just a few minutes. Tiny fluctuations after the Big Bang slowly grow. Filaments emerge like delicate threads of light. Galaxy clusters gradually take shape where those filaments intersect. Cosmic voids quietly expand. Then, after billions of simulated years, the final image appears on the screen, astonishingly similar to the very sky we observe today. That is not a coincidence. It is the result of humanity's steadily growing understanding of the profound laws that govern the universe. Perhaps what makes this chapter so memorable is not the extraordinary power of supercomputers, but a simpler realization. Mathematics, physics, and human curiosity have together built a bridge between imagination and reality. Across that bridge, we do not merely observe the cosmic web as it exists today. We watch it grow, breathe, evolve, and quietly tell the nearly 14 billion-year story of its own existence. In the next chapter, our journey will travel even farther back, to a moment almost beyond imagination in the history of the universe. Together we will explore how quantum fluctuations, smaller than an atom itself, combined with cosmic inflation and gravity to become the very first seeds of the cosmic web. From nature's tiniest ripples, the greatest structure in the universe began its extraordinary journey, the deepest origins of the cosmic web. As we concluded the previous chapter, we watched supercomputers recreate nearly 14 billion years of cosmic evolution. Within those simulations, filaments gradually emerged, galaxy clusters grew, and cosmic voids quietly expanded, like an ancient forest, slowly maturing through time. Yet another, even deeper question naturally arises. If the cosmic web can be recreated from the laws of physics, where did those laws first begin to shape its story? What planted the original seeds that would eventually grow into the largest structure humanity has ever discovered? To answer that question, we must travel farther back than at any point in our journey so far. Not merely to the birth of the first galaxies, not merely to a universe only a few 100,000 years old, but to the very threshold of time itself. It is a realm where every familiar image loses its meaning. There are no stars, no planets, no atoms, not even galaxies. Only a universe unimaginably hot, incredibly dense, and so extraordinarily small that it lies beyond ordinary imagination. If the universe's entire 14 billion-year history were compressed into a single day, we would now be returning to the very first fractions of the very first second. Here we encounter one of the strangest ideas in modern physics: quantum fluctuations. At first, the phrase may sound mysterious, but imagine a perfectly calm lake. Even when the surface appears completely still, tiny ripples continue to shimmer across the water, created by movements so subtle they are almost impossible to notice. The quantum world behaves in a somewhat similar way. According to quantum mechanics, even what we call empty space is never perfectly still. At unimaginably small scales, energy constantly fluctuates. Particles and antiparticles can briefly appear before vanishing almost immediately. These fluctuations are so incredibly tiny that no microscope could ever observe them directly. They occur on scales far smaller than atoms, smaller than protons, smaller than neutrons, so small that nearly all of our everyday intuition simply ceases to apply. If the story ended there, no one would imagine that such minute fluctuations could have anything to do with galaxy clusters stretching across hundreds of millions of light years. Yet it is precisely here that one of cosmology's most extraordinary ideas appears: cosmic inflation. According to this theory, during the first fleeting moments after the Big Bang, the universe experienced an astonishingly rapid period of expansion. Not because objects were flying through space at incredible speed, but because space itself expanded at an unimaginable rate. Within an extraordinarily tiny fraction of a second, quantum fluctuations once smaller than atoms were stretched across cosmic scales. It is an astonishing thought. Something unimaginably small expanded through inflation until it became regions that were just slightly denser or slightly less dense than the surrounding universe. Imagine placing a tiny ink dot on the surface of an uninflated balloon. As the balloon expands millions upon millions of times, the ink dot expands with it. Its nature remains the same, only its scale changes. Quantum fluctuations underwent a remarkably similar transformation. They did not disappear, they were amplified. Those amplified fluctuations became tiny ripples in the density of matter throughout the young universe. Without those ripples, matter would have been distributed almost perfectly evenly. No region would have been slightly denser, no region slightly emptier. Gravity would have had nowhere to begin its work. No filaments, no galaxy clusters, no cosmic web, perhaps no stars, no planets, and no us. That realization moves many people deeply, because the entire cosmic web may ultimately trace its origin to differences so incredibly small, just slightly denser, just slightly thinner. Yet across billions of years, those tiny differences grew into every large-scale structure we observe today. From a symbolic perspective, this recalls an idea that resonates with Carl Gustav Jung's work. He suggested that seemingly small symbols or fragile experiences within our inner lives can gradually develop into patterns that shape an entire lifetime. This is not a comparison between quantum mechanics and psychology, but rather a philosophical reflection. Both encourage us to appreciate a beautiful possibility. The smallest beginnings can sometimes give rise to the greatest transformations. When the era of cosmic inflation came to an end, the universe continued expanding at a slower pace. Those tiny density fluctuations remained, preserved within the cosmic microwave background that we explored in earlier chapters. When scientists examine maps of the cosmic microwave background, they are not merely observing minute differences in temperature. They are seeing the fingerprints of the universe's earliest quantum fluctuations. In other words, that ancient light tells us more than the story of a universe only a few 100,000 years old. It carries memories from an even earlier epoch, like the growth rings inside an ancient tree revealing the history of an entire forest. The cosmic microwave background preserves the memory of the universe's dawn. Perhaps this is one of astronomy's most beautiful insights. The largest structures in existence did not begin as enormous objects. They began as unimaginably tiny vibrations. As we ended the previous section, we had traveled back to the earliest moments of time, where quantum fluctuations smaller than atoms themselves were stretched by cosmic inflation into delicate ripples in the density of the young universe. Yet at that stage, the cosmic web still did not exist. There were no filaments, no galaxy clusters, no immense cosmic voids. Only a universe that appeared almost perfectly uniform, with differences so subtle that they would have been nearly impossible to notice. The remarkable truth is that nature did not require large differences to create an immense universe. It required only two things: time and gravity. If we had to choose the most patient character in the entire story of the universe, it would almost certainly be gravity. Gravity does not work through sudden violence. It creates no instant transformations. It is quiet, steady, and never ceases. Imagine a gentle rain falling across a vast plain. At first, the ground appears almost perfectly level. Only a few shallow depressions lie slightly lower than the surrounding land. Rainwater does not instantly become lakes. Instead, every tiny drop naturally flows toward the lower places. As more water gathers there, those depressions become deeper, and as they deepen, they attract even more water. Gravity shaped the early universe in much the same way. Regions that were only the slightest bit denser than their surroundings gradually attracted more matter. More matter strengthened gravity. Stronger gravity attracted still more matter. The process repeated itself over millions, then billions, of years. There were no sudden leaps, no miracles, only the almost limitless patience of nature. Over time, those slightly denser regions continued to grow. Dark matter accumulated first. Hydrogen and helium gas followed. Small concentrations merged into larger structures. Then, slowly, filaments appeared. Galaxy clusters, great walls of galaxies. And between them, cosmic voids expanded ever farther. The entire cosmic web gradually emerged like a tapestry woven over nearly 14 billion years. What astonishes many people is not only the final result, but the extraordinary difference in scale. The beginning consisted of fluctuations smaller than atoms. The outcome became a network stretching across tens of billions of light years. Few examples in nature illustrate such an immense journey from origin to outcome. It brings to mind the image of a tiny acorn, small enough to rest in the palm of your hand. Yet given fertile soil, water, and enough time, it can become a mighty oak that lives for centuries. No one looking at the seed can immediately see the forest it will one day become, but that forest was already contained within the seed from the very beginning. The cosmic web possesses that same quiet beauty. Quantum fluctuations did not literally contain galaxies, but they carried the initial conditions that allowed the entire cosmic structure to emerge billions of years later. Perhaps this is one of the universe's most beautiful lessons. Not everything magnificent begins with something magnificent. Sometimes, the smallest differences become the origin of the greatest transformations. From a symbolic perspective, this also echoes an idea often explored by Carl Gustav Jung. He suggested that profound changes within the human psyche rarely begin with dramatic events. Sometimes they begin with a dream, a symbol, a simple question, or an ordinary experience that slowly transforms the way a person understands themselves. This is a philosophical reflection rather than a comparison between cosmology and psychology, but both invite us to appreciate a similar truth. Given enough time, even the smallest seeds can grow into something extraordinary. Today, when scientists compare maps of the cosmic microwave background with simulations such as the Millennium Simulation and Illustris TNG, alongside modern galaxy surveys, they discover an astonishingly consistent chain of events. Quantum fluctuations become tiny density ripples. Those ripples are amplified by gravity. Dark matter builds the framework. Gas flows along the filaments. Galaxies are born. Galaxy clusters continue to grow. The cosmic web emerges, not as isolated events, but as consecutive chapters of the same story. There is something deeply moving about that realization. The universe is not a collection of random miracles. It resembles a vast symphony. Every movement grows naturally from the one before it. Every note prepares the next. And that symphony has been playing continuously for nearly 14 billion years. Perhaps that is why, when we gaze into the night sky, we are not simply looking at stars. We are witnessing the outcome of a process that began with the smallest vibrations nature ever produced. Every galaxy carries the memory of the cosmic dawn. Every carbon atom within our bodies was forged inside stars that formed from gas gathered along the cosmic web. If we trace that story back far enough, every path leads to those first quantum fluctuations. Rather than making humanity seem insignificant, that realization creates an even deeper sense of belonging. Perhaps we are not standing outside this story. We are part of it. Not because humanity occupies the center of the universe, but because the very atoms that compose our bodies have traveled through the same 14 billion-year journey. As the night grows quieter, imagine the cosmic web as an immense ancient tree spreading its branches throughout space. The filaments become great limbs. Galaxy clusters resemble dense canopies of leaves. Cosmic voids form the open spaces between the branches. Yet beneath everything, hidden from sight, lies the tiny seed that began the entire story. At the dawn of time, perhaps the universe's deepest beauty does not lie in its enormous size, but in the way unimaginably small beginnings, guided only by time and the simple laws of nature, can grow into structures beyond imagination. Perhaps that is why the night sky brings so many people a sense of peace. Within that immense darkness, we discover that every form of growth requires time. Every beauty begins humbly, and every great journey starts with a single, almost imperceptible movement. In the next chapter, we will return to the cosmic web as it exists today and explore another fascinating truth. This immense network has never stopped changing. Galaxy clusters continue to grow. Filaments quietly transport matter. Cosmic voids steadily expand. And the universe itself continues evolving in a slow rhythm that has never once come to a halt. The cosmic web is still evolving. As we concluded the previous chapter, we traveled back to the universe's earliest moments, when quantum fluctuations smaller than atoms were stretched by cosmic inflation into the first ripples in the density of matter. From those almost imperceptible differences, gravity patiently built the filaments, galaxy clusters, and the vast cosmic web that we observe today. It is a story spanning nearly 14 billion years, but by now, another natural question arises. Has that story already ended? The answer is no. In fact, it is still unfolding, right now. At the very moment you are listening to these words, somewhere beyond the vastness of space, the cosmic web is still changing. There are no sounds, no endless explosions like those in science fiction films, only movements so slow that a human lifetime cannot perceive them. Yet if we could observe the universe across hundreds of millions, or even billions of years, we would watch the entire cosmic network continue its quiet evolution. It is a remarkable thought. We often imagine the universe as a frozen picture, the stars fixed in place, galaxies suspended motionless in space. Reality is very different. The universe resembles a river far more than a statue. Everything is moving, only according to a rhythm far too slow for human eyes to notice. Within the cosmic web, galaxy clusters continue to grow. This happens because the filaments have never stopped performing their quiet work. They resemble invisible rivers, not flowing with water, but with matter, dark matter, hydrogen gas, helium gas, small galaxies. All gradually drift along the filaments under the influence of gravity. Across billions of years, this steady flow continuously delivers matter toward the intersections of the cosmic web. At those intersections, galaxy clusters become increasingly massive. Imagine a galaxy cluster as an immense lake. The filaments are rivers flowing into it. As long as the rivers continue bringing water, the lake continues to grow. Galaxy clusters mature in much the same way, not by appearing from nothing, but through extraordinarily long periods of accumulation. Even the galaxies inside those clusters never remain completely still. They orbit the cluster's gravitational center, sometimes drawing closer together, sometimes colliding, sometimes merging into larger galaxies. Many of the largest galaxies observed today are the products of countless mergers spanning billions of years. Viewed in real time, almost nothing seems to happen, but compress billions of years into just a few minutes, and an entire galaxy cluster begins to resemble a vast flock of birds slowly changing formation. No movement is hurried, yet none ever truly stops. From a symbolic perspective, this also recalls Carl Gustav Jung's observation that human growth rarely occurs through dramatic leaps. More often, it results from countless small changes accumulating over time until we recognize them only when looking back. This is a philosophical reflection, rather than a comparison between cosmic evolution and psychology. But both evoke the same feeling. The deepest transformations often unfold in silence. If galaxy clusters continue to grow, the filaments have never stopped working either. Both modern simulations and recent observations reveal that matter continues flowing along the filaments, much like blood circulating through a living body. It is a beautiful image, because the cosmic web is more than a structure. It resembles a living system, not alive in the biological sense, but alive through constant motion. Gas between galaxies continues to drift. Dark matter quietly shapes gravity. New galaxies continue forming wherever enough cool gas remains. Clusters steadily attract additional matter. The entire cosmic picture has never truly stood still. Meanwhile, the cosmic voids continue evolving as well. At first, that may sound strange. How can emptiness itself evolve? In reality, a void is not an empty box. It still contains tiny amounts of gas, dark matter, and a handful of galaxies. Yet gravity from the surrounding denser regions gradually pulls matter away from the void. As a result, the void becomes even emptier and steadily larger. Imagine a broad valley. If water continually drains away into larger rivers, the valley floor gradually becomes drier. Cosmic voids undergo a remarkably similar process. They are not pushed outward. Instead, the surrounding regions continually draw matter away from them. The result is that the boundaries separating voids from filaments become increasingly distinct. That is one reason the cosmic web appears far more sharply defined today than it did during the universe's earliest ages. Across billions of years, gravity resembles an extraordinarily patient sculptor, continuously refining its masterpiece, sharpening the filaments, growing the clusters, expanding the voids, gradually bringing the entire network into clearer form. Perhaps the most astonishing fact is that every one of these processes is still happening today, not only in the distant past, not only in the distant future, but at this very moment. They simply unfold far too slowly for human intuition to perceive. Perhaps that is one of astronomy's greatest gifts. It teaches us a different rhythm of time, a rhythm measured not in days or years, but in hundreds of millions of years. Within that rhythm, the patience of the universe seems almost limitless. And once we recognize that the cosmic web continues evolving every moment, another fascinating question naturally emerges. Where, within this immense network, is our own Milky Way? Is the galaxy that contains our Sun also moving as part of these larger cosmic structures? And what invisible forces are quietly guiding the entire local group on its journey through the cosmic web? That will be the story we explore in the next chapter, as our journey carries us to the local group, the Laniakea supercluster, and the mystery known as the Great Attractor, one of the most intriguing gravitational regions ever discovered in the universe. As we concluded the previous chapter, we came to realize that the cosmic web is not a motionless picture hanging silently in space. It is more like an immense river that is still flowing, even though its current is so slow that no human lifetime could ever perceive it directly. Galaxy clusters continue to grow. Filaments quietly guide matter across the cosmos. Cosmic voids slowly expand. But if everything is in motion, a very natural question arises. Is our own Milky Way standing still within this vast network? The answer is no. In fact, at this very moment, as you listen to this story, in the quiet of the night, Earth is orbiting the Sunday. The Sun is orbiting the center of the Milky Way. The Milky Way itself is traveling alongside dozens of other galaxies, and that entire group is participating in even larger motions throughout the cosmic web. At first, this may seem difficult to imagine. In everyday life, we always have the feeling that we are standing still. The chair remains where it is. The room does not seem to move. Even the sky appears almost unchanged. Yet on the scale of the universe, there is no place that is truly at rest. Everything is part of a journey greater than itself. Our galaxy belongs to the local group. This is a collection of more than 100 known galaxies, the largest of which are the Milky Way, Andromeda, and the Triangulum Galaxy. The galaxies within the local group do not exist in isolation. They are bound together by gravity and travel through space as members of a shared gravitational system. Seen from a great distance, the local group resembles a small family drifting across the cosmic ocean. Each galaxy has its own story, its own orbit, its own history, yet together they belong to something larger. What makes this even more fascinating is that the local group is not the end of the story. It is only one part of a much larger structure known as Laniakea. The name comes from the Hawaiian language and is often interpreted as meaning immeasurable heaven or immense sky. It is a fitting name because Laniakea is not a single galaxy cluster. Rather, it is a vast supercluster containing tens of thousands of galaxies, along with numerous galaxy groups and clusters. When the concept of Laniakea was introduced, many people realized for the first time that the address of the Milky Way was far longer than they had ever imagined. We do not simply live within the solar system. We do not belong only to the Milky Way. We do not belong only to the local group. We are also part of Laniakea, and Laniakea itself is woven into the immense cosmic web. Perhaps the easiest way to picture this is by imagining a set of Russian nesting dolls. One structure sits inside a larger one. That larger structure rests inside another, even greater one. And so it continues, until, eventually, the entire cosmic web comes into view. What makes Laniakea remarkable is not merely its enormous size. It is the way its galaxies move. Rather than wandering randomly through space, many of them appear to flow together toward a common gravitational region. Much like rainwater running down distant mountainsides eventually gathers into the same river. And that brings us to one of the most mysterious names in modern astronomy, the Great Attractor. Even its name immediately captures the imagination. Yet the scientific reality is even more fascinating. The Great Attractor is not a single object. It is not a gigantic planet, nor is it a supermassive black hole consuming everything around it. Instead, it is the name given to a region of space containing an extraordinary concentration of mass. Its immense gravitational pull influences the motions of many nearby galaxies, including those within our own local group, drawing them toward that region. Astronomers are still working to understand the true nature of this remarkable structure, because part of it lies hidden behind the dense plane of the Milky Way. That obstruction makes direct observation extremely difficult. This reminds us of a remarkable truth. Even in the 21st century, even with the most powerful telescopes humanity has ever built, the universe still keeps many of its secrets. Not because nature is trying to hide them, but because our journey of discovery is still unfolding. From a symbolic perspective, this invites a gentle reflection on the work of Carl Gustav Jung. Jung suggested that human beings are often guided by inner forces of which they are only partially aware. We gradually recognize their influence through observation, reflection, and the lifelong process of self-discovery. This is, of course, a philosophical association rather than a scientific comparison with the Great Attractor. Even so, both remind us that unseen forces can shape the motion of an entire system long before we fully understand them. perhaps the greatest beauty of the cosmic web does not lie in its unimaginable distances, nor only in its billions of light-years. Perhaps it lies in its profound sense of connection. No galaxy is ever truly alone. No galaxy cluster is ever completely isolated. Every structure is connected to others. Every motion is influenced by motions on an even greater scale. If we could step back far enough, the entire observable universe would resemble an immense symphony. Each galaxy would be only a single note. No individual note can create the entire composition. Yet if even one note were missing, the symphony would never be quite complete. Perhaps that is why, when we look up at the night sky, we often experience a sense of peace that is difficult to describe. Not because we understand everything, but because we realize that we belong to a story far greater than ourselves, a small planet, orbiting an ordinary star, within an ordinary galaxy, belonging to the local group, part of Laniakea, and ultimately embraced by the cosmic web, which has continued its slow evolution for billions of years. That thought does not make humanity seem insignificant, quite the opposite. It reminds us that every individual life unfolds within a vast structure where every movement is connected to something larger. As the night grows quieter, try to imagine yourself traveling silently through that immense network along with Earth. There is no sound, no urgency, only the gentle rhythm of the universe continuing its timeless journey, just as it has for nearly 14 billion years. In the next chapter, we will leave behind the scale of the cosmic web itself and look more closely at individual galaxies. Together, we will explore how the environment in which a galaxy lives, whether inside a galaxy cluster, along a filament, or within a cosmic void, can shape its rate of star formation, its appearance, and ultimately its destiny throughout the long evolution of the universe. How environment shapes galaxies. As we concluded the previous chapter, we stepped back to view the cosmic web from an immense distance. We followed the Milky Way from the local group to Laniakea, expanding our perspective until we could see the entire cosmic network slowly evolving over nearly 14 billion years. Filaments continue to channel matter, galaxy clusters continue to grow, cosmic voids quietly expand. But once we understand that grand picture, another gentle question naturally arises. If the cosmic web is the home of galaxies, does the place where a galaxy lives influence the course of its own life? The answer is yes. In fact, many astronomers believe that a galaxy's environment is one of the most important factors shaping the way it evolves. The idea is much like a forest. A seed growing on a rocky mountainside will develop in one way. A seed growing beside a river will follow another path, and a seed planted in a rich, fertile valley will have an entirely different story. The seed itself is important, but so is the environment in which it grows. Galaxies throughout the cosmic web tell a remarkably similar story. Let us begin with the busiest neighborhoods of the universe. These are the galaxy clusters, enormous collections containing hundreds or even thousands of galaxies packed into a relatively small region of space. Viewed from afar, they appear vibrant and crowded. Yet there is an unexpected paradox. Many galaxies inside these clusters produce surprisingly few new stars. This puzzled astronomers for many years. Intuitively, one might expect that regions containing more galaxies would also create more stars, but the opposite often proves to be true. Many galaxies within large clusters are known as red galaxies, not because they shine with a brilliant red color, but because they no longer produce large numbers of young, blue stars. Most of their light now comes from older stellar populations. So what happened? The answer lies in the environment itself. The space between galaxies inside a cluster is far from empty. It is filled with extremely hot gas that can reach temperatures of tens of millions of degrees. As a galaxy races through this environment at tremendous speed, the pressure exerted by the hot gas gradually strips away the galaxy's own supply of cold gas. Astronomers call this process RAM pressure stripping. You might imagine someone running at full speed through a powerful rainstorm. The rushing wind and rain continuously press against their body. Over time, anything light enough is swept away. A galaxy experiences something remarkably similar. Its cold gas is the raw material needed to create new stars. As that gas is removed, star formation gradually slows. Eventually, it may come almost to a halt. Many galaxies within clusters therefore enter a much quieter stage of their lives. They continue to exist. They continue to rotate. They continue to orbit the center of their cluster, but very few new lights are kindled within them. That is not the only influence of such crowded environments. Within galaxy clusters, the distances separating galaxies are significantly smaller than in most other parts of the cosmic web. As a result, close encounters become much more common. Sometimes galaxies simply pass one another. Sometimes they interact gravitationally. Sometimes they merge into larger galaxies. At first, the word collision may suggest a catastrophic explosion, but reality is far more graceful, because the stars inside each galaxy are separated by enormous distances. Direct stellar collisions are exceedingly rare. Instead, it is the galaxies themselves that change. Their spiral arms may be stretched. Their gas becomes disturbed. The orbits of billions of stars slowly rearrange themselves. Over hundreds of millions of years, two separate galaxies can gradually merge into a single giant galaxy. At the true pace of the universe, the process appears almost motionless. But if time were accelerated, galaxies would resemble luminous clouds slowly drifting together until they became one. From a symbolic perspective, this brings to mind an idea often associated with Carl Gustav Jung. Jung believed that human beings do not develop in isolation. Relationships, communities, and the environments we inhabit all help shape our inner lives over time. This is simply a philosophical reflection rather than a scientific comparison between galaxies and human psychology. Even so, both remind us that our surroundings are not merely the backdrop of life. They become part of the path that shapes our growth. Interestingly, not every galaxy lives in such a crowded environment. On the opposite side of the cosmic web lie places that are almost the complete reverse. These are the cosmic voids. If a galaxy cluster resembles a bustling city, a void is more like a vast open plain, where the distance between neighboring homes is so great that you could travel for a very long time without meeting anyone. Within these immense regions, galaxies rarely collide. They are also far less affected by their surroundings. As a result, many galaxies inside cosmic voids retain their reservoirs of cold gas for much longer. That allows them to continue forming new stars over much longer periods than galaxies living inside dense clusters. It is a beautiful contrast. In the most crowded places, evolution can sometimes slow. In the quietest regions, new stars continue to be born. Perhaps nature is not judging one environment as better than another. Instead, it simply creates different evolutionary paths. And it is precisely this diversity that makes the cosmic web a far richer cosmic ecosystem. Yet between these two extremes, the crowded galaxy clusters and the tranquil cosmic voids, there is another quiet character that binds everything together. Those are the filaments. If galaxy clusters are like the ancient, bustling cities of the universe, and cosmic voids are like vast, quiet plains where almost no one passes by, then between these two contrasting worlds lies a network of extraordinary importance. These are the filaments, the immense strands of matter that have appeared again and again throughout our journey into the cosmic web. At first glance, a filament may seem to be nothing more than a bridge connecting galaxy clusters. In reality, its role is far greater. If we examine a modern simulation such as illustrious TNG, we discover that filaments are anything but motionless. Gas between galaxies continues its slow migration. Dark matter quietly maintains the gravitational framework. Small galaxies gradually drift toward larger clusters. Perhaps the easiest way to picture a filament is as an enormous river. It does not carry water, it carries matter, for billions of years. These gentle currents have silently nourished the regions through which they flow. That is why many astronomers describe filaments as the circulatory system of the cosmic web. Blood carries oxygen throughout the human body. Filaments carry gas and matter throughout the universe, sustaining galaxies. Without these steady flows, many galaxies would eventually exhaust the raw material needed to create new generations of stars. There is something profoundly peaceful about that idea. Even on the largest scales of the universe, the life of a structure depends upon its ability to remain connected. A galaxy is influenced not only by its own internal history, it is also shaped by where it lives, by the streams of matter flowing through it, by its neighboring galaxies, by the gravitational pull of the entire cosmic network. That makes the cosmic web resemble an ancient forest, more than a collection of separate trees. Within an old-growth forest, no tree grows entirely on its own. They share underground water, they respond to the same sunlight, they endure the same winds, they change with the passing seasons. The galaxies of the cosmic web are connected in much the same quiet way. Astronomers have also discovered that filaments do more than simply deliver matter. They can influence the very shapes of galaxies. This is a fascinating discovery. We often imagine that a galaxy's appearance depends only on the way it originally formed, but its environment also plays a significant role. If a galaxy continuously receives fresh gas from one particular direction along a filament, the distribution of its matter can gradually change. If numerous smaller galaxies arrive from the same direction over billions of years, the pattern of mergers will likewise evolve in distinctive ways. Over immense stretches of time, these seemingly insignificant influences can reshape an entire galaxy. It is an extraordinarily slow process. There is never a single moment when a galaxy suddenly changes its form. Everything happens so gradually that it is almost impossible to notice, like a river slowly polishing stones, not in a single day, but over thousands of years. From a symbolic perspective, this brings to mind an idea often found in the work of Carl Gustav Jung. Jung believed that human beings are shaped less by dramatic moments than by the quiet influence of long-term experiences. Repeated encounters, enduring relationships, and the environments in which we live gradually transform the way we understand ourselves and the world. This is simply a philosophical reflection rather than a scientific comparison between galactic evolution and psychology. Even so, both suggest a familiar truth. The quietest and most persistent influences often possess the greatest power to transform us. Perhaps that is the gentle lesson the cosmic web has been telling us all along. No two galaxies share exactly the same destiny, not because one is somehow better or worse than another, but because each grows within a different environment. Some spend their lives inside crowded galaxy clusters, others drift through the tranquil stillness of cosmic voids. Still others spend billions of years traveling along filaments, continually nourished by fresh streams of gas. No path is exactly like another, yet every one of them belongs to the same immense network. That realization invites us to see the cosmic web from an entirely different perspective. It is not merely a geometric structure. It is not simply a map of matter. It is a living system in which location, environment, and connection together shape the history of every galaxy. Perhaps that is why, when astronomers study a galaxy, they do not ask only how large it is. They also ask, where does it live? Which cluster does it belong to? Does it lie along a filament? How much gas is flowing into it? How many neighboring galaxies surround it? Because to truly understand a galaxy, it is often not enough to study the galaxy alone. We must also understand the world to which it belongs. There is something deeply comforting about that thought. It reminds us that every form of existence unfolds within relationships that are far greater than itself. Not only galaxies, not only galaxy clusters, but the entire cosmic web itself is part of the nearly 14 billion-year history of our evolving universe. As the night grows ever quieter, Imagine our own Milky Way as a ship drifting silently along an invisible river. That river is a filament. It carries gas, dark matter, and subtle gravitational influences too gentle for human senses to perceive. Over billions of years, those slow currents have helped shape our galaxy, nourish generations of stars, and ultimately create the very atoms that now exist within each of us. Perhaps the deepest beauty of this chapter lies in one remarkably simple idea. No galaxy truly grows alone. No galaxy is ever completely separated from its environment. Every journey of growth unfolds within a network of influences, connections, and time. The cosmic web continues to tell that story every day, not with words, not with sound, but through the slow and graceful motion of galaxies across the vastness of space. In the next chapter, our journey will carry us toward an even more elusive layer of the universe, one that exists between the galaxies themselves. Together, we will explore colossal shockwaves, cosmic magnetic fields, high-energy cosmic rays, and immense rivers of plasma heated to millions of degrees, discovering that the space between galaxies has never truly been empty. Even in the deepest silence of the cosmic web, nature continues its quiet work in ways that humanity is only beginning to understand. Gas, magnetic fields, and shockwaves. As we closed the previous chapter, we explored how a galaxy's surroundings quietly shape its destiny. A galaxy living inside a dense cluster follows a very different path from one drifting through the stillness of a cosmic void. We also discovered that filaments do far more than connect galaxy clusters. They transport gas and matter, sustaining the birth of new generations of stars. From this, we learned that the space between galaxies has never been truly empty. But if we look even deeper into that seemingly vacant expanse, we uncover something even more remarkable. Between the galaxies, there is not only gas and dark matter, there are also rivers of plasma, heated to millions of degrees, magnetic fields stretching across cosmic distances, and enormous shockwaves that continue to ripple silently throughout the cosmic web. At first, this may seem difficult to believe. In everyday life, when we imagine the vast space between galaxies, we often picture a perfect vacuum, a cold and silent darkness, a place where nothing exists. Yet nature tells a very different story. Although incredibly diffuse, that immense expanse has never been truly empty. It contains gas, it contains plasma, it contains magnetic fields, it contains particles carrying extraordinary amounts of energy, and every one of these ingredients participates in the ongoing evolution of the cosmic web. Let us begin with the most familiar component, the gas that fills intergalactic space. Compared with Earth's atmosphere, this gas is unimaginably thin. In many regions of space, there are only a few atoms within an entire cubic meter. If a person could somehow stand in such an environment, it would feel almost completely empty. And yet, on the scale of the universe, this incredibly diffuse gas forms an essential part of the cosmic web. Over billions of years, it does not remain motionless. It flows along the filaments. Gravity gradually draws it toward galaxy clusters. Eventually, it becomes the raw material from which new generations of stars are born. You might imagine the cosmic web as an immense forest. The galaxies are its ancient trees. The gas between them is like moisture suspended in the air. You do not always notice it, but without it, the forest could never continue to grow. Intergalactic gas serves a similarly quiet but essential role. What makes this gas especially remarkable is that most of it is not cold, quite the opposite. It is astonishingly hot, far hotter than anything we normally encounter on Earth. In many regions of the cosmic web, this plasma reaches temperatures ranging from hundreds of thousands to millions of Kelvin. At first, that may seem like a contradiction. How can a place that is almost completely empty be so incredibly hot? To understand this, we need to remember that in physics, temperature is not the same as the sensation of heat experienced by humans. Temperature measures the average kinetic energy of particles. Even if there are only a few particles present, if each one is moving at extremely high speeds, the environment can still have an extraordinarily high temperature. The form of matter that exists under these conditions is called plasma. It is often described as the fourth state of matter, alongside solids, liquids, and gases. In a plasma, electrons are no longer tightly bound to atomic nuclei. They move freely. This allows plasma to respond very strongly to magnetic fields and makes it a key ingredient in many astronomical phenomena. It is fascinating to realize that most of the visible matter in today's universe does not exist as rock or water. It exists as plasma. The stars are made of plasma. The sun is plasma. And a significant fraction of the gas between galaxies is plasma as well. In other words, the most common state of matter in the universe is not the one most familiar to human beings. This reminds us that the universe was not designed to match our intuition. Instead, we are the ones who must learn to understand the way nature truly works. From a symbolic perspective, this recalls an idea often found in the writings of Carl Gustav Jung. He frequently suggested that the inner reality of the human mind is far more expansive than what consciousness can immediately grasp. There are deeper layers that may not be visible on the surface, yet they quietly influence the entire psychological structure. This is simply a philosophical reflection rather than a scientific comparison between plasma, astrophysics, and psychology. Nevertheless, both invite us to appreciate that what is difficult to see may ultimately prove to be the most fundamental. But gas and plasma are not the only hidden ingredients. Between the galaxies lies another elusive component: cosmic magnetic fields. If you have ever watched a compass needle point toward magnetic north, you have already witnessed the influence of Earth's magnetic field. But magnetic fields do not exist only around our planet. They are found within the sunday, throughout galaxies, and even stretching along the filaments of the cosmic web itself. These magnetic fields are far weaker than those we encounter in everyday life, yet they extend across astonishingly vast distances. Over millions and billions of years, they influence the motion of plasma, electrically charged particles, and countless other physical processes. You might imagine magnetic fields as invisible currents moving through the air. You cannot see them directly, but the movement of leaves reveals that they are there. The plasma within the cosmic web behaves in much the same way. Its motion allows astronomers to trace the enormous magnetic fields woven throughout the universe. Perhaps the most beautiful lesson here is one we have encountered before. Nature reminds us once again that invisible does not mean non-existent. Some forces cannot be seen with our eyes, yet they quietly help shape the universe itself. And as streams of plasma continue flowing along the filaments, they sometimes produce even more dramatic phenomena, shock waves and particles, carrying enormous amounts of energy that can travel across millions of light years. That is the journey we will begin in the next section, as we explore the quiet yet energetic heartbeat of the cosmic web. As we concluded the previous chapter, we discovered that the space between galaxies is far from being a perfect vacuum. It contains incredibly diffuse gas, plasma heated to millions of degrees, and magnetic fields stretching across distances that challenge the human imagination. Yet the story of the cosmic web reaches even deeper. Even within that profound stillness, the universe continues to generate invisible pulses, immense waves, and highly energetic particles that endlessly traverse the vastness of intergalactic space. One of the most remarkable of these phenomena is the shock wave. When we hear the words shock wave, we often imagine an enormous explosion. That is not entirely wrong. But within the cosmic web, shock waves are not always created by explosions. Sometimes they arise when colossal streams of gas collide, when two galaxy clusters slowly merge, or when matter flowing along filaments continually falls into regions of stronger gravity. Imagine two mighty rivers coming together. Their waters do not blend peacefully all at once. Where they meet, swirling currents, turbulent eddies, and expanding waves naturally emerge. Shock waves within the cosmic web possess a similar beauty. The difference is that they travel not through water, but through the intensely hot plasma, filling the space between galaxies. These waves can extend across millions of light years. Measured against the speed of light, they propagate relatively slowly, yet they still travel far faster than sound moves through the familiar environments of Earth. What makes these shock waves especially important is that they do far more than simply heat the gas. They also transfer energy to electrically charged particles. And here, another remarkable character enters our story: cosmic rays. At first glance, the name may suggest beams of light. In reality, most cosmic rays are not light at all. They are extremely energetic particles, primarily protons and atomic nuclei, traveling at speeds approaching the speed of light. Some are born in supernova explosions. Others may be accelerated near supermassive black holes. Still others gain additional energy while passing through the enormous shockwaves of the cosmic web. Their journeys can last millions, even billions, of years. Throughout that time, they continually interact with cosmic magnetic fields. As a result, the paths of cosmic rays are rarely straight. They bend, they curve, they change direction, like tiny leaves carried by invisible winds across countless skies. If we could somehow see every one of these particles moving through space, the cosmic web might resemble an ancient forest filled with countless fireflies drifting gently among enormous branches. Not noisy, not dazzling, but quietly alive. Astronomers are fascinated by cosmic rays not merely because of their extraordinary energy. They treasure them because these particles carry information from some of the most extreme environments in the universe. Each one is like a messenger. It has traveled from unimaginably distant places. It carries subtle clues about the environment in which it was born. By studying these particles, scientists can learn about regions that ordinary telescopes cannot easily observe. Once again, this reminds us that science does not always advance by looking directly at something. Often, it progresses by learning to read the traces that nature leaves behind. From a symbolic perspective, this recalls another theme frequently explored by Carl Gustav Jung. He suggested that the deepest contents of the psyche rarely present themselves directly to consciousness. Instead, they often emerge through symbols, emotions, and subtle signs. This is simply a philosophical reflection, rather than a scientific comparison between cosmic rays and psychology. Even so, both encourage us to recognize that understanding often begins with learning to notice the smallest of clues. If we could step back and view the entire cosmic web from an immense distance, one realization would become unmistakable. Nowhere is completely still. Gas continues to flow. Plasma continues to move. Magnetic fields quietly endure. Shock waves continue to spread. Cosmic rays continue crossing the darkness. All of this unfolds in absolute silence. At first, that seems like a contradiction. How can something be constantly moving, yet perfectly quiet? Perhaps because the silence of the universe is not the absence of activity. It is the presence of motions that are simply too slow, too vast, or too subtle for human senses to perceive. If we could compress hundreds of millions of years into only a few minutes, the seemingly empty space between galaxies would no longer appear as a motionless darkness. It would resemble a vast ocean. When those plasma streams begin to flow, shock waves ripple outward. The filaments glow with the ceaseless movement of matter. The cosmic web reveals itself as though it were a living organism, breathing in an almost imperceptibly slow rhythm. Perhaps this is one of the greatest changes that modern astronomy has brought to our understanding of the universe. Space is no longer simply empty. It is a rich and dynamic environment, where matter, energy, and the laws of physics coexist in an exquisitely delicate balance. As the night outside your window grows deeper, imagine immense rivers of hot plasma quietly drifting along distant filaments between faraway galaxies. Invisible magnetic fields gently embrace them, Vast shock waves continue spreading through space after the mergers of galaxy clusters, and countless cosmic rays carry on journeys lasting millions of light years, bearing stories that light alone could never fully tell. Perhaps the true beauty of this chapter does not lie in its physical terminology. It lies in a much gentler realization. Stillness is not the same as emptiness. Silence is not the same as an ending. Even within the quietest regions of the cosmic web, nature is constantly at work, never hurried, never seeking attention, simply continuing its grand symphony that has been unfolding for nearly 14 billion years. In our next chapter, we will follow one of the oldest mysteries in modern astronomy: the search for the universe's missing, ordinary matter. Through quasars, the Lyman alpha forest, X-rays, and fast radio bursts, we will discover how incredibly subtle signals ultimately led humanity to find the matter that seemed to have vanished from the cosmic maps for decades. Searching for the missing matter, as we closed the previous chapter, we ventured into the seemingly empty space between galaxies and discovered that it has never truly been silent. Rivers of plasma heated to millions of degrees continue their quiet journey. Invisible magnetic fields stretch across the cosmic web. Shock waves and cosmic rays silently transport energy throughout intergalactic space. Yet, just as astronomers began to understand this environment more clearly, another puzzle emerged. It appeared that the universe was missing some of its own matter. At first, that sounds rather strange. How can scientists know that something is missing? If it has never been seen, if it has never been found, how can anyone know it was ever there? This question lies at the heart of one of modern astronomy's most fascinating mysteries. Scientists call it the missing baryonic matter problem. One important point should be made immediately. The missing matter discussed here is not dark matter. These are two completely different concepts. Dark matter is a mysterious form of matter whose true nature remains unknown. Missing baryonic matter, by contrast, is perfectly ordinary matter, the same kind that forms stars, planets, oceans, trees, and even our own bodies. Cosmological models, together with observations of the early universe, indicate that a certain amount of ordinary matter must exist. Yet, when astronomers add together all the visible matter contained within stars, galaxies, and gas clouds, they find that a significant fraction is still unaccounted for. Imagine taking inventory of a vast library. According to the records, there should be 1 million books, but after counting every shelf, only 700,000 can be found. Where are the remaining 300,000? No one knows. For decades, this mystery inspired astronomers to keep searching. Some proposed that the missing matter was hidden inside galaxies too faint to detect. Others suggested that it existed as extraordinarily diffuse gas. Still others believed that we simply had not been observing at the correct wavelengths. Gradually, more and more evidence began pointing toward the same conclusion. Most of the missing ordinary matter was not hiding inside galaxies. It was hiding between them, threaded throughout the filaments of the cosmic web, existing as extremely hot, extremely diffuse gas. But how do you observe gas that is both incredibly thin and almost completely invisible? That is when astronomers came up with a remarkably elegant idea. Instead of trying to observe the gas itself, they would observe the light passing through it. Once again, light became the universe's most faithful storyteller. In this journey, another remarkable character appears: the quasar. We encountered quasars in earlier chapters. They are extraordinarily luminous regions surrounding supermassive black holes at the centers of distant galaxies. A single quasar can outshine an entire galaxy containing hundreds of billions of stars. In that sense, quasars are like gigantic cosmic lighthouses, standing near the edge of the observable universe. As the light from a quasar travels toward Earth, it must pass through countless clouds of intergalactic gas within the cosmic web. Each cloud leaves behind an incredibly subtle signature in the quasar's spectrum, At first glance, those signatures are almost invisible, yet with modern telescopes, they become invaluable clues. Imagine sunlight shining through multiple panes of colored glass. You never actually see each individual pane, but the color of the light changes. From those changes, you can infer how many layers of glass the light has passed through. Quasar light tells its story in much the same way. Every cloud of intergalactic gas absorbs tiny amounts of light at specific wavelengths. From these absorption patterns, astronomers can determine where the gas exists, whether it is dense or diffuse, hot or cool, nearby or distant. From a symbolic perspective, this recalls an idea frequently explored by Carl Gustav Jung. He believed that many of the most important aspects of inner life cannot be observed directly, but instead reveal themselves through subtle traces found in dreams, symbols, and emotions. This is simply a philosophical reflection rather than a scientific comparison between spectroscopy and psychology. Nevertheless, both remind us that the invisible is often recognized only through the delicate marks it leaves behind. These observations eventually revealed one of astronomy's most celebrated discoveries, the Lyman Alpha Forest. The name itself sounds almost poetic, and in many ways, it truly resembles a forest. When astronomers examine the spectrum of a distant quasar, they do not see one continuous beam of light. Instead, they find hundreds of tiny absorption lines crowded together. Those countless lines resemble slender tree trunks stretching across a distant horizon. Each one represents a cloud of hydrogen gas through which the quasar's light has traveled during its journey across billions of light-years. Not one cloud, not 10, but sometimes hundreds or even thousands. That is why the spectrum resembles a dense forest. Hence the name, the Lyman Alpha Forest. The remarkable thing is that every one of those trees tells part of the story of the cosmic web. By combining countless observations, astronomers gradually realized that the missing ordinary matter had never truly disappeared. It had simply been spread so thinly that it became extraordinarily difficult to detect. It exists throughout the filaments, quietly connecting galaxies, quietly nourishing structures that will continue evolving for billions of years to come. Perhaps this is one of science's most beautiful lessons. Sometimes what we believe has been lost has never vanished at all. It has simply been present in a far subtler form. As we concluded the previous section, we followed the light from quasars at the edge of the universe into the forest known as the Lyman Alpha Forest. Each tiny absorption line became a silent footprint leading astronomers toward the incredibly diffuse gas stretching between galaxies. Yet the search for the universe's missing matter did not end there. Most of the gas within the cosmic web is not only extraordinarily thin, it is also so hot that it emits almost no visible light. To observe it, humanity had to learn to see through entirely different eyes. One of those eyes is X-ray astronomy. In everyday life, X-rays are used to image our bones and reveal structures hidden beneath the skin. In astronomy, they serve a remarkably similar purpose. They allow us to peer into environments so hot that ordinary visible light reveals almost nothing. When intergalactic gas reaches temperatures of millions of Kelvin, it begins emitting faint X-ray radiation. Not bright, not spectacular, but just strong enough to be detected by specialized space telescopes. Through these incredibly delicate signals, astronomers gradually discovered enormous rivers of hot plasma stretching between galaxy clusters. They follow the filaments of the cosmic web, quietly linking galaxies together. Imagine a thin layer of mist covering an entire valley. In daylight, it is almost invisible, but when sunlight strikes it at just the right angle, the entire veil suddenly appears. X-rays perform much the same task. They do not create the gas. They simply reveal gas that has been there all along. Yet even X-rays could not solve the entire mystery. Some regions of gas are so diffuse that their X-ray emission is almost undetectable. Once again, astronomers needed another messenger, a mysterious signal discovered only in recent years. The fast radio burst, or FRB. An FRB is an extraordinarily brief pulse of radio waves, lasting only a few thousandths of a second. During that fleeting instant, it can release as much energy as the sun emits over many days. The precise origin of every FRB remains under investigation, although growing evidence suggests that many are produced by highly magnetized neutron stars known as magnetars. What makes FRBs so valuable is not merely their mystery, it is their journey. Every radio pulse travels across billions of light-years before finally reaching Earth. Throughout that immense voyage, its signal is influenced by free electrons scattered throughout intergalactic gas. Those electrons cause different radio frequencies to arrive at Earth with tiny delays. This phenomenon is known as dispersion. It may sound highly technical, yet the underlying idea is surprisingly intuitive. Imagine standing on the far side of a dense forest. Someone rings a bell. The sound still reaches you, but the way it changes along the journey tells you something about the forest through which it traveled. An FRB behaves in much the same way. It carries not only the story of where it originated, it also carries the story of every region of space through which it has passed. That is why every fast radio burst, FRB, acts like a natural probe passing through the cosmic web. By analyzing the tiny delays in its signal, astronomers can estimate the number of free electrons scattered between galaxies. From those measurements, they can infer how much gas is actually present throughout intergalactic space. From a symbolic perspective, this recalls a familiar theme in the thought of Carl Gustav Jung. He suggested that many things are best understood not simply by examining where an experience begins or where it ends, but by carefully observing the path it takes. This is merely a philosophical reflection rather than a scientific comparison between radio signals and psychology. Nevertheless, both remind us that the journey itself often contains as much information as the destination. Perhaps the most beautiful part of this story emerges when all these methods are brought together. The light from quasars, the Lyman alpha forest, X-ray observations, fast radio bursts. Each technique reveals only one piece of the puzzle, but together, they begin to complete the picture. Astronomers now possess growing evidence that most of the universe's missing baryonic matter was never truly missing at all. It has been there all along, distributed as extraordinarily diffuse, hot gas, stretching between galaxies throughout the filaments of the cosmic web. It is much like a symphony whose deepest notes have never disappeared. They were simply too quiet to hear if we listened in only one way. Perhaps this is one of the deepest lessons that science has to offer. Not every mystery is solved through a single dramatic discovery. Often, the truth gradually emerges as countless small pieces are assembled side by side. A beam of light, an absorption line, an X-ray photon, a radio pulse lasting only a few thousandths of a second. Each one is tiny, yet together, they tell the story of an entire universe. As the night grows ever quieter, imagine a distant quasar still shining somewhere across the cosmos. A fast radio burst flashes into existence, then disappears almost instantly. Its light and radio waves quietly travel through the delicate streams of gas stretching between galaxies. After billions of years, an unimaginably small fraction of those signals finally reaches telescopes on Earth, carrying answers that humanity has patiently sought for decades. Perhaps what makes this story truly remarkable is not simply that we found most of the missing matter, it is how we found it. Not through haste, not through premature conclusions, but by patiently listening to the faintest whispers of the universe. And perhaps that spirit has guided our entire journey together. The universe always holds its answers. Sometimes, it simply speaks very softly. In our next chapter, we will widen our perspective once more to explore an even greater role played by the cosmic web. We will discover why this immense network is not merely the structure that connects galaxies, but also the largest natural laboratory in the universe, where scientists investigate dark matter, dark energy, neutrinos, gravity, and the most fundamental models describing how the cosmos itself works. The cosmic web as a giant laboratory. As we concluded the previous chapter, we followed the light of distant quasars, listened to the fleeting whispers of fast radio bursts, and discovered how astronomers traced extraordinarily subtle clues to recover most of the ordinary matter once believed to be missing from the universe. In doing so, we learned that the cosmic web is far more than a network connecting galaxies. It resembles a vast book, where every stream of gas, every filament, and every galaxy cluster preserves part of the universe's story. Yet as scientists came to understand this immense network more deeply, they recognized something even more astonishing. The cosmic web is not merely an object to observe, it is the greatest natural laboratory humanity has ever known. When we hear the words laboratory, we usually picture a brightly lit room, microscopes, glassware, precision instruments. It is a place where people deliberately create controlled conditions to test hypotheses. But the universe is different. No one can build a laboratory spanning billions of light years. No one can create a galaxy from scratch. No one can repeat the Big Bang. Nature accomplished all of those things long before humanity ever appeared. The only thing we can do is learn how to observe. In a beautiful sense, the cosmic web is the laboratory that nature has quietly operated for nearly 14 billion years. Within this laboratory, every law of physics is tested on the largest scale imaginable. Gravity, the expansion of space, the formation of galaxies, the motion of matter, all of it unfolds there, not for minutes, but for billions of years. Perhaps what excites cosmologists most is that the cosmic web allows them to test theories that would be almost impossible to examine on Earth. One of the greatest examples is dark matter. To this day, we still do not know what dark matter is actually made of. It emits no light, absorbs no light, reflects no light, yet its fingerprints appear everywhere throughout the cosmic web. Dark matter formed the invisible framework upon which the filaments themselves emerged. If the visible galaxies resemble the lights of a city at night, then dark matter is like the land upon which the city was built. From a great distance, you cannot see the ground itself, yet the entire shape of the city depends upon it. That is why the cosmic web has become one of the best places to test models of dark matter. If a hypothesis is correct, computer simulations should produce a network closely resembling the one observed through telescopes. If the hypothesis is wrong, the simulated cosmic web will look different. Every filament, every galaxy cluster, every cosmic void becomes another line of data written by nature itself, without speaking, simply by existing. Dark matter is not the only mystery explored through this cosmic laboratory. The cosmic web also provides an extraordinary testing ground for gravity. At first, that may sound familiar. Since the time of Isaac Newton, gravity has been recognized as one of nature's fundamental forces. Yet when we extend our view across the entire universe, the story becomes far more complicated. Does gravity always behave in exactly the same way across every scale? Or might it reveal subtle differences over distances spanning billions of light years? This is precisely why the cosmic web is so valuable. If gravity behaved even slightly differently, the shapes of filaments, the growth rates of galaxy clusters, and the sizes of cosmic voids would all change accordingly. In other words, simply by studying the cosmic web, scientists can test whether our familiar laws of physics remain valid on the largest scales imaginable. Imagine watching ripples spreading across the surface of a lake. When a stone falls into the water, the waves expand according to well-defined rules. If those rules changed, the entire pattern on the lake would change as well. The cosmic web tells its story in much the same way. It reflects the very laws that created it. From a symbolic perspective, this recalls a theme often found in the work of Carl Gustav Jung. He suggested that to understand any complex system, it is sometimes necessary to look beyond its individual parts and instead observe the relationships that bind the whole together. This is simply a philosophical reflection rather than a comparison between psychology and cosmology. Even so, both remind us that the larger pattern often reveals more than isolated pieces ever could. Alongside dark matter and gravity, another invisible presence quietly shapes the future of the universe: dark energy. If dark matter acts as the force that gathers the cosmic web together, dark energy steadily stretches space itself. These two processes coexist, they interact, and together they produce the universe we observe today. By studying the cosmic web, astronomers can measure how large-scale structures have grown throughout cosmic history. From that growth, they can estimate how strongly dark energy has influenced the evolution of the universe. Perhaps this is what makes the cosmic web truly unique. It does not merely tell us about the past, it also allows humanity to glimpse the future. The network we observe today is the product of billions of years of evolution. At the same time, it offers clues about what may unfold over billions of years yet to come. Yet dark matter, gravity, and dark energy are still not the whole story. In the next section, we will journey even deeper into this immense natural laboratory to discover how the cosmic web also allows scientists to test bold theories of alternative gravity, investigate the nearly massless neutrino, and continually compare new observations against the standard model of cosmology, bringing us ever closer to understanding the profound laws that quietly govern the entire universe. When we concluded the previous chapter, we discovered that the cosmic web is not only the largest structure in the universe, but also a vast natural laboratory where scientists can test the most fundamental laws of nature. From the distribution of filaments and the growth of galaxy clusters to enormous voids spanning hundreds of millions of light years, every detail contains valuable clues about how the universe works. Yet the remarkable journey does not end there. Beyond dark matter, gravity, and dark energy, the cosmic web also allows humanity to explore even deeper mysteries, questions that lie at the boundary between what we know and what we are only beginning to discover. One of those mysteries is the neutrino. If there is one fundamental particle that truly deserves to be called the ghost of the universe, the neutrino is perhaps the strongest candidate. At this very moment, trillions of neutrinos are passing through your body every second. They come from the sunday, from distant stars, from exploding supernovae, and from countless other physical processes throughout the cosmos. Yet they leave almost no trace. Neutrinos interact with matter so weakly that a single particle can pass straight through the entire Earth without colliding with a single atom. That extraordinary behavior has made them one of the greatest challenges in modern physics. At first glance, neutrinos may seem completely unrelated to the cosmic web. In reality, the connection is surprisingly important. Although each neutrino has an incredibly tiny mass, the universe contains such an enormous number of them that, collectively, they influence the formation of large-scale cosmic structures. If neutrinos were even slightly more massive, they would slow the growth of galaxy clusters and subtly alter the shape of the cosmic web itself. That is why, as astronomers map the cosmic network with ever-increasing precision, they are also placing increasingly strict limits on the mass of neutrinos. At first, this may sound almost unbelievable. How can a structure stretching across billions of light-years help us understand a particle that possesses almost no mass at all? Yet this is one of the great beauties of science. Sometimes, the smallest things and the largest things are connected by the very same laws of nature. Neutrinos are not the only mystery. The cosmic web also allows scientists to investigate another bold question. What if the theory of gravity we currently use is not yet the complete picture? For many decades, Albert Einstein's theory has successfully explained an astonishing range of phenomena throughout the universe. Even so, some researchers continue to ask whether gravity might behave slightly differently on scales spanning billions of light-years. Ideas of this kind are collectively known as alternative theories of gravity. These models are not proposed because our current theories have failed. They exist because science remains open to testing new possibilities. If a new theory predicts a different cosmic web, or galaxy clusters that evolve differently, astronomers simply compare those predictions with observations. If the theory disagrees with nature, it is rejected. If it agrees more closely, it deserves further investigation. In that sense, the cosmic web serves as an exceptionally fair judge. It favors no hypothesis. It simply reflects, with complete honesty, what nature has actually done. From a symbolic perspective, this recalls the spirit of inquiry found in the work of Carl Gustav Jung. He repeatedly emphasized that a hypothesis gains real value only when it is confronted with experience and observation, rather than resting solely upon the researcher's expectations. This is simply a philosophical reflection rather than a comparison between cosmology and psychology. Nevertheless, both share the same humility before reality, a willingness to revise one's understanding whenever new evidence appears. Ultimately, all of these investigations return to one common foundation: the standard model of cosmology. This is not a closed book, nor is it a collection of immutable truths. It is simply the best model humanity currently possesses for explaining the evolution of the universe, supported by numerous independent observations. The cosmic microwave background, the expansion of the universe, the distribution of galaxies, the cosmic web, gravitational lensing, quasars, fast radio bursts. Each contributes another independent test of whether the model continues to describe reality accurately. Perhaps one of science's greatest strengths is that it never seeks to defend a theory at any cost. Quite the opposite. Every new observation is another opportunity to challenge the model. If it survives, our confidence grows stronger. If it does not, we learn something new. Perhaps that is why the cosmic web is more than an astronomical structure. It is a place where humanity has learned to enter into a dialogue with nature, not by imposing answers, not by rushing toward conclusions, but by observing patiently, questioning patiently, and listening patiently. As the night grows ever quieter, imagine the entire cosmic web as a laboratory without walls. The filaments become pathways through which matter flows. Galaxy clusters become meeting places where gravity reveals its strength. Vast cosmic voids become natural arenas for testing the expansion of the universe. Meanwhile, light from distant galaxies, neutrinos silently crossing space, and faint signals arriving from every corner of the cosmos become the data that nature itself has been preparing for billions of years. Perhaps what makes this chapter memorable is not the number of scientific ideas it introduces. It is the way it changes how we see the universe itself. The night sky is no longer simply something to admire. It is a laboratory in constant operation. Every galaxy is an experiment billions of years in duration. Every filament is an equation written in matter. Every cosmic void is a question that nature continues to ask with extraordinary patience. And humanity, guided by nothing more than simple curiosity, is slowly learning how to read those immense lines of cosmic writing. In the next chapter, we will return to the galaxies themselves to explore another remarkable journey. Galaxies do not remain in one place throughout their lifetimes. They travel through sheets, filaments, clusters, and voids, continually experiencing new environments. Those journeys, unfolding across billions of years, help determine each galaxy's shape, its rate of star formation, and ultimately, its destiny within the cosmic web, the evolution of galaxies. As we concluded the previous chapter, we explored the cosmic web as nature's greatest laboratory. Within this immense network, every filament, every galaxy cluster, and every cosmic void became a natural experiment lasting billions of years, helping humanity better understand dark matter, dark energy, gravity, and the fundamental laws governing the universe. But if the cosmic web is the grand stage, then galaxies are its travelers, wanderers, that are never truly at rest. They are not born only to remain forever in one place. They move, encounter new environments, and gradually write the story of their own evolution. Perhaps this is one of the most fascinating ideas in astronomy. When we look up at the night sky, everything appears still. The constellations remain in place. The Milky Way stretches across the heavens like a silver ribbon. Distant galaxies seem suspended in the darkness, but that impression is true only on the timescale of a human lifetime. If time could be accelerated by hundreds of millions, or even billions of years, the entire picture would change. Galaxies would reveal themselves as travelers, quietly, patiently, never ceasing to move. Within the cosmic web, a galaxy does far more than rotate around its own center. It does more than travel with the galaxy group to which it belongs. It also participates in immense journeys across the largest structures of the universe. Over a lifetime lasting billions of years, a galaxy may experience many different environments. At times, it resides within sheets, broad, thin layers of matter spread across space. At other times, it drifts along the great filaments. Eventually, it may enter the crowded environment of a galaxy cluster. While some galaxies spend much of their existence within the quiet isolation of cosmic voids, each environment tells a different story. That is why modern astronomers no longer ask only, "How large is this galaxy?" They also ask, "Where has it traveled? What kind of environment does it inhabit? How has its surroundings shaped its evolution?" Perhaps those questions are just as beautiful as the answers, because they remind us that no galaxy matures entirely on its own. Let us begin with the sheets. These are broad regions whose density is lower than that of filaments, yet still greater than that of cosmic voids. If we imagine the cosmic web as a giant spider's web, the sheets resemble delicate membranes stretching between its larger strands. Here, galaxies have room to grow, without experiencing the intense gravitational influences found inside crowded galaxy clusters. Many galaxies begin their evolutionary journeys in environments like these. Slowly, they accumulate gas. They formed the first generations of stars. Slowly, they grew over billions of years. Yet that journey rarely comes to an end. Under the influence of gravity, many galaxies begin drifting along the filaments. These are like the great highways of the universe. There are no road signs, no rest stops, only streams of matter and gravity quietly guiding the way. As a galaxy travels along a filament, it does far more than change its location. It continues to draw in fresh gas from its surroundings. That gas becomes the raw material from which new stars are born. You might picture this as a river nourishing every landscape through which it flows. As long as the water continues, life continues as well. Filaments play a similar role for countless galaxies. They carry hydrogen, helium, and many other ingredients, quietly replenishing galaxies throughout their long journeys. This helps explain why many galaxies embedded within filaments continue forming new stars for extraordinarily long periods of time. From a symbolic perspective, this echoes an idea often found in the work of Carl Gustav Jung. He suggested that human growth never unfolds in complete isolation, but is always shaped by the continuous flow of experience, relationships, and the environments we inhabit. This is simply a philosophical reflection rather than a comparison between galaxies and psychology. Nevertheless, both invite us to consider the beautiful possibility that the paths we travel gradually become part of who we are. Yet, for many galaxies, the journey still is not over. Gravity continues pulling them toward increasingly crowded regions, toward the great galaxy clusters. If filaments resemble rivers, clusters are like vast oceans, where countless rivers finally converge. As a galaxy enters a cluster, its surroundings change dramatically. The gas between galaxies becomes hotter. The density of galaxies becomes much greater. Gravitational interactions occur far more frequently. The conditions that once shaped life along a filament no longer remain the same. The galaxy enters a new chapter of its existence. Some gradually lose their reservoirs of cold gas as they interact with the surrounding environment. Some experience close encounters with neighboring galaxies. Some merge into larger systems. Others slowly stop forming new stars and become older in the astronomical sense, not because time passes more quickly, but because the environment has changed. Curiously, if we looked only at the galaxy as it appears today, we would find it difficult to imagine everything it has experienced. Yet by reading the history preserved in its shape, its remaining gas, and its stellar populations, astronomers can reconstruct a journey stretching across billions of years. Much as an archaeologist can rebuild the story of an ancient civilization from only a handful of pottery fragments, a galaxy also carries the traces of its own past. Perhaps that is what makes every galaxy so remarkable. It is not merely a collection of billions of stars. It is a story, a journey, a memory written in light. When we concluded the previous section, we followed an imaginary galaxy on a voyage lasting billions of years across the cosmic web, from the peaceful environment of the sheets, along matter-rich filaments, and eventually into crowded galaxy clusters. We discovered that the life of a galaxy is not a motionless picture. It is more like an extraordinarily long sea voyage, where every region of space leaves its own imprint. Yet perhaps the greatest wonder still lies ahead. The environments through which a galaxy travels do not simply change its location. They gradually reshape its appearance, its rhythm of life, and ultimately, its future. If we examine the images captured by modern telescopes, we find galaxies displaying an astonishing variety of forms. Some are graceful spirals, like our own Milky Way. Some are smooth elliptical galaxies. Others appear distorted, as though they have endured a dramatic event. For many years, astronomers believed that these shapes were determined primarily at the moment a galaxy first formed. Today, we understand that the story is far more complex. A galaxy is shaped not only by its beginning, it is also shaped by every stage of the journey that follows. Imagine two stones broken from the same mountain. One remains quietly in a sheltered valley. The other is carried downstream until it reaches the sea. After millions of years, they will look completely different. Not because they began differently, but because they traveled different paths. Galaxies tell much the same story. Galaxies that spend most of their lives within cosmic voids experience a very different rhythm. There, space is vast. Galaxies lie far apart. Collisions are rare. Cold gas can remain intact for billions of years. As a result, many of these galaxies continue forming new generations of stars over immense spans of time. Young blue stars continue to shine. Their spiral arms retain their graceful structure. In many ways, galaxies in voids resemble ancient forests that have experienced very little human disturbance. They evolve slowly, steadily, according to their own quiet rhythm. Galaxies that eventually enter galaxy clusters follow an entirely different path. There, the density of galaxies is far greater. Gravitational encounters become much more common. The hot gas between galaxies continually influences the cold gas within them. Over time, the rate of star formation gradually declines. Many galaxies lose their distinctive spiral arms. Slowly, they evolve into elliptical galaxies. Their light changes as well. Older stars begin to dominate. Their color shifts toward red, not because the galaxy is dying, but because it has entered a different phase of its life. It is a beautiful idea. Nature has no concept of success or failure for a galaxy, only different evolutionary paths. One phenomenon that especially fascinates astronomers is galactic mergers. Within a cluster, two galaxies may slowly drift toward one another under the influence of gravity. The process unfolds over hundreds of millions of years. There is no deafening collision, no explosive impact like those seen in science fiction films. Their spiral arms are gradually stretched. Their gas becomes stirred and reshaped. The orbits of billions of stars slowly change. Eventually, the two galaxies merge, forming a single, larger galaxy. If billions of years could be compressed into only a few minutes, the scene would resemble two luminous clouds slowly blending together across the sky. From a symbolic perspective, This recalls another idea closely associated with Carl Gustav Jung. He viewed human development not as a fixed, unchanging path, but as a continuous process of transformation shaped by experience and environment. This is simply a philosophical reflection rather than a comparison between galaxy evolution and psychology. Even so, both suggest a familiar truth. Identity is shaped not only by where we begin, but by the entire journey we travel. Perhaps the greatest lesson the cosmic web offers in this chapter is that no galaxy possesses a fixed destiny. Every galaxy has the capacity to change. Each environment opens a different path of evolution. Every encounter leaves its mark. Every fresh supply of gas creates an opportunity for new stars to form. Every merger begins the story of a new structure. The history of a galaxy is therefore not a collection of disconnected events. It is one continuous narrative, written by gravity, nourished by gas, shaped by time. When astronomers observe a galaxy today, they do not see only its present. They are reading the oldest chapters of a very ancient book. Its shape tells the story of past collisions. Its stellar populations reveal periods of intense star formation, or long epochs of quiet. Its remaining gas reveals the environments through which it has traveled. Even its location within the cosmic web forms part of that story. Perhaps that is why the night sky has never been merely a collection of distant lights. It is a library. Every galaxy is a book. Every galaxy cluster is a chapter. And the cosmic web is the immense bookshelf quietly preserving the evolutionary history of them all. As the night grows ever more peaceful, imagine that our own Milky Way is still continuing this journey. It is not standing still. It is traveling with the local group within Laniakea, and together with the entire cosmic web. Billions of years from now, our galaxy will continue to change, encounter new companions, and eventually merge with the Andromeda galaxy, opening an entirely new chapter in the history of the region of space we call home. The first galaxies. As we concluded the previous chapter, we discovered how light allows humanity to look back through time itself. Every distant galaxy is not merely a point of light in the sky, but a memory that has been slowly traveling toward us for billions of years. Through redshift surveys, astronomers have reconstructed a three-dimensional map of the cosmic web, allowing us to trace the history of the universe from the present day back into unimaginably ancient eras. But if we continue traveling farther into the past, another profound question naturally arises. What happened before the first mature galaxies came into existence? What did the universe look like before brilliant spiral galaxies, before enormous galaxy clusters, and before the cosmic web had fully taken shape? To answer that question, we must journey back to the dawn of cosmic history, an era astronomers often call the cosmic dawn. After the Big Bang, the universe did not immediately fill with stars. Quite the opposite. For an extraordinarily long period, space contained little more than hydrogen, helium, and dark matter. There were no planets, no galaxies as we know them today, no starlight illuminating the darkness. This period is often known as the Cosmic Dark Ages. It is a name that sounds almost melancholy. Yet it was not a darkness of despair. It was the quiet stillness. Before the first lights were ever kindled, imagine standing in a great forest during the final moments before sunrise. Everything is silent. The trees remain motionless. The birds have not yet begun to sing. The first rays of sunlight have not yet reached the leaves. Nothing appears to be happening. Yet beneath that silence, the entire forest is waiting. The universe experienced a similar moment. It was not empty, nor was it lifeless. It was simply waiting for gravity and time to continue their patient work. Although no stars yet existed, the tiny density fluctuations left behind after inflation had never disappeared. Gravity continued gathering matter, slowly, steadily, without interruption. Dark matter formed invisible halos. Hydrogen and helium gradually fell into those gravitational wells. Over millions of years, the densest regions accumulated more and more material. Eventually, some of those clouds became so massive that gravity compressed them until their centers grew unimaginably hot. And then, for the first time, the universe witnessed something entirely new. The first stars were born. Astronomers often refer to these pioneering stars as population 3 stars. No one has yet observed one directly. Even so, our best theoretical models suggest they were very different from the stars we see today. They formed from almost pure hydrogen and helium because the heavier chemical elements had not yet been created. Many of them were likely enormous, dozens, perhaps even hundreds, of times more massive than our Sunday. Because of their tremendous mass, they burned through their nuclear fuel incredibly quickly. Their lives may have lasted only a few million years, a mere instant on the timescale of the universe. Yet, during those brief lives, they transformed everything. Inside their blazing cores, the first heavy elements were forged: carbon, oxygen, silicon, iron, the very ingredients that would one day become planets, oceans, mountains, and eventually living beings. When these giant stars reached the ends of their lives, they exploded as powerful supernovae, scattering those newly created elements across space. The universe was no longer made of only hydrogen and helium. For the first time, it became chemically richer. In many ways, those first stars were the universe's earliest artists. They painted the cosmos with colors that had never existed before. From a symbolic perspective, this recalls a theme often found in the writings of Carl Gustav Jung. He suggested that genuine transformation frequently begins quietly, long before its results become visible. This is simply a philosophical reflection rather than a comparison between stellar evolution and psychology. Even so, both remind us that the most profound beginnings often unfold in silence before revealing themselves to the world. As more stars appeared, their light gradually spread across the cosmos. The long darkness slowly began to fade. This marked another pivotal chapter in cosmic history, the epoch of reionization. Before this era, most of the hydrogen filling the universe existed in a neutral state, which absorbed much of the light traveling through space. As the first generations of stars and young galaxies emitted enormous amounts of ultraviolet radiation, that neutral hydrogen began losing its electrons, becoming ionized once again. Little by little, the cosmic fog lifted. Light could travel much farther. The universe became increasingly transparent. Imagine a valley wrapped in thick morning mist. At first, only the nearest trees are visible. Then, as the sun slowly rises, the mist begins to dissolve. More of the landscape comes into view. Eventually, the entire valley emerges. Reionization transformed the universe in much the same way. It did not happen all at once. It unfolded gradually, over hundreds of millions of years. One region after another, the darkness gave way to light. The first galaxies also began to gather. They were much smaller than galaxies like the Milky Way. Many were irregular in shape. Many were still rapidly assembling. Yet, they became the first building blocks of everything that would follow. They merged. They grew. They exchanged gas. They continued producing new generations of stars. Slowly, the earliest threads of the cosmic web became increasingly visible. The immense structure we observe today did not appear suddenly. It emerged patiently, step by step, over billions of years. Perhaps this is one of the most beautiful ideas in astronomy. The greatest structures in the universe did not begin as great structures, that they began with tiny fluctuations, the first stars, small young galaxies, and the quiet persistence of gravity. As the night grows deeper, imagine yourself standing beneath a sky unlike any we know today. There is no glowing band of the Milky Way, no familiar constellations, only vast darkness, broken by the appearance of the very first stars, one after another, like distant candles being lit across an endless plain. Each tiny light marks the beginning of a story. Each newborn galaxy becomes another thread woven into the cosmic web, and together, over billions of years, those first faint lights will grow into the magnificent universe we call home today. The trees were already there, the ground was already there, the air was already moving, but the light had not yet appeared. It only took the first rays of sunrise for the entire forest to change. The early universe experienced a remarkably similar moment. During its first few 100 million years, vast hydrogen clouds drifted quietly through space. At that time, hydrogen was the most abundant element in existence. It was like the first bricks nature would use to build everything that came afterward. Under the influence of gravity, these primordial hydrogen clouds slowly began to collapse, not rapidly, not violently, but with extraordinary patience. Over tens and then hundreds of millions of years, matter gradually became more concentrated. Density increased, temperature rose, until, in certain regions, the first miracle occurred. The first stars ignited. Perhaps this was one of the most beautiful moments in the entire history of the universe. Before that moment, there had never been a single star. There had never been starlight. There had never been heavy elements such as carbon, oxygen, or iron. Those first stars became nature's earliest nuclear furnaces. Deep within their cores, hydrogen gradually fused into helium and eventually forged heavier elements. When those ancient stars reached the ends of their lives and exploded as supernovae, they scattered these newly created elements throughout space. Those elements would later become planets, oceans, forests, and eventually, every one of us. That means every carbon atom within the human body was once forged inside generations of ancient stars. From a symbolic perspective, this recalls an idea often found in the work of Carl Gustav Jung. He frequently suggested that the deepest layers of the present are nourished by origins that reach far into the past. This is simply a philosophical reflection, not a comparison between stellar evolution and psychology. Nevertheless, both invite us to consider that everything existing today still carries the imprint of a very ancient beginning. The appearance of the first stars did more than create light. It transformed the very state of the universe itself. Powerful ultraviolet radiation emitted by these stars began ionizing the neutral hydrogen that filled space. This process is known as reionization. It marks one of the most important eras in cosmic history. Before reionization, most hydrogen existed in a neutral state. Afterward, more and more hydrogen became ionized. Space gradually became transparent to many forms of radiation. Light from galaxies could travel much farther. Large-scale cosmic structures slowly became visible. You might imagine reionization as the moment when a thick morning fog gradually dissolves beneath the rising sunday. The forest itself has not changed, but as the fog thins, every shape begins to emerge. The universe experienced something much like that, not over a few minutes, but across hundreds of millions of years. It was an era during which the first stars did more than illuminate themselves. They opened the way for the formation of the first galaxies. Those first galaxies were initially very small, far less massive than today's Milky Way. They continuously merged with one another, accreted fresh gas, formed new generations of stars. Over billions of years, they gradually grew into the galaxies we observe throughout the modern universe. Every mature galaxy once had a childhood. Every giant galaxy cluster began as an extraordinarily small seed. And the cosmic web that we continue exploring today was once nothing more than delicate strands of matter slowly taking shape. Perhaps the most beautiful reminder in this chapter is that even the grandest structures in the universe began with remarkably humble beginnings. At the end of the previous chapter, we traveled nearly 13 billion years into the past to witness the era when the first stars began illuminating the cosmic darkness. Primordial hydrogen clouds slowly collapsed under gravity. The first natural nuclear furnaces ignited within ancient stars. Reionization quietly transformed the state of the universe, opening the path toward the birth of the first galaxies. Yet all of these events occurred billions of light years away and billions of years ago. So how can humanity observe such a distant age today? This is where modern telescopes enter the story. For centuries, humanity observed the heavens primarily through visible light. But visible light reveals only a small fraction of the universe. It is like listening to a symphony while hearing only a few instruments. To understand the full performance, we must learn to listen across many different frequencies of nature. One of the instruments expected to open that window is the Square Kilometre Array, SKA. This is not a single telescope. Instead, it is a network of thousands of radio antennas spread across sites in South Africa and Australia, working together as one enormous radio observatory. What makes the SKA extraordinary is not merely its size, it is its ability to detect incredibly faint radio signals that began their journeys during the earliest moments of cosmic history. In astronomy, seeing does not always mean using our eyes. Sometimes it means learning to listen to wavelengths that human vision can never perceive. Imagine standing in the middle of a forest at night. If you rely only on your eyes, you will notice very little. But if you listen carefully, you begin to hear insects, the wind, running water, and countless other sounds quietly telling the forest's story. Radio telescopes perform a similar task. They do not search for brilliant light. They listen for the faint whispers the universe continues to broadcast. One of the most important of these signals comes from neutral hydrogen. Hydrogen is the first and most abundant element in the universe. Before mature galaxies existed, much of space was filled with primordial hydrogen clouds. By studying hydrogen's characteristic radio emission, particularly the famous 2-1 centimeter line, stretched by the expansion of the universe, astronomers can trace the history of the cosmic dawn and the era of reionization. It is much like reading faint ink on the first page of an ancient manuscript. The writing is no longer clear, but with enough patience and the right tools, the story slowly reveals itself. From a symbolic perspective, this recalls an idea closely associated with Carl Gustav Jung. He often suggested that the deepest layers of human experience cannot be understood solely through what is immediately visible, but require patient attention to subtle and easily overlooked signals. This is simply a philosophical reflection, not a comparison between radio astronomy and psychology. Nevertheless, both remind us that the faintest traces sometimes open the door to the deepest understanding. With observatories such as the SKA, together with other next-generation telescopes, scientists hope to answer questions that once seemed impossible. How massive were the first galaxies? Did the first stars form rapidly or gradually? Did reionization occur everywhere at once, or spread region by region? Did the early cosmic web already resemble the network we see today? Or was it still far simpler? Each answer will bring us closer to understanding the origin of the immense cosmic structure we observe today. What is especially remarkable is that the more astronomers study the first galaxies, the more they realize that the universe did not evolve through sudden leaps. Everything unfolded gradually, from tiny quantum fluctuations to primordial hydrogen clouds, then the first stars, then the first galaxies, those first filaments, then galaxy clusters, and finally, the vast cosmic web stretching across the universe. No chapter stands apart from the next. Every stage prepares the way for what follows. Perhaps that is why the history of the universe resembles a grand symphony. No note is unnecessary. No melody appears by chance. Every movement follows the one before it with a rhythm that is extraordinarily slow, yet remarkably precise. As the night grows quieter, imagine that somewhere unimaginably far away, faint radio signals emitted by ancient hydrogen clouds are still continuing their journey. They have traveled across billions of light years, passing countless galaxies, filaments, and the immense voids of the cosmic web. It may take many more years of observation, generations of increasingly powerful telescopes, and extraordinary human patience before those signals are fully deciphered. Yet they are still there, faithfully carrying the memory of the universe's first dawn. Perhaps the greatest beauty of this chapter is not that it teaches us a few more astronomical concepts. Rather, it leaves us with the feeling that everything truly great often begins with something very small. A cloud of hydrogen, a first star, a young galaxy, a faint ray of light. Given enough time, all of them together became the largest network humanity has ever known. And perhaps this is how nature has always created. Never in haste, never for display, simply allowing time to patiently complete its work. In the next chapter, we will continue following that journey as we explore the future of the cosmic web. We will discover what happens as dark energy continues expanding space, why the most distant galaxies will gradually disappear beyond our observable horizon, and why, in the unimaginably distant future, the local group may become the entire visible universe for the astronomers of that era. The future of the cosmic web. As we concluded the previous chapter, we journeyed back to the dawn of the universe to meet the first hydrogen clouds, the first stars, and the young galaxies that began illuminating the darkness left behind by the Big Bang. We watched the cosmic web grow, little by little, over billions of years, from tiny primordial fluctuations into the immense network that now connects hundreds of billions of galaxies. But if the universe has experienced both a beginning and a long period of growth, does it also have a future? What will become of the cosmic web tens or even hundreds of billions of years from now? Will this magnificent network continue growing forever? Or will it one day enter an entirely new chapter of its history? This is one of the deepest questions in modern cosmology. Interestingly, the answer does not begin with galaxies. It begins with space itself. Throughout the previous chapters, we have often mentioned dark energy. This is the name scientists give to the phenomenon responsible for the accelerating expansion of the universe. An important point to understand is that galaxies are not necessarily flying through space like spacecraft. Instead, the space between them is gradually expanding. A helpful analogy is a loaf of raisin bread rising in an oven. If raisins are embedded throughout the dough, the distances between them increase as the dough expands. The raisins do not need to move on their own. It is the dough between them that grows. This is only a visual analogy, because the expansion of space is not literally the same as rising bread. Nevertheless, it helps illustrate how, on the largest cosmic scales, galaxies can become farther apart even when they are not moving away in the everyday sense. Over billions of years, gravity and dark matter have worked together to build the cosmic web. They pulled matter together into filaments. They assembled galaxy clusters. They created the largest structures known in the universe. At the same time, dark energy has never ceased its own quiet work. It has continuously stretched space itself. Today, observations indicate that on the largest scales, this accelerating expansion is becoming the dominant influence governing the universe's evolution. That means that in the unimaginably distant future, dark energy will play an even greater role. This does not mean the cosmic web will suddenly disappear. There will never be a day when the entire network simply falls apart. Everything happens extraordinarily slowly, so slowly that millions of generations of stars will be born and die before the greatest changes become obvious. Galaxy clusters already held tightly together by gravity can continue to exist. However, the distances between clusters, separated by enormous expanses of space, will continue to increase. The filaments connecting distant regions will gradually become stretched. The cosmic web will not vanish. Instead, its network will become increasingly separated on the larger scales. Imagine a spider web covered with morning dew. At first, every strand is clearly visible, each connected to the next. But after a very long time of gentle wind, different parts of the web slowly drift farther apart. The openings between the strands become larger. the points of connection become fewer, not because the web has been torn apart, but because the distances between its different regions continue to grow. This image closely resembles how many cosmological models describe the future evolution of the cosmic web. From a symbolic perspective, this recalls a theme that often appears in the work of Carl Gustav Jung. He frequently emphasized that every living system is continually moving and transforming through time rather than remaining fixed in a permanent state. This is simply a philosophical reflection, not a comparison between dark energy and psychology. Nevertheless, both invite us to recognize that change is a natural part of existence. Even more astonishing is that this gradual transformation will directly affect what future civilizations will be able to observe. Today, when we look into the sky with our largest telescopes, we can observe hundreds of billions of galaxies. We can see the cosmic web stretching across space. We see its filaments, its galaxy clusters, its immense cosmic voids. But if dark energy continues accelerating the expansion of space for tens or hundreds of billions of years, light emitted by many distant galaxies will no longer be able to reach future observers, not because those galaxies have disappeared. They will still exist. They will still shine. The space between them and the observer will simply be expanding too rapidly for newly emitted light to bridge the growing distance. As time passes, more and more galaxies will move beyond the observable cosmic horizon. It is an idea that is both strange and deeply poetic. Not everything that disappears has truly ceased to exist. Sometimes, it has simply moved beyond what we are able to see. When viewed this way, the night sky takes on a new meaning. Every galaxy visible to us today is a gift from time, one unimaginably distant day. Other civilizations may no longer be able to witness this vast cosmic panorama. At the end of the previous chapter, we imagined a universe far into the future. Under the persistent influence of dark energy, space will continue expanding ever more rapidly on cosmic scales. Filaments will become increasingly stretched. Galaxy clusters, separated by immense distances, will grow ever farther apart. Not because they vanish, but because the space between them never stops growing. Yet perhaps the question that fascinates cosmologists most is not how the cosmic web itself changes, but how the sky will change for the civilizations that come after us. Imagine a time tens or even hundreds of billions of years from now. By then, many of the stars that shine within today's Milky Way will have completed their life cycles. Countless new generations of stars will also have been born. The galaxies of the local group will have continued their gravitational dance. According to current models, the Milky Way and the Andromeda Galaxy will most likely merge into a single, much larger galaxy in the distant future. Yet the most remarkable transformation lies beyond the local group itself. The distant galaxies we observe today will gradually slip beyond the observable cosmic horizon because of the accelerating expansion of space. New light emitted by those galaxies will never reach future observers. That means the sky seen by an astronomer living in that era will be profoundly different from the one we know today. Today, our telescopes reveal billions of galaxies, vast galaxy clusters, filaments weaving together the cosmic web, immense cosmic voids. The large-scale architecture of the universe gradually reveals itself, but in the unimaginably distant future, most of that cosmic panorama may no longer be observable. For astronomers of that distant age, the local group may appear to be the entire visible universe, not because everything else has disappeared, but because its light will no longer have enough time to overcome the accelerating expansion of space. It is an idea that is both beautiful and humbling. It reminds us that every civilization's view of the universe is inseparable from the era in which it exists. Had humanity appeared too early, the cosmic web would not yet have formed. Had we appeared far too late, most of it would already lie beyond our reach. We happen to exist during a remarkably special epoch, when the universe is mature enough to reveal its grand structure, yet not so expanded that it has hidden its own history. Imagine standing atop a mountain at sunrise. Arrive too early, and everything remains hidden in darkness. arrive too late, and mist conceals the distant peaks. Only during a brief window does the entire landscape reveal itself. According to our current understanding of cosmology, humanity lives during just such a fortunate moment for observing the largest structures in the universe. From a symbolic perspective, this recalls an idea closely associated with Carl Gustav Jung. He often suggested that the meaning of an experience depends not only on the event itself, but also on the time and circumstances in which we encounter it. This is simply a philosophical reflection, not a comparison between cosmology and psychology. Nevertheless, both remind us that timing is itself part of truth. Perhaps that is why, when astronomers study the cosmic web today, they are doing more than investigating the present. They are preserving a cosmic portrait that future civilizations may never again have the opportunity to see in its entirety. Every three-dimensional galaxy map, every redshift measurement, every observation of a filament, each becomes part of the universe's own memory. There is something profoundly beautiful in that thought. The universe continues to change. Our ability to observe it changes as well. No perspective lasts forever. No window remains open forever. That is why every scientific discovery made today possesses the value of a moment that can never be repeated. As the night outside your window grows ever quieter, imagine an astronomer living in that unimaginably distant future. Standing beneath the sky of a distant world, they look upward and see only one enormous galaxy, the merged descendant of the Milky Way and Andromeda, together with the stars contained within it. No vast walls of galaxies stretching across space. No filaments connecting galaxy clusters over billions of light years. No obvious evidence that the universe was once so unimaginably immense. Without the observations humanity collected during our own era, those future scientists might find it extraordinarily difficult to discover that beyond their galaxy, there once existed a vast cosmic web. Perhaps that is what makes this chapter one of the quietest in our entire journey. Not because it tells the story of an ending, but because it tells the story of a transition. The universe will continue, stars will continue to be born, galaxies will continue to evolve, but the way they are seen will change. And sometimes, what changes is not the world itself, but the window through which we observe it. Perhaps that is the final gift the cosmic web offers us. It reminds us that everything belongs to the flow of time. Even human understanding is part of that flow. Every time we look up at the night sky today, we are participating in a uniquely precious meeting between human curiosity and a universe that happens to exist at exactly the right moment to tell its story. In the final chapter of our journey, we will set aside equations, telescopes, and numbers to reflect on the philosophical meaning of the cosmic web. We will explore why empty space also carries meaning, why no galaxy is ever truly isolated, and what the largest network in the universe may be quietly trying to tell each of us before our voyage beneath the stars comes to an end. The philosophical meaning. As we concluded the previous chapter, we looked toward the unimaginably distant future of the universe. We imagined a time when, under the influence of dark energy, most galaxies would gradually drift beyond the observable horizon, leaving the local group as a lonely island in an ever-expanding sea of space. It was a vision both majestic and deeply quiet. And perhaps it is precisely here that our journey arrives at its final question. After everything we have explored, from the tiny quantum fluctuations that followed the Big Bang to the cosmic web spanning billions of light years, what is the cosmic web truly trying to tell us? Perhaps the first lesson is a beautiful paradox. Even emptiness has meaning. Throughout our journey, we have often spoken of the cosmic voids. Vast regions of space so immense that they seem almost completely empty. If we relied only on intuition, it would be easy to assume that the regions containing fewer galaxies must somehow be less important. But science tells a very different story. It is those vast, empty spaces that allow the filaments to stand out. It is because the voids exist that the great galaxy clusters become so striking. The differences in the density of matter are what give rise to the entire architecture of the cosmic web. Without the empty regions, the network would no longer be a network. Perhaps it is much like a piece of music. We often fall in love with the notes themselves. Yet it is the silence between the notes that creates the rhythm. If every sound flowed together without pause, music would become nothing more than noise. The same is true in painting. Light only becomes truly radiant because shadows exist. And in poetry, some of the most meaningful lines are the ones that are never written, yet quietly linger in the reader's heart. The universe seems to create in much the same way. It does not fill every corner with matter. Instead, it leaves behind vast stretches of emptiness, allowing those empty spaces to tell the rest of the story. From a symbolic perspective, this gently echoes an idea often found in the work of Carl Gustav Jung. Throughout many of his writings, he suggested that our inner lives are shaped not only by what consciousness can clearly perceive, but also by deeper layers that remain unseen. This is simply a philosophical reflection, rather than a comparison between cosmic voids and psychology. Even so, both invite us to consider that what appears empty may still hold profound significance within the larger structure. The cosmic web also offers another quiet reminder. No galaxy is ever truly isolated. For centuries, when humanity first began exploring the night sky, each galaxy seemed like its own solitary island of light. Today, we know that picture is incomplete. Galaxies are connected through gravity, through filaments of matter, through streams of gas, and through a shared history stretching back nearly 14 billion years. Even galaxies drifting within the immense cosmic voids are not completely detached. They still belong to the cosmic web. They still respond to the same universal laws that shape the cosmos as a whole. Perhaps the best way to imagine this is to think of the leaves on an ancient tree. Viewed one by one, each leaf appears independent, but deep beneath the surface, they are all connected to the same trunk, the same roots, drawing water from the same source. The cosmic web is much like that. Galaxies are simply luminous leaves growing upon the immense branches of the universe. And that realization changes the way we look at the cosmos. Instead of asking, how does this galaxy exist on its own? Astronomers today are more likely to ask, what is it connected to? Which filament does it belong to? How has its environment shaped its evolution? Perhaps those questions are beautiful in themselves, because sometimes, to truly understand something, it is not enough to study the object alone. We must also understand the relationships that helped create it. That is why the cosmic web is more than an astronomical discovery. It is also a new way of seeing the universe, a perspective in which every structure exists within something even larger. Each galaxy belongs to a group. Groups belong to clusters. Clusters belong to superclusters. And the superclusters themselves are woven into the cosmic web. Nothing truly exists outside the network. Perhaps this is one of the most beautiful ideas science has ever revealed. Not because it makes humanity seem greater, but because it reminds us that we live within a reality far larger than our imagination first allowed us to believe. And as we continue expanding that perspective, one final question quietly emerges. If every galaxy is part of the cosmic web, then could we, formed from atoms forged in the hearts of ancient stars, also be part of that same story? That is the final reflection we will step into together as our journey draws toward its close, before we end this evening beneath a peaceful sky filled with stars. As we brought the previous chapter to a close, we reflected on one of the most beautiful messages the cosmic web offers us. Emptiness is not the absence of meaning, and no galaxy truly exists in isolation. The invisible filaments connecting galaxy clusters remind us that even on the grandest scales of the universe, existence is always woven together through relationships. And now, as our journey draws near its end, only one simple question remains. If every galaxy is part of this vast network, then where do we, as human beings, belong within the greater picture of the cosmos? Perhaps this is no longer a question belonging only to astronomy, nor is it solely a question of philosophy. It is a question each of us can quietly carry while looking up at the night sky. From the perspective of science, the answer is both humble and extraordinary. Our bodies are made of atoms: carbon, oxygen, nitrogen, calcium, iron. None of these elements existed immediately after the Big Bang. They were forged deep within the hearts of the earliest generations of stars, and in the countless stellar generations that followed through the process of nuclear fusion. Later, many of these elements were scattered into space as stars reached the ends of their lives, especially during supernova explosions and through other stages of stellar evolution. Over billions of years, those atoms became part of vast clouds of gas. They formed new stars, new planets. Eventually, they became part of the Earth. And much later still, they became part of each of us. In the most literal physical sense, human beings are truly made from the material of the universe. We do not stand outside the cosmic web. We are a very late chapter in the long history that the cosmic web helped make possible. That does not mean the universe was created for humanity. Science makes no such claim. But science does show that we belong to the same material history as the stars and the galaxies. Perhaps that realization alone is enough to make the night sky feel much closer than before. From a symbolic perspective, this gently echoes a theme often found in the work of Carl Gustav Jung. In many of his writings, he viewed human beings as part of a reality far greater than the individual ego, where relationships and symbols play an important role in shaping the meaning of life. This is a philosophical reflection rather than a scientific conclusion about the universe. Even so, it suggests that exploring the heavens can also become a way of exploring ourselves. Perhaps that is why, after all the immense numbers, after the distances measured in billions of light years, after terms such as dark matter, cosmic void, and filament, what remains is not simply knowledge. It is a feeling, a deep and peaceful feeling. The feeling that we live within an orderly universe. A universe in which even the greatest structures emerged from simple, patient, and consistent laws working across billions of years. Not every mystery has been solved. We still do not know what dark matter truly is. We still do not understand the nature of dark energy. We are still searching for the very first galaxies, still listening for the faint whispers carried from the dawn of the universe. But perhaps the beauty of science has never been about having every answer. Its beauty lies in the courage to keep asking questions, and in the humility to accept that every new answer reveals even deeper mysteries. As we look back upon our entire journey tonight, we have traveled from quantum fluctuations smaller than an atom to the birth of the cosmic web. We followed galaxies as they grew, explored the mystery of dark matter, looked back through time by following ancient light, returned to meet the first stars, then lifted our eyes toward the unimaginably distant future of the universe. Each chapter seems to have been connected by an invisible thread, the thread of connection. Perhaps that is what the cosmic web has been quietly whispering to us all along. No galaxy truly stands alone. No star appears apart from the history of the universe. No atom within our bodies was born outside the long journey of ancient generations of stars. And no journey of discovery ever truly comes to an end. It simply opens another door. Now, as the night outside your window grows quieter, allow your thoughts to drift like a gentle cloud, floating among the invisible filaments of the cosmic web. Imagine the Milky Way continuing its silent rotation around its galactic center. Picture distant galaxies still moving to the slow rhythm of gravity. Ancient rays of light are still crossing the vastness of space, carrying stories that began billions of years ago. And our own small Earth continues its quiet voyage with the local group through this immense cosmic network, just as it has for millions of years, and will continue to do long after tonight has come to an end. If your eyelids are beginning to feel heavy, if your breathing has become slow and steady, perhaps now is the perfect time to let every thought gently settle. There is no need to remember every number, no need to hold on to every scientific term. Simply carry with you the feeling that you have just completed a remarkable journey through the history of the universe. A journey not meant to search for greatness, but to discover the quiet beauty of connection. Thank you for joining me on this journey through the cosmic web. If these gentle stories have brought you a little peace, a fresh perspective, or simply helped you relax before sleep, I would truly appreciate it if you took a moment to subscribe to the channel. Every subscription, every like, and every share helps us continue creating new journeys where science, history, and reflections on what it means to be human come together beneath a sky full of stars. And now, let every sound slowly fade away. Let your breathing become soft and effortless. Let your thoughts drift with the slow current of the galaxies. And remember that somewhere far beyond tonight's night sky, the cosmic web is still quietly telling its story. With the patience of billions of years, I wish you a deep sleep, a peaceful sleep, and perhaps, somewhere within tonight's gentle dreams, you will continue your journey among the stars once again. And with that, our journey together this evening is gently drawing to its final moments. If you are still listening at this moment, then perhaps we have just completed one of the longest journeys the human imagination can ever take. Together, we left the Earth behind, traveled beyond the Milky Way, crossed the local group, drifted along the immense filaments of the cosmic web, and gazed upon galaxy clusters, vast cosmic voids, and ancient light that began its journey billions of years ago. We witnessed how tiny fluctuations after the Big Bang, smaller than an atom itself, slowly evolved through the patient work of gravity and the passage of time into the largest structure humanity has ever discovered. We encountered dark matter, the invisible framework of the universe. We reflected on dark energy, the mysterious force quietly stretching the fabric of space itself. We watched rivers of plasma, millions of degrees hot, flowing silently between the galaxies. We followed ancient light back through time to meet the very first stars, the first galaxies, and the dawn of the cosmic web. And then we lifted our eyes toward the unimaginably distant future, where the night sky, seen by civilizations yet to come, may look entirely different from the one above us today. Yet perhaps, after all of that scientific knowledge, what remains with us is not merely a collection of astronomical concepts. What remains is a feeling that is difficult to put into words. The quiet realization that we live within a universe far greater than anything our eyes alone can perceive. In our everyday lives, we measure time in relatively small pieces: a day, a week, a year. Sometimes, a single lifetime seems long enough to hold countless memories. But when we look up at the night sky, we suddenly realize that nature tells its story using entirely different measures: millions of years, hundreds of millions of years, billions of years. To the universe, patience seems to be one of its fundamental laws. No star is born in a hurry. No galaxy grows overnight. No cosmic web appears in an instant. Everything takes time. Everything matures, little by little. Perhaps that is one of the universe's quietest gifts to us. It reminds us that not everything beautiful has to arrive quickly. Not every answer needs to appear all at once. Some seeds need years before they begin to grow. Some rivers require ages to carve a valley. Some galaxies need billions of years to reach maturity. And some people simply need time to understand themselves. From the symbolic perspective often found in the work of Carl Gustav Jung, the journey outward into the universe and the journey inward into ourselves can illuminate one another. When we patiently observe the vastness of the cosmos, we sometimes learn to observe our own inner lives with greater calm and understanding. This is a philosophical reflection rather than a scientific conclusion, but perhaps it is one reason why looking up at the night sky has always carried such a special feeling. Interestingly, the cosmic web also teaches us a remarkably simple lesson. No galaxy truly exists alone. Every galaxy belongs to something larger. Every cluster is part of a greater network. Even the immense voids spanning hundreds of millions of light years contribute to the beauty of the whole. Nature seems to remind us that connection is just as important as presence. Some of the most important things cannot be seen, yet they quietly support an entire system, like gravity, like dark matter, like the ancient light that patiently traveled across billions of years to reach human eyes, and perhaps, like the quiet kindness we offer one another in everyday life. Tonight, as you prepare to close your eyes, try holding on to one simple image. Imagine the Milky Way continuing its slow, graceful journey within the cosmic web. The invisible filaments still connect millions of galaxies. New stars are still being born somewhere unimaginably far away. Ancient rays of light continue their silent voyage across the vastness of space, carrying stories that began at the dawn of time. Within that immense picture, the Earth is only a tiny point, and each of us is smaller still. Yet our smallness does not make our existence any less meaningful. If anything, it makes every moment spent gazing at the sky, every question we dare to ask, and every glimpse of the universe's beauty feel all the more precious. Perhaps the greatest wonder is not how vast the universe truly is. Perhaps it is that one tiny part of the universe has become capable of looking back at the universe itself and wondering where it came from. And if tonight has brought you even a small measure of peace, a spark of curiosity, or simply helped your mind grow a little lighter before sleep, then this journey has already fulfilled its greatest purpose. Thank you for spending this time with us, from the very beginning of our journey until this final moment. If you enjoy these gentle stories about the universe, history, science, and thoughtful reflections on what it means to be human, all told in a slow, relaxing rhythm to help you drift into sleep, please consider subscribing to the channel, turning on notifications, and joining us on future journeys. Every subscription is more than a show of support. It helps us continue creating new adventures where knowledge and peace meet beneath a sky full of stars. And now, take one slow, gentle breath in and let it out even more slowly. Allow your shoulders to relax. Let every lingering thought quietly settle. Let this story fade away like small waves dissolving upon the surface of a calm night sea. Out there, the galaxies continue their endless journey. The cosmic web still unfolds in harmony with the rhythm of time. The stars continue to shine in silence, and the night sky patiently waits for anyone willing to look up. May you have a truly peaceful night. May your mind find rest after a long day. May your dreams be as gentle as ancient starlight quietly crossing the universe. And perhaps, in one of those gentle dreams, we will meet again among the galaxies, listening together to the stories the universe has been telling for nearly 14 billion years. Sleep well, and until our next journey together, good night.